Good morning, everyone. Welcome again to our weekend webinar. Try to choose a different topic, but a lot of you guys wanted some revision on subwoofers and everything, so we are going to try and do some revision today. And just to introduce everyone who's there with us today, we have Nitesh with us, who's head of tech support. Nitesh, you can say hi to everyone.
Hi everyone. Thanks to everyone for coming in.
And we also have Rajesh Khade, who is the Smart and Dante trainer and also the distributor for Smart. Rajesh, you can say hi.
Hi everyone. Hello. Good morning.
सभी को आज वेलकम. मुझे कुछ कॉल्स आए सुबह कि ये आज का कंटेंट थोड़ा इंग्लिश में भी करना चाहिए. काफी लोग साउथ में उन्होंने बोला कि हिंदी हमारी राष्ट्रभाषा है, बट फिर भी उनको इंग्लिश में ज्यादा कंफर्ट है, तो मैं दोनों लैंग्वेजेस में जितना हो सके एक साथ कंटेंट शेयर करना चाहूंगा. जस्ट टू स्टार्ट ऑफ इमीडिएटली, सबको आज वेलकम. हमारे साथ आज नितेश है, जो आप हमारे साथ सब वेबिनार में स्टार्टिंग से रहे हैं. वो हेड ऑफ टेक सपोर्ट है. और हमारे साथ ही साथ डॉक्टर राजेश खड़े हैं, जो स्मार्ट के सर्टिफाइड और ट्रेनर है, और डांटे के सर्टिफाइड ट्रेनर है, और स्मार्ट के ऑल्सो डिस्ट्रीब्यूटर है. हम आज थोड़ा स्मार्ट दिखेंगे. जैसे कि लास्ट टाइम हमने एक स्मार्ट का डेमो वर्जन को डाउनलोड करने के लिए कहा था. अगर आपने सबने डाउनलोड किया है, बहुत ही अच्छा होगा. इफ नॉट, जस्ट पे अटेंशन एंड go with us. We'll try and keep it as simple as possible. So moving on, just to get an idea what we're going to be doing over the next few hours, we are going to be doing a basic overview of measurement systems, smart, and some concepts again for 30 minutes. अगले 30 मिनट के लिए हम थोड़े basics measurement के overview और smart के लिए करेंगे. बहुत से लोग यहाँ जो आए हैं, उन्होंने बोला है कि उनको कुछ थोड़ा रिवीजन चाहिए. उन्हें कुछ सबवूफर या अलग अलग टॉपिक्स के ऊपर थोड़ा एक रिविजिट चाहिए. We also going to be doing revision of subwoofer techniques for 30 minutes. Just try and do some simulation. Again, बहुत लोगों ने बोला कि हम अपने कंप्रेसर और लिमिटर को कैसे सेट करें. उसके ऊपर थोड़ा हम लोग थोड़ा और विस्तार में बात करेंगे. We are going to speak a little in detail on compression and limiter settings for 30 minutes. We are going to do infinite impulse response crossovers with slopes, जो हमारे रेगुलर जो भी DSP प्रोसेसर्स है, DVX या BSS या सिलिका, बहुत से अलग अलग DSP प्रोसेसर है. मरानी जो हम आज यूज कर रहे हैं, उसमें इनफाइनाइट इंपल्स रिस्पॉन्स के क्रॉसओवर, अलग अलग स्लोप और क्रॉसओवर्स के सेटिंग के साथ क्या रिस्पॉन्स हम एक्सपेक्ट करते हैं. वी आर गोइंग टू गेट इनटू दैट एंड व्हाई इज इट डिफरेंट फ्रॉम FiR filters. So the main subject for 2 hours, you're going to be looking at FiR filters, the advantages, disadvantages, how to use them, and बहुत से high end system जैसे कि सभी, अगर आप एलोकुस्टिक देखेंगे या DNB या एडमसन या मेयर साउंड या कोई भी देखेंगे, EAW, almost all of them have FiR filtering in their systems. So most of the bigger systems, DNB, Adamson, acoustics, they all use FiR filtering. Where do we use them? What are the advantages, disadvantages? How do we set it up? We are going to try and demystify them. उसके अंदर क्या secret है? We are going to try and learn about it. Third party software use करके, and there are quite a few manufacturers who have FiR filtering in their system, in their DSP. बहुत से मैन्युफैक्चरर है जिनके पास FiR filtering के options है. Some of them are Dolby Lake. Marani is one of them. Dolby Lake उनमें से एक है, Marani है उसमें से. XTA, BSS, all the good DSP processors would be giving you an option of FiR filtering. So just quickly moving on. I don't know if I've shared my audio, but let me just stop share and share again just to make sure my audio is shared as well. And I just want to show about how a human ear works so that you guys get to know what a complicated, we don't see sound, हम sound को देख नहीं सकते, but you guys should know how complicated our hearing is. So I'm just going to be sharing a quick presentation of how we actually hear. Okay.
Our world is full of infinite sound.
Nitish, is the audio visual is audible of
Yes,
the video?
Yes.
Okay. So I'm just going to start it again.
Our world is full of infinite sounds. But how do we actually perceive them? Sounds are collected by the outer ear, which consists of the auricle and the external auditory canal. The sound is guided through the ear canal to the middle ear. The sound arrives at the eardrum, a flexible circular membrane which starts to vibrate when sound waves strike it. The sound waves are passed on by the movement of the eardrum to the middle ear. In the middle ear are 3 tiny bones, referred to as the hammer, the anvil, and the stirrup. Collectively, they are known as the ossicular chain. These form a bridge from the eardrum to the entrance of the inner ear. Their interaction increases and amplifies the sound vibrations further before these are relayed fully into the inner ear via the oval window. In the inner ear is the cochlea, which is similar in shape to a snail shell. It contains several membranous sections which are filled with watery fluids. When the sound waves vibrate the oval window, the fluid begins to move, thus setting minute hair cells in motion. These hair cells then transform the vibrations into electrical impulses, which are sent via the auditory nerve and onto the brain. What we call noises are actually just sound waves, which are transmitted through the air.
Okay, so just not to scare you all, आपको सब डराने के लिए नहीं, but sound is pretty complex. हमारे कान का response is pretty complicated. Our ear response is pretty complicated, and we are going to try and use our two. Never doubt your ears. अगर आपके कान में कुछ अजीब सुनाई दे रहा है, never doubt it. Always use tools like Smart or Systune or any of the tools that you have to assist you to make a better system. But if you hear something wrong, always rely on the fact that your ears are the better judgment. If you don't have time or something to set up a sound system, use your ears to get the best kind of output that you can. These are just merely tools that will kind of help you to understand. बहुत से सिस्टम जैसे स्मार्ट या कुछ, ये सिर्फ आपके लिए साधन है आपको समझने के लिए कि क्या हो रहा है सिस्टम में. हमेशा अपने कान पे विश्वास कीजिए. इट्स अ वेरी कॉम्प्लिकेटेड स्ट्रक्चर. Just to add, as you go, जो हमारे कान के अंदर जो साउंड वेव्स आते हैं, जो हाई फ्रीक्वेंसी है वो थोड़े बॉर्डर की तरफ रहते हैं, और जो लो फ्रीक्वेंसी है वो एकदम अंदर कॉक्लिया के अंदर, जो आपने छोटे छोटे हेयर रिसेप्टर्स देखे, द स्मॉल हेयर रिसेप्टर्स यू सी इफ यू गेट इनटू द बायोलॉजी ऑफ द ईयर, जो अंदर के छोटे रिसेप्टर्स है दैट इज मोर टुवर्ड्स लो फ्रीक्वेंसी, एंड जो बाहर की तरफ है इज मोर टुवर्ड्स हाई फ्रीक्वेंसी. With age, as you grow older, you kind of आपका high frequency का hearing ability कम होते जाता है. That's because of those receptors near the border that start losing their response with age. So just to quickly move on, one of the most important things that I would like to stress on is polarity, phase and time. बहुत से लोग confuse हो जाते हैं, polarity क्या है, phase क्या है, time क्या है. And all three are completely different. बहुत से especially home subwoofers के पीछे मैंने देखा है कि phase का पीछे एक switch दिया है जिसपे लिखा है phase. Behind there's a switch that says phase, and people press it, but it's actually the polarity is getting inverse. The positive becomes negative and the negative becomes positive. Now what happens in polarity inversion is all frequencies get inverted by 180 degrees. जब हम polarity inversion करते हैं, सभी frequencies 180 degrees से phase shift experience करते हैं. And if you're talking about phase is phase का है एक time relationship है. A versus B, मतलब कोई भी एक reference signal है या कोई भी signal 1 है, उसके compared to that, what is the phase or position of signal 2 is determined by phase. And again, time is another thing, that you may have two signals that are in phase but not necessarily in time. And we're going to try and just make sure that we know all this, so that for the first 30 minutes, once this is clear, then over the next 30 minutes and for the rest of the session, we know what's going on. So Just to quickly move on, I hope everyone has got all the questions of or the concept of polarity is completely clear. What you're seeing right now, जो आप देख रहे हैं यहाँ पे, is polarity inversion. That's it. There is nothing. Speaker के terminal को आपने reverse किया है या amplifier की तरफ से reverse किया है. ये सिर्फ आपने polarity change किया है. And then we're going to do all this in smart to understand what's exactly happening with phase and polarity. But polarity is by far the easiest. It's just an inversion. आपका पॉजिटिव और नेगेटिव को सिर्फ इन्वर्ट करेंगे एंड दैट इज अ पोलैरिटी इन्वर्जन. एंड नाउ वी आर गोइंग टू गेट इनटू फेज. जैसे कि हमने देखा एक साइन वेव है. साइन वेव एक सर्कुलर फंक्शन है व्हिच यू कैन सी एज यू आर रोटेटिंग इट अराउंड द टाइम एक्सिस. इट्स एक्चुअली अ टाइम फंक्शन दैट्स रोटेटिंग अराउंड अ सर्कल एज वी आर मूविंग द सर्कल अहेड. सर्कल को हम आगे करते हैं तो ये सर्कुलर फंक्शन को अगर सीधा 2D में प्लॉट करेंगे तो एक साइन वेव आएगा. That's the reason don't get confused. ये कोई भी mathematical equation से आप please confuse मत होइए. We are not here to prove mathematics, but just to kind of make sure what it looks like. And again, if there's a way that I can show it, अगर आप यहाँ देखेंगे sine wave और circular function को to understand why we use circular function. So यहाँ आप देखेंगे we have both the position of the wave at position 0, जो इसका phase 0 है. I'll quickly annotate that and show you guys. They're both standing at position 0, and if you move forward, it's all in a circular motion. And if you move forward, ये जा रहा है 90 degrees पे. तो आप देख सकते हैं कि circle जो 90 degrees पे आया, this as it's moving up on its peak, it's 90 degrees. So what is phase exactly? This position is 90 degrees with respect to this red जो origin हमने देखा. ये इसका नया position 90 degrees आगे है. And then as you keep going ahead, it's at 180 degrees. It goes at 270 degrees, and it goes at 360 degrees. तो ये जो phase हमने देखा ये 360 degrees एक cycle हो गया इसका पूरा complete. This cycle is now one cycle ahead with respect to the origin. So that's what you're being determined by phase. Your 360 degrees. आप एक पूरा revolution हमने आगे खत्म कर दिया ये sine wave के लिए. So phase is nothing but denoting your position in time with respect to an origin or with respect to another wave or in comparison to anything else. आप कोई भी दूसरे comparison के against phase का एक position आप check कर रहे हैं. So just quickly again, we're going to try and see what's happening on a phase. जब हम smart में देखते हैं एक मेयर साउंड का बहुत ही अच्छा animation है that Rajesh had shown as well 2 weeks ago, and I really like it. Is why it's very important to understand time and phase, and then we'll work on an Excel sheet to understand what's happening with time and phase. Why are they not always necessarily the same? So just quickly going ahead, आगे हम देखेंगे एक animation जो राजेश ने 2 हफ्ते पहले अपने presentation में किया था. हम उसको वापस देखेंगे कि ये बहुत ही अच्छा एनिमेशन है मेयर साउंड द्वारा उन्होंने बनाया है. एंड जस्ट टू क्विकली शो यू गाइस, दिस इज द फेज व्हील. आप देख रहे हैं एक पोजीशन पूरा खत्म हो रहा है. 0 डिग्रीज 360 डिग्रीज खत्म हुआ है. 720 डिग्रीज का रोटेशन हुआ है. 1080 और 1440 at the origin. Although let me see if I can pause it. At the origin जो हम 0 डिग्रीज पे आप देख रहे हैं वो इन फेज है. वो हमेशा इट्स कमिंग पासिंग थ्रू द ओरिजिन एंड ऑल द वेव्स आर at 0 but it's not necessarily, it's not all in time because one wave is at 360 degrees and although now that wave has reached this position, it's in phase but it is 1880 degrees ahead in time. So I hope the concept जो है कि it's clear that being in phase is not necessarily being in time. So now it's completed what Rajesh, can you help me out with the calculation? It's completed 10 revolutions. Oh, sorry, 6 revolutions.
Yep.
Okay. So जैसे कि आप देख सकते हैं ये 6 revolution 6 cycle ahead है in time. So it's not really in time, but both are passing through the origin of 0 degrees and it's in phase. So phase and time are completely different. So and we go ahead and just see the animation once again. So moving ahead, ये हमारा circular function है. And if you see, it is completing for, okay, so let me quickly pause this out here. जो हमारा 4 किलोहर्ट्ज का जो 4 किलोहर्ट्ज का वेव है, 4 kilohertz का time period, if we just quickly get onto the formula, 1000 divided by 4000 जो है 4 kilohertz, it's 0.25. So it's 0.25 milliseconds is the time period of 4 kilohertz. और 8 kilohertz का आप देखेंगे, sorry, 1000 divided by 8000, उसका है 0.125. तो अगर उसको 0.25 मिलीसेकेंड्स में ये इसको into 2 करेंगे, इसके 2 साइकिल खत्म हो गए. तो 8 किलोहर्ट्ज पे ये इसने 8 किलोहर्ट्ज के फ्रीक्वेंसी ने 2 रेवोल्यूशन ऑलरेडी खत्म किए. तो इफ आई एम अगेन गोइंग बैक टू माय फेज व्हील, okay, let's just resume from here. You're seeing that at 4 kilohertz it's completing 1 revolution, but 0.25 milliseconds, 720 degrees, and it, the trend just continues. ये trend आगे बढ़ते जाता है. At 8 kilohertz is giving you 2 cycles. So, and then you can see plotting on the phase graph of जो हमारे smart में phase graph है, you can see that it's this is how we plotted on a linear phase graph. And अगर उसको logarithmic में देखेंगे, so let me just pause it out here. So you can see the phase which is gone from 0 to 2, and it's, let me just highlight it here, from 0, and you can see at 4 kilohertz ये पूरा phase graph में एक cycle खत्म किया है, और वही 8 kilohertz पे उसने 2 cycle खत्म किया है. So at 8 kilohertz is going through 0.25 milliseconds, is going through 2 cycles at 8 kilohertz, and which is why we see this kind of response on the phase graph. And again, don't get too confused by it. इस पे ज़्यादा confuse होने की ज़रूरत नहीं है. You don't have to get too confused. We are going to go through it step by step again, so that everyone out here understands what we are really doing. And there's no misunderstanding. We have a good close to 200 participants again, so I want each and everyone to kind of understand. And if you all have any questions, if you all want me to repeat, अगर किसी को मुझे चाहिए कि मैं repeat करूँ, please put it, inform Rajesh and Nitesh. They're both the moderators. Rajesh is a smart certified trainer. Rajesh जो है smart certified trainer है, and he can go through it in detail with you as well. But as long as you are interested, we're just more than happy to just go through things over again. So quickly moving forward, we are just going to go through a phase wheel, but before that, I want to show you a graph. इसके पहले I just want to show you there's one Excel file which is on the website of Merlin Van Veen. Merlin Van Veen के website पे एक Excel file है जो बहुत ही महत्वपूर्ण है, and it's kind of going to help us out here to understand when you're adding 2 signals. So just before that, let me just go through period again. एक आगे बढ़ने से पहले टाइम का मैं आपको एक छोटा सा एक एग्जांपल दिखाना चाहूंगा वापस. So ये हमारा साइन वेव है, और जैसे कि आप देख रहे हैं ये 100 हर्ट्ज का साइन वेव है, and you can see the time period of that is 10 milliseconds. So if I make it, as you keep increasing the frequency, जैसे ही frequency हम बढ़ाते जाते हैं, let's say you make it 300, and you can see the time period has become 3.33. So there are a lot more a lot more cycles in the same time period of 10 milliseconds. जो नीचे है, let me highlight the time scale. So this is the time scale, which is 10 milliseconds, and the time period, which is 1000 upon the frequency in milliseconds. You can get to know that there are more cycles at 300 hertz, and you can change this to maybe 1 kilohertz, and you can see that it has 10 cycles now. उसका जो time period है 1 millisecond है. So in 10 milliseconds, it's completing 10 cycles. And then as you keep going, maybe you say 5000, and you can have a lot more cycles in that same time period. So this is something that you would see जो आप हमारे आपके oscilloscope पे आप लगाएंगे, आप एक signal generator लगाएंगे, और जैसे ही frequency बढ़ाते जाएंगे, आपको और ज़्यादा से ज़्यादा जैसे ही frequency बढ़ाते जाएंगे, उसके time period में ज़्यादा phase देखेंगे. और इसके सामने अगर आपको मैं अगर छोटे डिटेल में एक रेस ट्रैक दिखाऊंगा, जो आप देख सकते हैं here, this is a race track, and it's all by rational acoustics. 7 figures, just 7 animation है. जो लो फ्रीक्वेंसी लेके हाई फ्रीक्वेंसी तक जाते हैं, ये पूरा आप ये इन कैरेक्टर्स को देख सकते हैं. ये रेस ट्रैक है जो साइकिल जो खत्म करेंगे, एंड द सेम वे यू हैव इट देम ऑन अ सर्कुलर स्केल. How many cycles and how many this things that they are completing in a given time period. आप देखेंगे ये यहाँ हमने इसको पूरे मार्क किए, इसको फ्रीक्वेंसी और इसके टाइम पीरियड को. एंड if I am supposed to just quickly say that यहाँ हमारा ये 0 milliseconds, if I just say 0.05, आप देख सकते हैं कि एकदम जो छोटा वाला है जो 10 किलोहर्ट्ज का वेव है, यू कैन सी 10 किलोहर्ट्ज आउट हियर, व्हिच इज द टाइम पीरियड जिसका है 0.1 milliseconds. दिस इज ऑलरेडी फिनिश्ड हाफ अ साइकिल. तो आप देख सकते हैं इसका टाइम पीरियड 0.1 milliseconds है. हमने अगर 0.05 मिलीसेकंड में 10 किलोहर्ट्ज ने ऑलरेडी इतना वेव खत्म किया है. और जैसे ही हम लोग टाइम पीरियड बढ़ाते जाएंगे, लेट्स से यू मेक इट 0.2, and again in 0.2 ये जो 10 kilohertz का wave है, the 10 kilohertz has come back to the origin because it's already finished 2 cycles, whereas something at 4 kilohertz which is 0.25 would have completed almost 1 cycle that you can see out here. जो यहाँ it's on the racetrack, it's almost finishing its cycle and coming back to the origin. But जो हम low frequency में देखेंगे, which is around 50 hertz, it's barely moved. You can see that यहाँ almost उसका टाइम पीरियड 20 मिलीसेकंड है, and it's just moved 10%. So it's just, if I just show you the actual now you can see that जो low frequency is just moved 4 degrees in terms of phase. Something that is 4 kilohertz is moved 288 degrees. Something that's 10 kilohertz is already moved 720 degrees. With 360 degrees is one cycle, 308 degrees one cycle. So it's already moved 2 cycles ahead. So again, if you can see, if I just make this entire cycle, let's say 20 milliseconds. 20 milliseconds के बाद आप देखेंगे जो हमारा 50 hertz का sine wave है, that's just completed one cycle. It's 360 degrees. But the same time, that is 10 kilohertz is completed 20 cycles. Is that correct? Or 200 cycles, I think. Yeah, 200 cycles is what is completed. So 50 hertz और 10 kilohertz दोनों फेज में आप देखेंगे, इधर ये जो सर्कुलर स्केल में है, दोनों एक ही पोजीशन पे है, दोनों इन फेज है, बट दोनों का टाइम पीरियड सेम नहीं है. सो I just want to show you that being in phase is not necessarily meaning you're in time. So they all it all depends on how many cycles have been completed, and that's something you always keep in mind when you're aligning your subwoofers and all, and that we'll get to that shortly. So just wanted to show you guys what it actually looks like. Let me just close this here. So we come back and let me just clear my screen as well. Okay. And now we're just going to get back to adding two sine waves. जो दो sine waves को हम add करते हैं, हम देख सकते हैं कि okay, so here you can see there's two sine waves, A and B. यहाँ दो sine wave है हमारे पास, A और B. A का कलर है ग्रीन, B का कलर है ब्लू. हम A को देख नहीं सकते, we can't see A right now because the blue and green are overlapping each other. So you're just seeing signal B. और हम देख सकते हैं कि दोनों वेव को हम ऐड करते हैं, then we get a 6 dB addition in the final result. You can see the ratio out here. If there is any, let me just see if I can, no, actually if I zoom this, it'll kind of cut one part of the screen. So you can see that the ratio out here is 2:1. So हम दो sine wave को ऐड करते हैं. If they are in phase, you get a level change of 6 dB. So if I just add a phase offset of say minus 30 degrees, you can see now both the signals. आप दोनों सिग्नल को देख सकते हैं, A और B, और हमने उसको 30 degrees के phase shift से फर्क डाला है उस दोनों में की अंदर. And you can see that the जो उनका total level है, it is, the red level is no longer 6 dB but it's about 5.7 dB. So उसका जो ratio है, it's about 1.9:1. It's not exactly 2:1. It's about 1.9:1. And as we keep increasing the phase difference between two cycles, let's say we make it 60 degrees, and you can see right now जो A और B wave है, हमारा जो wave है, we are adding some phase shift between them, and you're seeing the level of the summation level is keeping on coming lower. Is now 1.7. जो हमारा summation level है is 1.7 1:1 का रेशियो है और उसका लेवल अभी जो 6 dB था जब दोनों फेज में थे is now 4.8 dB. We can make it minus 90 degrees. We add a 90 degree phase shift and the level still keeps going down. So let's just add 120 degrees. So whenever there's a phase difference of 120 degrees, you can see now that the level of the sum signal, जो red signal है दोनों का sum signal, you know that the level is now same. So you can see that ratio is 1:1 and there is no increase in level. जो उसका level का increase है, it's still 0 dB. So we are not kind of changing the level when there is 120 degrees of phase shift. Let's just say let's go to 150. जैसे हमने 120 degrees के ऊपर phase shift add करना चालू किया, you can see that now the level is now half. It is minus 5.7 dB. It's half of what the original level is. You can see out this from the on the graph itself. And let's just see when it is completely out of phase, or 180 degrees out of phase. Now this is, you see when this two sine wave, जो दो sine wave है, is completely, जो हमने polarity inversion किया, this could also mean a phase inversion. So polarity inversion, all frequencies go through a 180 degree phase shift, and phase inversion, we're just adding a phase inversion of this particular frequency. And you can see आपका जो red line है एकदम zero level पे है. And we're going to simulate everything in smart and see how everything works. And then we keep increasing more and more phase shift. And then again from 180 we go to 210. Again we see the level is now थोड़ा वापस zero के बदले में you're still getting some level which is lesser. And we again go from 210 to say 240. And you can see वापस 120 degrees पे जो हमारा phase जो sum signal zero था, दोनों signal के same बराबर level में था, you're getting the resultant level to be the same. And then we again go to 270, and then it starts increasing, and then you go to 300, it increases further. Let's go to 330, increases further. And when we go to 360 degrees, we have दोनों cycle in phase है, दोनों signal in phase है, but उनमें one पूरे cycle का फर्क है दोनों में. तो time में दोनों एक साथ नहीं है, but दोनों एक साथ phase में है, and you're getting this sum signal which is 6 dB above. So just quickly going back to a presentation out here, what we're showing from on our phase cycle, you can see that as we have moved, आप देख सकते हैं जैसे कि हम 0 से 120 तक गए. अगर 120 तक गए, यहाँ ये पूरे एरिया में हमें समेशन मिल रहा है क्योंकि ये 6 dB से 0 dB तक आया. Let me just kind of use a different color and use maybe green, so it's a good area to be in. So you can see out here you're adding from when the phase difference is going from 0 to 120, you're still getting some in the जो हमारा resultant signal है, you're still getting something out of adding those two signals. And let me go back and change the color. Hold on, my mouse has disappeared. And if I change the color to red, from 120 to, sorry, too much. Yeah, I think Nitesh or Rajesh have done it. From 120 to 240, you're getting a lot of cancellation. आप देख सकते हैं अलग-अलग color में है ये. At 240 degrees, again you're back to 0. And then again, once from 240 to 360, you're getting some good summation in your signals. Now, just quickly moving on, I want to show you what happens when we are crossing between low frequency to mid-range to high frequency. We are trying to figure out what area is important and where should we see the phase very critically. So I'm just going to go back to my the Excel sheet. Let me just quickly go back. So आप देख सकते हैं here out here, both A and B, the level is the same. दोनों का level जो है, it's pretty much the same. So let's see if you have a level difference of maybe 3 dB. Oh, sorry, it's going out of scale, so minus 3 dB. So आप देख सकते हैं if I'm introducing a level difference of of, let's say just 3 decibels from 2 signals like A and B, you're still getting a sound signal which is 4.6 dB, and दोनों का level दोनों same नहीं है, but we're still getting a good addition. And as we start increasing, let's say we go to 120 degrees, you're still getting some kind of addition out here, which is higher than one of the signals, but not as high as the second signal. Let's see what happens when you go to 180 degrees. So when you're going to 180 degrees, जो हमारा 180 degrees में, you were seeing that the level was previously 0, which was because both the signals, जो हमारे दोनों signals थे, they were exactly the same in magnitude. So we are getting the sum signal as 0. But now because there is a level difference of 3 dB, you're not getting the जो हमारा final result है, you're not getting it as 0. So maybe we could use this to our advantage. हम इसको हमारे advantage के लिए use कर सकते हैं. And how is that? Is because if we have complete phase reversal, अगर हमारे पास 180 degrees का phase reversal है, if we are seeing as there is a level difference, the sum signal which was completely going down to 0 is no longer 0. And let's just try and increase the level difference. Let's say you make it -6, and let's say you make it -8, and keep increasing, maybe -10. So अगर हमारे पास दोनों signal में 10 dB का फर्क है, if you're having a 10 decibel difference in the level, we're still seeing that the resultant जो हमारा addition, जो हमारा red wave है, is not completely 0, but you're at least getting 70% of your signal which was originally being used. जो हमारा original signal use कर रहे थे, you're still getting 70%, even though you have 180 degrees of complete phase reversal. And that's because we have a level difference of 10 dB. And probably we could use this to our advantage to understand where should we have phase being in, दोनों signals का phase should be together. We should try and understand whether phases of utmost value when we are crossing over between low to mid, mid to high. Is there any question until now, Nitesh or Rajesh? Any questions until now?
None, no questions as such.
Okay, so just going back to a presentation out here, we are seeing now that, I'm just going to quickly annotate this and make some box and make it red. So if I mark these areas, yeah.
Do you mind? I'll just like for this entire comb filtering, there's an entire video that I've done on YouTube. Okay. Also demonstrating the level differences and all. So whoever wants to see it, I'll just drop in a link in the Q&A section.
Sure.
So that they can watch it later also.
Yeah, sure.
Okay.
Hold on and undo. So you're seeing out here that जो हमारा crossover region है, wherever the level difference between the two signals, let's say we are going between the low and the mid, and let me use a different color. So let's say this is my low. Oops, it's on my mouse, and let me go back to draw. Okay. जो हमारा local level है and between the mid, if the level difference is 10 dB, even if we are starting to go in this area between the low and the mid, if the phase difference is going towards more than 120 degrees, we know that we have a reduction in the final resultant signal when the phase difference is between 120 to 240 degrees. So even if in this this blue area outside the level difference where it is almost more than 120 degrees, but the level difference is more than 10 dB, the maximum dip in the resultant, जो हमारा जो blue area मैंने mark किया है, दोनों के level के बीच में जो फर्क है 10 dB के अधिक है, if the phase difference between both of them is more than 120 degrees, we know that we don't need to be so bothered because maximum cancellation will be only 0.3 dB. We are still getting 0.7 dB of the higher value signal. Mid range का जो level है, उससे जो level drop होगा will maximum be 0.3 dB. That too if the phase difference is 180 degrees. If it is 120 degrees, it will be much lesser than that. So between 120 and 180 degrees, it will be much lesser than that. So I hope we've understood that where the phase difference needs to be as much as close together between two components, between the low and the mid, जो हमारे low और mid के बीच में phase difference है, should be as much close together as possible, is probably something that you can call the combing zone. And जहाँ हमारा दोनों के बीच में level difference is 10 dB or more, we can call it the isolation zone. So somewhere out here, हम लोग को इतना phase के बारे में सोचने की जरूरत नहीं है when we are adding two signals, because they are pretty much isolated. दोनों के बीच में जो level difference है 10 dB के ऊपर है. So and the same thing can be applied to the between the mid and high, जो हमारे line array हम लोग use करते हैं. Sorry, I'll just use a square. So many line arrays, they use a biamp system, जो HF के लिए हम अलग से amplifier use करते हैं, mid range के लिए अलग से amplifier use करते हैं. So many times we see that it's pretty much we are using a biamp signal, and we need to make sure the phase is in this red zone, which is actually of importance. And then the minute the level difference is going beyond, sorry, I'm on the mouse. And wherever the level difference is more than 10 decibels, we don't need to be bothered in the green zone so much about the phase between those two components. So is there any doubt that we have on so far? Because we're going to, be adding signals and all and on smart.
Yeah, there's one question. Well, if you can explain again, in what context are you saying this? And how much should it be ideally in terms of the crossover frequencies? And does it depend on the order of the crossover?
So number one, as we change the order, we are going to do हम crossover के order भी करने वाले हैं, and we are going to be seeing how different crossovers and different orders are introducing different phase shifts. So it is very critical that it's not only at the crossover frequency that they are in phase, but in a region where the levels are of significant value. So to the left and to the right, we are going to try and make sure that it's not only on the crossover frequency that they should be in phase. And we're going to demo this whole thing again to you guys, so you guys can understand that it's important that we add signals properly. And we're going to demo this whole thing actually. So don't worry about this. We're going to do an actual live example. Unfortunately, my office building is quarantined because the security is being tested positive. So I was hoping to do a lot of simulations actually with actual subwoofers, but I've just got a couple of speakers at home from my audio system. जो मेरे audio system से मैंने speaker निकाल के हम उस पे demo करेंगे. But I really wish to show you guys FiR and all those guys a lot of configurations. So of what importance it is, yes, it is important. Not only in the crossover frequency, but at the towards the left and towards the right, where they're still significant. मतलब हमने अगर एक crossover frequency डाल दिया, let's say the low pass filter on the subwoofer, let's say 100 hertz. अगर 100 hertz का हमने low pass filter डाल दिया, इसका ये मतलब नहीं है कि we don't have a signal coming in at 110 or 125 from the subwoofer. It's just rolling off, but the level keeps dropping. उसका level गिरते जाता है. And as it goes to the mid high, the both of them are adding and coming to your ears. तो दोनों जो low frequency और mid high के बीच में जो level है, जो level difference है वो बढ़ते जाता है क्योंकि ये low frequency का level कम होते जाता है. But we are going to be looking at a level of maybe where the level difference is within about 8 to 10 dB. So it still has a significant effect. And what crossover and slope we choose is going to determine how to. So any good system, जो हमारे actual systems है, जो बहुत ही अच्छे brands है, they do a lot of research on the type of. That's why they come with presets, right? That's why a company like Adamson or DNB or L-Acoustics, they have their default presets because they know the जो हमारे component का actual response है. And we're going to come into that next week again. We're going to do actual जो हमारे speakers components है, जो woofer, mid range और HF के है, उसके अलग-अलग phase response देखेंगे. So every woofer has its own roll off. Every woofer would have its own phase response. और जब भी हम उसको एक cabinet में mount करेंगे, the minute you mount in the cabinet, that would exhibit a different roll off. Like a sealed enclosure would probably have a much shallow or much less steep roll off than a ported an enclosure with a port. अगर हम एक इंक्लोजर में जो सील्ड है, जिसके पास कोई पोर्ट नहीं है, जैसे बहुत ही होम थिएटर सिस्टम्स है, उसका रोल ऑफ बहुत ही शैलो होगा. उसमें अगर हम पोर्ट इंक्लूड करेंगे थोड़ा गेन और जो स्पीकर के पीछे के साइड का रेडिएशन को इनहेंस करने के लिए, you get more gain, but you get a much faster, steeper roll off. So that's why we need measurement to try and understand what is the kind of response we're getting from your loudspeaker system and what kind of crossover we choose between both of them to make sure in the summation zone they are pretty much in phase. Does that answer that question?
Yes, I guess.
And we'll do it now again. We'll just, add some signals and just out of the blue, we can choose different crossover slopes and different frequencies and see what the resultant is. So
just one other question is, why have you taken a figure of 10 dB like, and not less? Is anything specific about 10 dB?
No, you could probably, just to give you an idea, you could, keep it 12 dB, but in a real world situation, that you will see that, that phase changes because हमारे जो low pass filter का phase characteristic of the subwoofer and the high pass filter का characteristic on the mid high is not the same. You would get them to be as close as each are, at the crossover point to be in phase. And as you keep moving away, you'll see that both the phase, the idea is to be as if you can keep them in phase for a much wider range, then yeah, that's great. I mean, you've achieved something amazing, but it requires a lot of critical components which are with a very good response. That's why it's not you can't just go and pick up any. It's like saying using a DSP and take up any Chinese driver, take up some speaker from China and then just put a DSP to it and then say okay fine, let's just make it look flat, but at the end of it inherently जो हमारे एक solution बहुत लोग बोलते हैं कि एक चाइना से कोई भी एक सस्ता स्पीकर उठाओ, उस पर DSP लगाओ और उसको बहुत ही अच्छा क्रॉसओवर लगाओ और उसका फेज मैग्नीट्यूड फ्लैट रखो, but they all have their own separate phase responses and if you are able to get, अगर आप बहुत ही अच्छा phase response deliver कर सकते हो over a wider range, then it's great. That's why a lot of people use different techniques. It's and we'll get to that sometimes just matching the phase at the crossover region is not the only solution. Sometimes you'll see that before and above the crossover region, they start splitting drastically, and then probably you need phase inversion and different kind of thing, or maybe change the crossover slope to make that phase in that region a lot better. But I wouldn't be too critical to say if the level difference is maybe 15 dB या अगर हमारा level difference 15 dB या 20 dB है, I wouldn't waste my time too much because the influence of that would be very minimal. So it's not something fixed that you need to keep 10 dB as a level isolation. It could be 8 dB. It's not something that you'll always get. Sometimes beyond 8 dB you'll get a lot of big phase difference between the two signals. So if you're having left and right 8 dB, I think it will be pretty good, and you see the overall response and the overall phase response of the signal. And again, you can correct a lot of it with FiR filters, which is why FiR filters is important. जो आप देखेंगे कभी-कभी आपको बहुत maybe 5 dB के level isolation या 6 dB 8 dB के level isolation के ऊपर आपको phase difference बहुत ही ज़्यादा मिलते जाएगा. So it's not necessary that you're going to be stuck to a 10 dB window. You got to kind of take a real world decision. आपको एक दुनिया में actual decision. Not everything is a perfect world. हमारी दुनिया perfect नहीं है. 2.5 महीना पहले हम बहुत ही अच्छा काम कर रहे थे, and since 2.5 months we are at home, so it's not a perfect world. You got to take the best decision that it's working that scenario for you. Is that okay?
Well, do you mind just adding something to that?
Yeah.
So 10 dB, are we talking about the 10 dB difference in between two drivers during the crossover thing?
When you're adding two signals, just you're making sure that you're trying to keep maximum phase coherence, or keeping the two signals in phase where the level difference is at least within a 8 to 10 dB window. If it is greatly separated in levels and if the phase is going separating quite a bit, we're not so concerned, because even if it is 180 degrees out of phase, the maximum dip you would expect one component to influence on the other would be, 0.3 dB or something like that, not more than that.
Yes. So basically, like, मतलब Karan भी क्या बोलना चाह रहा है और मुझे भी क्या बोलना है. There are frequency like SPL ranges. Like if the difference is between 0 to 4 dB, आपको जो summation और cancellation मिलता है वो बहुत ज़्यादा होता है. और around 4 to 10 dB it is something that is acceptable. लेकिन 10 dB के ऊपर जो एक दूसरे का सिग्नल का इन्फ्लुएंस है एक दूसरे पे, it doesn't matter at all. So it does not like जो ripple आ रहा है, the 0.3 dB, 0.1 dB is something जो हमें सुनाई नहीं देता है, तो it doesn't make a difference. So 10 dB के ऊपर you can actually neglect it if that is the difference.
And again, जो जैसे कि हमने देखा, like we just saw that you're having an actual reduction in level when the phase difference is going above 120 degrees, between 120 and 240. So you'll be at, even if you're between 0 and maybe 30 degrees, between when the level difference is from 0 to 10 dB, and after 10 dB is going more than 30, from 30 to 30 to 120, you're still having some amount of addition. You're not having cancellation, and phase difference actually goes beyond 120 degrees. So I would try and keep a 10 dB window to again we'll measure that stuff on smart, and just generate two signals and see what it looks like.
Okay.
And so yeah, that's
and just taking care of one more question right there. So there's someone who has asked that, so basically what you are saying is 8 to 10 dB of difference in amplitude gives you the phase to be around 0 degree to 120 degrees.
Yeah, you can say that. 0 to I would keep it around 0 to 90 is what I would do. But again, it's again a real world scenario where you have to see a good manufacturer, एक अच्छा manufacturer would always have a preset, and their slopes and high pass filter and low pass filter chosen correctly, so that setting the right amount of time delay between both of them and aligning both of them would give a pretty good phase coherence over that crossover region. So a good manufacturer would always choose their crossovers pretty well. And a lot of you guys have your own system. बहुत से लोग we sell a lot of components. So the reason हम इतने components बेचते हैं because आप सब अपने अपने खुद के cabinet के design में add करते होंगे. And again, measure your cabinet, spend some time with it, and make a good preset for it. And once you've chosen your low pass filter, high pass filter for it, and seeing after this session, I hope you guys can use your DSP a lot more wisely in choosing a filter. ये session के बाद मैं चाहूँगा कि आप अपना DSP बहुत ही wisely choose करें, बहुत ही wisely use करें, और अपना low pass filter, high pass filter सही तरीके से use करें, और अलग अलग slope है इसके. That's the reason we have so many options. It's not that I have speaker A and I'm using a Linkwitz Riley 24 dB an octave low pass filter, and then I tell my customer who's using speaker B, जो मैं एक तरह का speaker use कर रहा हूँ, और उसमें बोलूँ कि मेरे पास जो Linkwitz Riley 24 dB an octave का जो low pass filter है, और कोई दूसरा use कर रहा है maybe RCF का speaker और या कुछ अलग W bin में, और वो बोलूँ कि नहीं आप यही low pass filter use करो. It's not necessary, because दोनों के कैबिनेट अलग है, दोनों के स्पीकर अलग है, दोनों का फेज रिस्पांस अलग है, दोनों का मैग्नीट्यूड रिस्पांस अलग होगा. So the crossover is more dependent on your system that you're choosing and what you're using along with it regularly. That's why you see most manufacturers, they have a couple of subwoofers with a couple of their mid highs. अगर हम Adamson की बात करेंगे, they use a E series subwoofer with the E15, E12 liner. If you talk about D1B, they use a SL sub with the GSL or the KSL. So they have a family where they've said this subwoofer is for this mid-high, and it's not that you can't use something else, but they've pretty much spent time in seeing what is fitting with each other, and that's the reason they have a uniform sounding system. आप कोई भी venue पे जाएंगे, they have a pretty much uniform sounding system, and user के लिए कुछ ज़्यादा कुछ ये नहीं है. अगर L-Acoustic is using K1, K2, they have the KS28, or they have the subwoofers pretty much the presets done for whatever reason they have. Can we move on? Otherwise, it's just I'm just worried that we.
Yeah.
Okay, so just quickly moving on to some important formulas. We're a little gone. We are behind time. Hum time ke piche. So I'm just going to quickly go through. We've gone through this before. It's about calculating the limiter and compressor. And Again, Ohm's law is very important. A voltage is equal to current into resistance. Current is voltage into resistance. I'm just going to go quickly because we've gone through this previously. Resistance is voltage upon current. Power is voltage into current, but we don't always use it. हम हमेशा ये power is equal to voltage into current use नहीं करते हैं, क्योंकि voltage और current दोनों vector quantity है. दोनों के बीच का phase angle would or not necessarily, they may not always be in phase, so it's only applicable when they are in phase. Otherwise you got to include the phase angle between them. So we replace current is equal to voltage upon resistance, and then हम हमारे power amplifier का अगर output power सही में देखना चाहेंगे तो हम बहुत बड़ा resistor use करेंगे, उसके across voltage check करेंगे, input signal में 1 kilohertz का sine wave देंगे. We'll give a 1 kilohertz sine wave to match up, and I'll cover this again next week when you're going to amplifier and speaker and horn configuration and specifications. So don't worry too much. इसके बारे में ज़्यादा घबराई मत. मैं अगले हफ्ते इसको ज़्यादा विस्तार में करूँगा. And again, we saw as frequency goes up, time goes down. And the reason I keep using this again and again because we will be using it at some point or the other. ये इसके बारे में हम बार-बार करते जाते हैं क्योंकि हम इसको कहीं ना कहीं ज़रूर use करेंगे, और ये बहुत ही simple formula है. The more you get used to it, the better it is. Amplifier का voltage gain देखने के लिए, behind the amplifier you always see a voltage gain, which is always mentioned. A good amplifier would mention. Right now we're using an amplifier which has 32 dB of voltage gain. If you don't, बहुत से, like for example we sell a lot of amplifier, जो हम amplifier बेचते हैं उसके पीछे एक input sensitivity का switch दिया जाता है, जिसमें कभी-कभी दिया जाता है कि 0.775 volt, 1 volt, 1.4 volt. So what is the meaning of this 0.775 volt, 1 volt, or 1.4 volt? It means when your input signal is 0.775 volt, is going to give you your maximum voltage output. When your signal is going to give you, when a signal is going to be 1 volt, is going to give you maximum output. अगर आपका amplifier 2000 watt है at let's say 4 ohms, अगर आपका input signal 0.775 volt है, your output is going to be delivering that output voltage, and if your load is 4 ohm, it's going to give 2000 volt. If your input sensitivity is 1 volt, you will get, and if your input signal is 1 volt, अगर आपका input signal 1 volt है, तो आपका output voltage फिर भी 2000 watt होगा अगर आपका speaker 4 ohm का है. अगर आपका sensitivity 1 volt है और आपके signal पे 0.775 volt है, तो आपको ये situation में 2000 watt नहीं मिलेगा, because the voltage gain or the input sensitivity is not full. I mean, it is a lot lower. So you're not getting the full power, and then only if you increase the level from 0.775 volt to 1 volt, or just to make it simple, अगर हमारा input sensitivity 1 volt है या 1.4 volt है, और हमारा input voltage जो है 1 volt है, half volt है, 0.5 volt for example, हमें पूरा power नहीं मिलेगा. And that is important because when you're doing gain structure, आपका अलग-अलग mixer, I know that the output of a Yamaha mixer is not the same as a Soundcraft mixer, and then you got to adjust the input sensitivities. So it's important to select the correct gain structure or the input sensitivity. By default, हमारे जो internationally most amplifiers work on a 32 dB voltage gain. जब यहाँ हमारे इंडिया में चाइना से amplifier का बहुत बड़ा you know, I would say it exploded. Like when this would be something around 10 years back, when, you know, in Palm Show and all, I saw a lot of dealers getting, we ourselves got amplifiers about 8 or 9 years ago. And then there were many old players like, you know, our colleagues like Narayan and all who got amplifiers from Phonic and all, and they started having a sensitivity of 0.775 volts. The 0.775 volts is not a very good sensitivity because it just gives you the idea. अगर we are keeping the sensitivity in 0.775 volt and giving an input, the speaker is sounding a lot louder, but all it's doing is just giving a small signal a very large voltage gain, and it's not ideal because you would not be using your mixer to give a good signal to noise ratio. Your noise floor would be your signal would be pretty low compared to your noise floor. So it's not something that would be recommended, but it's something that was just, it came out in terms of people perceiving it as, you know, connecting two amplifiers. Log do amplifier use karne lage, and that time there was some good amplifiers by Crest Audio and all. And I know that people used to just start comparing, and I know that the input sensitivity of all these amplifiers, I'm myself to blame again, but the idea out here is to, to clarify all concepts so you know what's happening. So if your sensitivity is 0.775 volt and you actually give a 1 volt signal, which is the output of, which is the full capacity of your Yamaha mixer, or I think Yamaha is 1.4 and Soundcraft is 1 volt. I can't remember exactly, but you can measure it. And if you actually give the actual output of your Yamaha mixer or your actual Soundcraft, you're actually using the full the gain structure in your mixer to give a good, nice signal to noise ratio. Your signal is up there and noise is low, way below. And if the output is 1 volt, it's going to be clipping. Agar aapka input sensitivity is 0.775 volt, it's going to be clipping. So it's not something that you should be using a lot, but I see people always using a lot because they feel that the attack is by just आपके mixer के DJ के mixer से थोड़ा सा gain आप बढ़ाते हो and you get great gain and you feel, oh wow, this amplifier is so powerful, which is not the case. But that's why they have a switch behind, which is where you can change it, so you can adapt to different mixers or different outputs of different mixers. So I hope this is clear, and we'll just see what happens if the amplifier you're using today is 32 dB, but if you're using something that is a much higher input voltage sensitivity, this is what exactly happens. So we know that last time we did, हमने last time किया कि voltage gain is 20 log of maximum output by the input signal, and the maximum output जो है, जो हमारा 8 ohm का rated power है, is into the resistance, which is, again, if you go back, you can use the power formula, which is power is equal to voltage into voltage divided by resistance. So you put resistance on the other side, you get voltage square is equal to power into resistance, and voltage is equal to square root of power into resistance. So you're seeing the rated power at 8 ohm into the 8, which is the resistance. Why we use 8 ohms is because आप कोई भी amplifier का specification sheet देखेंगे, अगर आप देखेंगे कि amplifier का output power is, let's say, 1000 watts at 8 ohms, if you make the load impedance, let's say the loudspeaker is 4 ohms, you should ideally expect double of it. अगर आप उसको आधा करेंगे, you would expect the power to kind of double. From 1000 it should go up to maybe 2000, but it's always lesser than double. It's maybe 1800 or something by measurement. Then that's because there are thermal limitations. There are आपके amplifier के अंदर एक thermal limitation होगा, transformer का current carrying capacity का एक limitation होगा, which won't always go, or your transistors won't always deliver exactly double, because there's always a lot of heat. Amplifier आप देख सकते हैं बहुत ही गर्म होता है. A lot of energy gets converted into heat. As you get more and more current into it, you get more and more heat. So this is why it's never always double. So we try and go with the highest power rating, which is in terms of you could do 4 ohm, the rated power, and multiply by 4. But out here you get the maximum output as we all agree that it would be at the 8 ohm into 8. So let's say आपका amplifier का output है 1000 watt at 8 ohm, and you get square root of 8000 watts, which is 89.44 volts RMS. And if your input is, let's say, 0.775 volt, you know that this is going to be the maximum output when your input is 0.775 volt. So if you are at 0.775 volt and this is your output power, I know that a lot of I'm admitting to you all as well, जो आपका amplifier का output power है, there are a lot of ways to play around with it. The ideal way is to measure it at 1% harmonic distortion, and we'll get into that next week. Don't worry about it. But you'll see a lot of manufacturers, and we've taken advantage of it, that you can bump the harmonic distortion and measure it at a much higher harmonic distortion, and say that my power is not 1000, it's maybe 1300 or 1400. But then it comes in with the cost of a lot of harmonic distortion. जो आप Ahuja के you'll see just a great company like Ahuja, like you can go online and see this thing, and they'll say power at 1% THD, total harmonic distortion, is, let's say, 500 watts, and then power at 10% total harmonic distortion is 650 watts. Now you could write 650 watts, but if you actually add 10% total harmonic distortion in your sound signal, you're not going to be able to hear anything. I mean, it's just going to be extremely horrible for you to kind of, even you're going to be saying it sounds horrible, ye bahut hi ganda baj raha hai. But then just to make it look great, we all do it. I mean, we all are part of it. It's all a marketing stunt. It's all there from the big manufacturers all the way down. I mean, a lot of the big manufacturers I've seen loudspeakers is saying that my subwoofer can generate 150, 150 dB max SPL, and then that's nothing but just a formula saying that my 1 watt at 1 meter SPL is 94. My power capacity is 2000 watts, so I'm going to use a formula and see what my max SPL is, and we'll calculate all that next week and see what is actually. But in the real world scenario, it doesn't deliver 150 dB max SPL. I mean, it's just something that's theoretical, and then people start comparing. हाँ जी, ये speaker का max SPL इतना है, ये speaker का max SPL 147 है, तो इसका जो 150 dB SPL है, ये बहुत ही ज़्यादा अच्छा speaker होगा क्योंकि इसका max SPL ज़्यादा है. And it's not entirely true, because it just could be a formula, and then there are a lot of things that happen. I mean, your voice coil becomes hot, आपका voice coil गर्म होते जाता है, your resistance increases, there's thermal power compression. A lot of factors happen in something that you can't, and that's the way. Always use your ears. इसके लिए मैं हमेशा बोलता हूँ, our ears are very sophisticated, complicated, products that we've been given. Use your ears to determine what sounds better, and it's one of the reasons why बहुत से लोग मेरे को आके पूछते हैं that why does Adamson sound the way it sounds at those high SPL levels, because it's using Kevlar, and then compared to paper, it's a lot more stiff, it's a lot lighter, and it kind of retains its shape, and it's something that people use. But then हमारे common system is, you can't use Kevlar because the cost of the cone paper is probably 6 times of normal paper. So it's a lot of these things. So anyways, I'm just diverting and just wasting time, and I just get carried away. Sorry. हम आगे देखेंगे कि इसका वोल्टेज गेन जो हम इसका एक्चुअल कैलकुलेट पे अब अगर आप कैलकुलेट करेंगे, ये लगभग 40 dB होगा. तो आपका वो इनपुट सेंसिटिविटी is going up, and you feel it's great, but it's not giving you, आपको एक्स्ट्रा पावर नहीं मिल रहा है, खाली इसको आपके छोटे से इनपुट सिग्नल को और मैग्नीफाई कर रहा है. So is there any questions on this formula or anything until now, or we can move on? Hello, Nitesh, Rajesh, anyone here?
Yeah. There are a few questions, but I think you will be covering them in the, there's one question which is asking, what is the gain level that should be set on the amplifier?
32 dB is, I think, pretty standard, but that's a safe level, and it kind of gives you pretty much all manufacturers set their voltage gain at 32 dB, and almost all manufacturers set their presets at 32 dB. So I know that at least I know that Adamson does. So that's the reason that it's just the voltage gain that the voltage gain that matters in terms of setting your compressor or limiter. So there was this question asked even by Nitesh and myself when Adamson was doing the webinar, where they said that we're using the S10 and you have a preset on the PLM 12K44 and you have a preset on the PLM 20K44. Does the threshold or anything change? But it doesn't, because both the amplifiers have a 32 dB voltage gain. So internationally, I've seen Camco, I've seen a lot of the good manufacturers keeping the voltage sensitivity at 32 dB, but they always have, like for example, lab grouping. अगर आप lab grouping के पीछे देखेंगे, आप input sensitivity, voltage sensitivity कम करने का dip switch है, where you can make it as low as 18 dB. So if you have a very powerful signal coming out of a mixer or something, I don't know, I don't know what applications, but usually I know that आपके mixer से, I think Soundcraft gives 1.4 volts. You have to see the specification sheet. आप अपने mixer के specification sheet देख सकते हैं, and you can see it on your levels on your input level, right? If you're getting able to use a good gain structure on your mixer without clipping your amplifier, without clipping the input, or without clipping the input levels of your mixer, you're using a good gain structure, and that's why those LED indicators are there, because to आपको indicate करने के लिए कि it should not be that you're just थोड़ा सा आप mixer से थोड़ा सा green LED आ रहा है और you're clipping your amplifier immediately. That means you're giving a very high sensitivity to your amplifier, and then you would probably want to reduce the input sensitivity, and try and use as much gain from your mixer to ensure a good signal to noise ratio. And that's something that would be you'll be experiencing in practice. And so yeah, most amplifiers come with 32 dB. बहुत से amplifier में जिसमें ऑप्शन नहीं रहता है चेंज करने के लिए. आई नो मोस्ट ऑफ देम आर 32 dB, but that's pretty much an international standard I've seen. But like our amplifiers give you the option of 40, 32 and 26. So if you have a mixer with a higher output voltage, you can reduce it. You can, you know, to make it sound great, just by little small mixers that come from China that don't have much of an output, they just go up to maybe 0.5 volts. You can use the 0.775 volt or 40 dB voltage gain. So it depends on the specification, but 32 dB is pretty much standard, and most good companies come with the option of changing your input voltage. Would that be it? And can we move on, or anything?
Just one thing, someone was asking in this formula for the Vmax, what is the figure? What is 8 stand for? Rated 8 ohm power into 8.
8 is impedance. So let me just quickly
Just
go
power
back.
into impedance. Okay. Sorry, yeah.
So power is voltage into current, which is जो है voltage into voltage upon resistance. So you put resistance on the other side, which is your load, जो भी speaker है आपका, and power voltage is let's say your rated power is to 1000 watts at 8 ohm. So your power is 1000, your resistance is 8. 8 is going on the other side, so it's 1000 into 8, and then there's the square root of that. So any question? I mean, we did that calculation last time, and you guys can now calculate your voltage gain of amplifier. And we're going to come again to what we're actually doing out here. So any questions so far? Anything else?
There are a bunch of questions, but I think we'll come to them a little later. Let's move on and then.
Okay, cool. So I'm trying to be as Hindi and English as possible. If you guys feel, अगर आपको लगता है कि कोई हिंदी में ज़्यादा बात करना चाहिए या इंग्लिश में ज़्यादा बात करना चाहिए, please feel free to barge in and just tell me whenever. Okay. So again, we said this is a speaker, any speaker that you want. आपका subwoofer है, आपका mid high है, आपका line array है, कोई भी component. Power is voltage into voltage divided by resistance. Voltage is, so you're getting what is the maximum voltage that should come from your amplifier to your speaker. This is what you're calculating. Now, if you're using a peak limiter, you would ideally, if your RMS power is, let's say 300 watts, you would probably double it and say, okay, 600 watts is my peak power that I would be using, and calculate the voltage accordingly. If you're using a peak limiter, if it's an RMS limiter, many use, I know PowerSoft provides an RMS limiter as well in a Harmonia platform. So you can use a RMS limiter as well. PowerSoft जैसी company में RMS limiter भी है. Most provide a peak limiter because the damages, or they actually suspect it. I mean, you would expect a higher failure rate out of the peaks that are coming in a signal rather than the RMS. If you're taking care of peaks, your RMS is pretty much taken care of, because your average, with considering a crest factor of 12 dB or anyways, would be pretty much lower than that. So I know only very few manufacturers that provide RMS limiters, but they mostly provide RMS compressors. जैसे कि Marani provides an RMS compressor. So there's no loss in, you try and retain some dynamics by just compressing rather than actually just limiting. And we'll again get into that next week, but just calculating compressor and limiter. So power is again, आपका जो speaker का power है, let's say आपका subwoofer है double 18 का subwoofer जिसका power है 2000 watt, उसका resistance है 4 ohm, and you can calculate the maximum power. Let's say it's 2000 watt RMS, you could make it 4000 watt peak and calculate the maximum peak voltage that should be coming out of amplifier. आपके amplifier से maximum peak voltage जो आ रहा है should be coming on that way. We then know our voltage gain from the previous calculation, let's say 32 dB or anything that we use, check the input sensitivity, and you can use anti-log in your calculator. I mean, there is a log function and there's a 10 raised to x function, which is the anti-log version. So you know the maximum, so let's say maximum voltage is, let's say 60 volts or 70 volts. You know the voltage gain, which is 32 dB. You know the maximum voltage, which is V1, let's say whatever you get out of the calculation. And then you get to know what is the maximum input voltage, which is V0 that should be applied to your amplifier. So आपके amplifier के input में maximum input voltage क्या होना चाहिए? जो आपके amplifier का voltage gain है उसके ऊपर dependent होता है. जो आपके speaker का maximum power rating है उसके ऊपर डिपेंड होता है, and that you can calculate V0. So once you calculate V0, we've also done it last time that dBu, जो हमारा dBu का unit है, उसका calculation है with a reference of 0.775 volts, which is also the voltage across a 600 ohm resistance. You know, when considering the standard 1 milliwatt power being dissipated across microphones, and you know, a lot of previous dBm was a common factor for input measurements, but with time हमको realize हुआ कि हमारा input impedance 600 ohm पे standard नहीं है, बहुत से जगह पे 250 ohms है या अलग-अलग input impedance है, so we just stuck to voltage because that would change with time. So 0.775 volt is a when you're saying dBu, हमारा जो reference है is with respect to 0.775 volts, and you would get your threshold level. So and then again, like I said last time, it's the same slide as last time. It's something that I can share a white paper on, why the HF time has a much faster attack time and low frequencies have a much lower attack time. And we keep release time basically anything between 8 to 10. That's what we do. And that's what I know a couple of guys who do it, like Nova Audio, and a couple of guys who use their limiter calculations and they do it this way. They keep the release time. What the attack time is doing is basically, जैसे ही हमारा ये जो थ्रेशोल्ड है, अगर ये अटैक टाइम अगर अगर हमने 2 मिलीसेकंड रखा है, फिर इज 2 मिलीसेकंड के ऊपर ये थ्रेशोल्ड हमारा इनपुट लेवल ये थ्रेशोल्ड के ऊपर है, 2 मिलीसेकंड्स के अंदर ये लिमिटर एक्टिव हो जाता है, और रिलीज टाइम है अगर वो थ्रेशोल्ड के नीचे, सपोज हमने 2 मिलीसेकंड का अटैक टाइम सेट किया और उसका रिलीज टाइम 16 मिलीसेकंड या 20 मिलीसेकंड सेट किया है, अगर 20 मिलीसेकंड के ऊपर अगर वो लेवल जो हमारा थ्रेशोल्ड जो सिग्नल लेवल है थ्रेशोल्ड के नीचे है, if the signal level is below the threshold for more than maybe 20 milliseconds, the limiter is going to be going off. So that's what the attack and release times do. And before we move on to compressors, is there any question on limiters?
Not specifically on limiters.
Okay,
so
cool.
We'll address these questions a little bit.
Cool. We will get into that soon. So just moving to compressors. Now, limiter jo hai, limiter is not letting you go above the limiter is not letting the signal go above that threshold level. Now, we also have compressors, and then I know Marani has an RMS compressor. So we're going to quickly go into RMS compressor. So जो आपका signal का actual RMS value है, like last time you're seeing the peak value, let's say it's 600 watts, let's say आपका 2000 watt का dual 18 का subwoofer है जिसका 4000 watt peak है. Let's say the RMS is actually 2000. So you want to make sure that above 2000, you're getting some peaks that are in, and you're keeping some compression for the RMS value. So let's say you set the threshold level. Again, this is again you're setting the threshold level based on the previous calculation. Nothing different, nothing. But this is, let's say, let me just kind of annotate this and make it maybe a red line. So let's say around 6 dB. So I'm drawing a red line around 6 dB. Or let me just make it a nice square so it's a little visible. So is my red line clearly visible? Nitesh, is a line visible? Everything's okay?
Yes.
Okay, so let's say we have a signal that is going from, let's say this is a signal. This is the sine wave that we're getting. Now, let's say that in compressor, it's basically compressing. You're just how you kind of compress a hydraulic pump or something. That's probably this. Let's just say this is your signal. You set a 6 dB threshold, and always a compressor will come up with something known as a compression ratio. So if I quickly, let's say 4:1 is your compression, or 2:1. Let's have a 2:1. Okay. So 2:1 is a compression ratio. That means whatever is above your threshold, जो हमारे threshold के ऊपर है, let's say it's 6 to 14. 14 minus 6 is 8. 8 dBu is going to be compressed to half. So हमारा जो अगर 8 dB is the input signal is going to be then get compressed to by 4 dB. So this compression signal at this thing is going to be 6 to 10. So this is what the signal is going to be. If you want a higher compression ratio, let's say it's 4:1, and in that case, it's 8 dB above threshold, and it's going to be just probably 2 dB above threshold. And then if you have higher compression, let's say 8:1, and then you would probably get maybe only 1 dB above threshold. So is this clear what we are doing with compression ratio? It's pretty simple. It's not limiting. अगर आप limiter होगा, your signal is going to be restricted to this level out here. And it's not always desirable. Imagine someone playing a nice drum or kick drum or something, and it's just kind of losing its attack. And it's not, if you set a limiter, it's just going to kind of limit the signal out there. And yeah, but a lot of you guys, Rajesh and Nitesh, you guys use compressors in your mixes, and you guys can stretch on. You guys want to add something on compressors or anything?
Not really.
I think you have explained it pretty well, I would say.
Okay, cool. So again, attack release time, is something that you can set. Something that compressors that all come with is something called as makeup gain, which is you guys, Rajesh and Nitesh, you want to add something on makeup gain?
Well, it's not really relevant on the output part of the compressor.
We use it sometimes. It's sometimes signal routing is something that we use. Basically, जो हमारा dynamic range है, इसको compress करने के बाद signal का level काफी कम हो जाता है. इसके लिए बहुत बार compressor के बाद आप देखेंगे कि एक makeup gain है, जो कि उसका gain, signal का gain है after compression. Some of the mix engineers can explain to you guys the utility of it better. They use it a lot on the mixes. Do you all use it on the mixes? I'm not sure.
Yeah. What I meant was that you definitely use it on the microphone side, but how do you really use it on if you're putting a compressor on your output? Because won't it give a more compressed signal, which will be moving?
It will. It would again increase the level, but I think it has something to do with also enhancing the signal to noise ratio, but I'm not too sure on this thing. But basically, I know it adds gain after the compressor. But anyways, this is something we don't get too much makeup this thing. And then we also have something known as hard knee and soft knee. जो हमारा knee है, बहुत बार आप compressor के बाद एक hard knee देखेंगे और soft knee देखेंगे. Which is जो आप hard knee देखेंगे, आप इसका left में देखेंगे hard knee का position कैसा है, और soft knee का आप देखेंगे इसका position कैसा है. Just to give you a brief idea, so let's say in soft knee, the compression would start a little below the threshold, but at a much lesser. Let's say you said 8:1 का threshold, and let's say a signal is not going way above here, but let's say somewhere here, but it will start compressing somewhere a lot before, whereas a hard knee would compress only when the signal is straight away above the threshold. Is this clear? I mean, I don't know how better to explain it, but
yeah, this is quite, it's exactly what it is.
Okay, so any questions until now that I need to address, because we'll be moving on to the next topic?
Can you give an example of the knee? That's more, I mean, at least for me as a mix engineer, it would be more used when you're using it, when you're compressing like any kick or something like that, or any percussive instrument. I really don't think you would change
So
the
we use
knees.
it. We also use it a lot to हमारे loudspeaker में the most. What is the thing that blows out the most? Is the HF, right? So something on the HF, I use a much softer knee, whereas on the, so that I at least start compressing it at some point below the actual threshold, so it's not heating up the voice coil directly. So it's got this smooth transition, and it's also more easy to hear. Something that's getting compressed on the mid high. Our ears are very sensitive. 1K, 2K is very sensitive. So I start, instead of giving a direct compression directly at threshold, where it's going above and below, I just kind of start using a softer knee on higher frequencies rather than lower frequencies.
Okay, sorry, there are 2-3 people who asked that, can you just quickly go through the compressor ratio, attack and release in Hindi?
Okay. Okay, so let me just clear this. जो हमारा compression ratio हमने देखा है, अगर हम RMS compressor को देखेंगे, so let me just quickly exit and let me see if I can bring up Marani's hold on out here. And is Windows visible, Nitesh?
Yeah.
Okay, cool. So is my processor on? Yes, it is. So
also,
for those,
I would like to add one thing here, Karan.
Yeah.
Like, this hard knee and actually how the ratio and attack is working. I think, the best way to understand them is to actually overdo it and try to listen to it.
Yeah, correct.
For everyone, like that is the best. No matter how much we try to make you understand, ये ऐसे सुनाई देता है, वैसे सुनाई देता है. The best is to just dial in and hear it.
Honestly, मैं चाहता था, I would wish that, I mean, I miss the Palm show. I miss meeting you all. हर साल we get, such a great turnout at Palm, and अगर हम Palm की बात करेंगे, next week would be, by Monday would be setting up a stall and everything at Palm, and I was hoping that, we could get into a lot of details, interact a lot more, but unfortunately we are doing what we are doing. That's the best we can do. So just let me just quickly just show you on a processor that how outputs have a compressor limiter. Just give me a minute. And okay. So हमारा जो output है, you can see that this RMS compressor है जो bypass किया गया है. इसमें हम threshold जैसे कि DBU सेट किया है. रेशियो यहाँ हमें देना पड़ता है जो can I zoom in? You want me to zoom in? Okay, I'll just try and zoom in this one. New share, advanced portion of the screen, and oh, I think it's the wrong screen. Sorry.
Yeah, it's correct.
It's correct. Okay.
Yeah.
Just switched. So आप देख सकते हैं कि ये RMS compressor और peak limiter है. Peak limiter had ये threshold और release और attack time है. Nitesh, do you want me to cover the limiter, or it's only the compressor, right?
Yeah, I mean
Okay.
You can touch on both.
Okay, so ये हमारा RMS compressor है जहाँ हम threshold set करते हैं. ये level के ऊपर ये compress करना चालू करता है. जो compression ratio है क्या सेट करना है मैं आपको दिखाऊंगा. आप कुछ भी सेट कर सकते हो, 2:1, जो भी सिग्नल लेवल है. नी का परसेंटेज आप यहाँ आप देख सकते हो कि अगर नी हम अलग अलग लेवल सेट कर सकते हैं, सॉफ्ट नी या हार्ड नी. 0% में हार्ड नी है, और जैसे ही नी बढ़ाते, सॉरी 100% में हार्ड नी है, जैसे ही हम बढ़ाते जाते हैं नी बढ़ते जाता है. So if I just kind of see, I can just set any threshold, any knee, and you can set the release, attack, and the makeup gain that we all spoke about. So I'm just going to quickly show that this on the PPT as well. So let me just stop share and go back to my desktop, which is here. Okay. So like I said, let's just set, this is a level different settings of your compression ratio, compressor threshold, and I'm going to set maybe a threshold. Let's say हमारा signal जो है 6 dB. Okay, ये जो हमारे आप white line देख रहे हैं ये 6 dB है, and इसका अगर हम कोई भी सिग्नल देंगे, लेट्स से ये थ्रेशोल्ड के ऊपर है, लेट्स से 14 dB से है, 14 dB के बाद हमने उसको अगर 2:1 थ्रेशोल्ड सेट कंप्रेशन रेशियो सेट किया, मतलब ये जो थ्रेशोल्ड के लेवल के ऊपर जो लेवल है जो कि 14 - 6 वो है 8 dB। 8 dB का जो थ्रेशोल्ड हमने जो अगर कंप्रेशन रेशियो सेट किया 2:1, तो 8 dB को वो आउटपुट में 4 dB देगा। तो ये आउटपुट, ये हमारा इनपुट है, या आउटपुट में आउटपुट की तरफ दूंगा, ये 4 dB, तो ये 10 dB तक जाएगा। और जैसे ही हमने उसको, अगर उसका कंप्रेशन रेशियो बढ़ा है, सपोज 4:1 किया, तो 4:1 में उसका जो 8 dB है वो 2 dB बढ़ेगा, तो वो 6 + 2 वो 8 dB पे आएगा। और अगर हमने उसको कंप्रेशन रेशियो और बढ़ाया, उसको 8:1 किया, तो जो 8 dB इनपुट में बढ़ रहा है, आउटपुट में 1 dB से बढ़ रहा है। Is the compression ratio clear? You want me to write it? Let me just write it here. 2:1, 4:1, and 8:1. So is the compression ratio okay?
Yeah, I think compression ratio is fine.
And then again, your attack and release time, like I said, you get to know about reading. There's no formula for it.
Hindi.
ये अटैक और रिलीज टाइम के लिए कोई फॉर्मूला नहीं है। ये इसके बाद मैं आपको एक पेपर दे सकता हूँ, AES का पेपर, जिसमें हाउ टू सेट अटैक और रिलीज टाइम, कैसे अटैक रिलीज टाइम का क्या वैल्यू होना चाहिए, उसका ये वैल्यू क्यों है, ये है। बट तो यहाँ आप देख सकते हैं कि हमारा जो अटैक और HF के लिए, अगर सिर्फ हमारा HF का ड्राइवर है, तो उसके लिए 1 से 2 मिलीसेकंड हम सेट करते हैं उसको, काफी जल्दी प्रोटेक्ट करने के लिए। मिड फ्रीक्वेंसी या मिड हाई के बॉक्स के लिए हम उसको 5 से 10 मिलीसेकंड, अगर 2A अगर पैसिव क्रॉसओवर बॉक्स बिल्ट इन है, तो यू आर प्रॉब्ली यूजिंग 5 to 10 मिलीसेकंड्स। और LF और सबवूफर के लिए, जो कि इट कैन विथस्टैंड अ लॉट ऑफ पावर, यू यूजिंग अ लॉट ऑफ, उसका अटैक रिलीज टाइम काफी बड़ा है, 40 से 50 मिलीसेकंड। और जो भी आपका रिलीज टाइम है उसके अटैक टाइम का 10 गुना, रफली अराउंड 8 से 10 गुना है। तो इसका छोटे समझाने के लिए, अटैक टाइम क्या है कि जब आपका लेवल थ्रेशोल्ड के ऊपर जाएगा, और अगर अटैक टाइम आपने 2 मिलीसेकंड फॉर एग्जांपल रखा है, तो अगर आपका लेवल 2 मिलीसेकंड के लिए थ्रेशोल्ड के ऊपर रहेगा, तो ये लिमिटर या कंप्रेसर इंगेज हो जाएगा। और उसका रिलीज टाइम, मतलब अगर उसका 10 गुना आपने सेट किया, सो सपोज 20 मिलीसेकंड के लिए सेट किया, अगर आपका इनपुट लेवल जो है कंप्रेसर और लिमिटर के थ्रेशोल्ड के नीचे गिरा, और समझो 20 मिलीसेकंड के लिए कंटिन्यूस एक साथ वो थ्रेशोल्ड के नीचे ही है, तो ये हमारा कंप्रेसर लिमिटर डिसएंगेज हो जाएगा, मतलब बंद हो जाएगा। सो इज दैट क्लियर ऑन द? और जो हार्ड नहीं और सॉफ्ट नहीं है, जैसे कि हमने कहा कि जो हमारा हार्ड नहीं है, जैसे ही सिग्नल थ्रेशोल्ड के ऊपर जाएगा तभी कंप्रेसर चालू होगा। बट अगर हमारा सॉफ्ट नहीं है, तो ये लेवल पे भी थोड़ा थोड़ा कंप्रेशन होना चालू हो जाएगा। जैसे ये जरूरी नहीं है कि थ्रेशोल्ड के ऊपर ही पूरा कंप्रेशन होगा। हमारा कंप्रेशन रेशियो अगर 4:1 है, शायद इधर 1.5:1 से थोड़ा कंप्रेशन चालू हो जाएगा, 1.5:1 या 2:1। और थ्रेशोल्ड की, जब थ्रेशोल्ड के ऊपर ही जाएगा, तभी 4:1 का पूरा कंप्रेशन चालू होगा। So does that clarify in Hindi?
Yeah, I think that is clear. Can you, someone says that the attack and release time depends on frequency. Yes, we generally, if you're setting the compressor for different components, like for the HF, MF, and LF, can you just go back to that slide?
Yeah, hold on. Let me just, when I annotate my, hold on. Okay. Which slide? This one?
No, yeah, this one. Yeah. So yeah, this is like just a kind of recommended setting for a HF. You want a faster attack time, so that we are compressing the signal faster, because obviously the HF is more amongst the components, it's the most delicate. And yeah, you would set a longer attack and release time for a sub or a LF component.
Okay, can we move on?
Yes, just one question about how does it work when you put it on auto mode? That the auto mode actually differs from compressor to compressor, like different brands. That I think that algorithm for auto mode is slightly different.
Any good compressor limiter, you got to know what you're doing. Don't set it on auto. I'll tell you what happened. One incident. Auto is very good cosmetic wise. आपका जो auto mode है बहुत ही अच्छा दिखता है cosmetic wise, but you know the DBX driver at 260 used to come with an Behringer के DSP में और DBX के DSP में एक auto EQ का function था. What this used to do is that you give pink noise. आप अपने system को pink noise देते थे. ये pink noise चालू होता था system से, mic लगाते थे, and it used to measure, और अंदर प्रोसेसर में आपका ग्राफिक EQ अपने आप सब सेट करता था. और सब ने ये किया है, मैंने खुद किया है, एंड मैंने अपने स्कूल में जाके ये किया. तो इसमें क्या हुआ कि मेरा जो माइक है was at a point जो stereo system था, right? Left right system. We all make mistakes. Everyone learns from mistakes. I mean, we just keep learning. I set a mic at a position. It was at a point where there was acoustic cancellation. Now, there was this probably around 1.5 kilohertz or 2 kilohertz, and there was this actual acoustic cancellation because of, let's say, comb filtering. जो दोनों speaker के बीच में जो फर्क था, उसकी वजह से मेरे माइक में एक acoustic cancellation नजर आया. और at that time I was using a DBX. I was amazed by this auto EQ function, and I switched on the auto EQ function, and it suddenly just spiked the 1.5 in the graphic EQ में अगर gain देखा, it just spiked the 1.5. Like you could see that in terms of the EQ it said it was doing it. It was not. It was, I don't know. I think it was graphic EQ. It was not doing it on a parameter EQ, but it just spiked it. And then it was my school, and of course my principal came up to me, and then they said, let's just run some people talking, and then suddenly I'm getting immense feedback, and then जो student का जो आवाज है इतना shrill हो गया, और मैं सोच रहा हूँ क्या हो गया. मेरे को लगा auto EQ solves all my problems. मतलब it just kind of gave you that distinct, and then suddenly I'm going in the EQ and I'm saying, अरे ये 1-2 kilohertz में इतना why am I getting so much of gain in this 1-2 kilohertz? And it turns out that the measurement mic was not able to differentiate between an actual system dip and an acoustic dip. Am I clear on this? I mean, is it making sense to everyone?
Perfect, Kiran.
So we all make mistakes. We all learn from mistakes. I you know, there are a lot of things, like as simple as doing something on Rajesh's seminar that day, and I had my frequency time windowing on, and then I'm figuring out what's the problem, and then I had no idea that I'd set a 10 millisecond window, and then that's why I was giving me this you know, high pass filter. And anyways, we'll get to that later, but you need to know what you're doing. So don't go to ज़्यादा करके automatic पे ज़्यादा मत जाइए, but the more you know, the better decisions you can take. That's why आप हमेशा अपने कान को हमेशा ट्रस्ट कीजिए. You know, डेटा के ऊपर आपका कान अगर आपको बोलता है कुछ गड़बड़ है, इसका आप वो you know, मैग्नीट्यूड रिस्पॉन्स पे देख के ये मत देखना कि ये फ्लैट है, सिस्टम कुछ एकदम सही है पर मेरे कान में कुछ तेल या कुछ चले गया है, कुछ something. Anyways, let's just move on. So Rajesh has done this, but and in his great smart session, and it was brilliant. And I'm quickly, because बहुत से लोगों को जानना था कि you know, in a simple way, how do we just set it up? I'm just doing a small, short you know, schematic. हमारा एक computer है, which we're going to start using now for the next maybe 45 minutes, 30 to 45 minutes. हमारा ये computer है जो ये 2-channel के sound card के साथ connected है, and we're going to do a lot of simulations out here and, you know, kind of prove everything. 2 चैनल साउंड कार्ड में 2 इनपुट है, 2 आउटपुट है। ये हमारे यूएसबी कनेक्शन से हमने कंप्यूटर जो मैं यूज कर रहा हूँ, मैं प्रीसोनस, मेरे पास सिर्फ 2 इनपुट है। तो 2 एक यूएसबी केबल के साथ मैंने मेरे ये लैपटॉप को कनेक्ट किया है। यही इसका एक जो आउटपुट है, मेरा जो मरानी LPP 260 है उसको मैंने कनेक्ट किया है। वहां से मैंने एम्पलीफायर को या जो भी हम एम्पलीफायर यूज करें उसको कनेक्ट किया है। वहां से उस स्पीकर को कनेक्ट किया है। साथ ही साथ जो इनपुट है, जो हमारा एक इनपुट है, ये इनपुट को हमने माइक्रोफोन को कनेक्ट किया है। और फिर उसके बाद हमने एक रेफरेंस के लिए एक अलग से सेकेंड आउटपुट से लूप करके सेकेंड इनपुट को दिया है। और you could also use a Y cable from the, I have used a Y cable from the first input and connected to my second input. This is the most simple way of setting up a dual channel FFT measurement system. So what is doing, ये आपको क्या बता रहा है कि हमारा जो रेफरेंस है, जो भी हम सिग्नल दे रहे हैं, you can give music, you can give anything, you can give पंकज उदास का गजल, or you can give बादशाह का गाना, or you can give pink noise, you can give any signal. That's why it's called source independent measurement, because it's independent of the source of a signal. आप कुछ भी गाना दे सकते हैं, both your the जो signal आपके system को जा रहा है and what is going back into your sound card, both should be identical. That's the only requirement. There is no I've seen a lot of, again, to talk about this and going a little off center, Rajesh, correct me if I'm wrong, but as long as the measured signal is, I think, 12 to 15 dB above noise floor, it should give you almost a 90% above coherence, right?
Yep, ideally it's said to be 20 dB above the noise floor.
तो आपको जब भी मेजरमेंट करना है, आपको स्पीकर को एकदम जोर से बजाने की जरूरत नहीं है। मैं वो, and I have done it again as well, and then I've gone sometimes, when at Palm Show we used to be allowed to present demo speakers and play speakers. I used to bajao the life out of those speakers and put pink noise at 100 dB or 120 dB SPL, and annoy the life out of all the workers, and I say, be quiet, sab chup raho, meko measurement karna hai. And we've all done this as well, and then I didn't know what is actually going on, but the more you realize you just can play any music. I could play some good music जो सबके लिए अच्छा है। वहाँ Palm Show में, those who work at Palm and late night, there's no air conditioning for the first 3 days. It's extremely hot. There's carpenter and this thing, and everyone's annoyed. सब बहुत गुस्से में, और मैं pink noise सबके कानों में ढूंसता हूँ 110 dB SPL से. So you can play some good music. It just has to be about 20 decibels above the noise floor, and you're doing a good measurement, irrespective of what signal you use. बहुत ही एक एकदम सिंपल तरीके से बताने के लिए, अगर आप समझो अपना मेजरमेंट सिस्टम एक बुढ़ी आंटी है जो चश्मे से सब कुछ देख रही है, और वो चश्मे से दोनों चीजों को एक जैसे देखेगी, और दोनों के बीच में जो फर्क है वो आपके मेजरमेंट सिस्टम में आपको नजर आएगा। आप उसका इफ शी सीइंग, अगर आप वो एक लाल कलर को she's seeing red color as white, she's going to see all red colors as white, and then you're giving one red color to your system and one red color showing her, and she's actually just comparing what is the difference between the two, and that's what actually doing with your smart measurement system. And then जरूरी नहीं है कि आपका output sound card से लेना जरूरी, it's not necessary. You need to take the output from a sound card. Like Marani has as its own pink noise generator or our own noise generator, and as long as I keep one input, which is my reference, it may not be coming from the output. It could just come out from one of the outputs of Marani, which is giving my noise generator, and a lot of mixers. I've seen Digico has its own pink noise generator. So as long as the noise source is the same, and you're giving one to your speaker system and one as your reference measurement, it's just going to be calculating the difference between the both of them. And then जो last चीज आपको account करना है वो है time of flight, जो propagation, जो speaker से microphone तक आता है. Sound travels at 331 meters per second plus 0.6 into the temperature. जैसे temperature बढ़ते जाता है, sound की गति बढ़ते जाती है, तो ये sound कितने time के बाद आपके microphone पे आ रहा है वही आपको एक डिले डालना है कि सिस्टम को बताने के लिए कि ये इमीडिएट रिकॉर्ड करना चालू मत करो, ये थोड़ा टाइम रुको, ये साउंड को स्पीकर से माइक्रोफोन तक आने दो और तब तक उतना डिले डाल के रुको, उसके बाद आप मेजर करना चालू करो. So I hope this is clear because now we're just going to go into some measurements and see how things are working out. So any questions on this so far?
No.
None.
Okay. So I hope this is an extremely clear schematic and you can take a screenshot and next time you buy a sound card. Sound card बहुत ही सस्ता है, 7-8 हजार में आपको ठीक ठाक 2 channel का sound card मिल जाएगा. Measurement mic would be, Rajesh, how much would be a decent measurement mic? Maybe 6, 8, 10,000?
Yeah, starting from 5 to infinity, I would say. 5,000 से चालू हो जाते हैं DBX.
Yeah, and then you know even if the 5,000 mic would do a pretty decent job, you don't.
Yeah, it does a very good job to start with, to be very frank.
Yeah, let's not don't be too this thing that you need to buy a extremely critical mic or matched pair. And then there was this amazing session. I'll send you guys a link. This by this guy named Jim Yakabuki who did this measurement in a theater, and then वो बोलता है कि you don't need matched pairs from the factory or something to kind of get too critical and too, you know, बहुत से oh no I need some microphone this 20,000 or 30,000. So basically within under 15,000 with a sound card and a measurement mic, आप 15,000 के अंदर आप अपने इसको सेट कर सकते हैं. DSP starts with what 20,000. So you can do a lot of things with, you know, just within 25-30,000 you can kind of make your system sound extremely good. You know, the difference that you will come out is great. So 30 minutes we are just going to use this thing Smart, and I'm just going to quickly bring up Smart. So we're just going to do a revision of subwoofers with Smart and show you what exactly is happening. So this is end-fired subwoofer जो हमने देखा था. ये subwoofers है, end-fired के subwoofer. एक के पीछे एक हम क्या यूज कर रहे हैं कि आगे वाले सबवूफर को जो भी हम फ्रीक्वेंसी सेट करें, we are using a quarter wavelength of the target frequency, and we keep and you know we separate both of them by a distance by quarter wavelength. So which is for example, let's say sound is traveling at 350 meters per second. So at 30 degrees 30 degree के temperature पे sound अगर travel कर रहा है 350 मीटर पर सेकंड की गति से, अगर हम 50 हर्ट्ज के फ्रीक्वेंसी को देखेंगे, we know that the wavelength is 350 divided by 50 जो है 7 मीटर. 7 मीटर का जो क्वार्टर डिस्टेंस है वो है 1.75 मीटर. That's 1.75 meters, which is quarter wavelength. And the delay that we are keeping on adding is of 50 milliseconds, the quarter delay of quarter wavelength. So 50 hertz, you know that the time period is 20 milliseconds. So you're going to be adding a delay of 5 milliseconds. And then as you keep going ahead, you keep adding quarter wavelength of target frequency, and then you keep adding the spacing from grill to grill. जो आपका grill to grill का जो spacing है, वो quarter wavelength जो कि 1.75 मीटर से आपको बहुत ही आपको दोनों के बीच में फर्क रखना है. So what's going to be happening is when you're adding a delay, let's just go back to just the first instance. So when you're adding a delay of quarter wavelength, so let's say 5 milliseconds, and you're separating the subwoofers by quarter wavelength, what is exactly happening is that, let me annotate this out here. ये the time it takes, जो time लगता है ये sound को पीछे वाले subwoofer से, what is the color? It's white, sorry, maybe it's yellow. जो time लगता है ये subwoofer से लाल वाले subwoofer तक आने को, ये हमने डिले ऐड किया है 5 मिलीसेकंड का. जो टाइम लगेगा इसको येलो से रेड तक आने तो, और जैसे ही येलो से रेड तक आएगा दोनों एक साथ आके फिर वापस आगे चलते जाएंगे. और पीछे की तरफ क्या हो रहा है, येलो ऑलरेडी पहले निकल गया है. सबवूफर हमारे जो है सबवूफर ओमनी डायरेक्शनल, सबवूफर्स हैव ऑलरेडी स्टार्टेड गोइंग अप, एंड रेड इज कमिंग अप स्टार्टिंग आफ्टर अनदर क्वार्टर वेवलेंथ. सो क्वार्टर वेवलेंथ के बाद चालू हो रहा है. जब इसका क्वार्टर साइकिल खत्म हुआ, रेड यहाँ से जो रेड सबवूफर है तभी वो उसका वहां से लो फ्रीक्वेंसी आना चालू होगा, और वो आने तक उसको ट्रैवल करने को और एक क्वार्टर साइकिल लगेगा, क्योंकि दोनों के बीच में फर्क है एक क्वार्टर वेवलेंथ का. तो जैसे ही वो येलो तक आएगा उसका ऑलरेडी हाफ क्वार्टर डिले और क्वार्टर क्वार्टर का जो डिले हमने दिया और क्वार्टर ट्रैवल करने का डिस्टेंस जो है वो येलो तक आने तक हाफ वेवलेंथ से पीछे हो जाएगा, एंड विच इज द रीजन यू गेट कैंसिलेशन एट द बैक. So this is the way that we are moving ahead, and we keep adding a delay and we keep adding a delay. And if I'm actually just showing you guys on an animation what it looks like, this is what it would look like. जो रेड लाइन है वो सामने ऑडियंस की तरफ है. आई होप एवरीवन इज क्लियर ऑन दिस.
Yeah,
questions?
I think,
Okay, so let's simulate this on Smart. So I'm just going to quickly start Smart out here. Sorry, too many things running on my PC. There's Windows and everything. So let's start a new session, and let's not just show the live impulse response as yet. So we are going to show the magnitude and phase, and Rajesh has shown me how to use AU Lab. So if I make any mistakes, please excuse me, because the first time using a digital audio workstation. पहली बार मैं digital audio workstation use कर रहा हूँ. And the reason I'm using this is because I have only 2 signals on my measurement card. So you have something known as Soundflower. जो Soundflower जो है वो एक it emulates a just let me just open this, and okay. So this is my internal kind of audio workstation, and it's working on my sound card, which is, I'm going to change the Soundflower 64 channel. I don't have a 64 channel sound card, but ये हम लोग को 2 अलग-अलग signal और दोनों का sum signal दिखाने के लिए we are using this just to emulate this so that you get a good idea of what you're doing. So, and if I go into input output configuration, measurement में आप देख सकते हैं जो signal है मेरा measurement signal Soundflower का input 3 है. I mean, because it's pretending to have a sound card built in of 64 channels, and I've used input 2 as my reference. So this is just signal 1 is input 3, and signal 2 is input 4, and the sum of 1 plus 2 is signal input 5. And I've if you can see out here, if it's visible, I've kind of routed 1 and 2 to input 5. Can everyone see? Nitesh, can you annotate audio 1 and 2 on?
hold on.
So, yeah, sorry. So I'm adding the 2 signals. Let's see if I can quickly generate and see if I'm getting some levels on. Okay. And okay, so I have 2 signals out here. I'm going to quickly run my measurement. Again, like I said, it's comparing one with the other. So it's signal 1, signal 2, and I have to add जो phase trace जो है आप देख सकते हैं is because I need to find my signal delay जो है internal delay, and you can see it kind of gets pretty much evened out. So so now just quickly to go back, let's just look at, where's my presentation? It is, yeah. So if you're looking at this, leave from current slide. If you're seeing, does everyone agree that if I had only 2 subwoofers, आगे की तरफ, both would be in time, both would be in phase. There would be nothing, no time delay difference between the 2 of them. Does everyone agree on that? Because the subwoofer 2 is waiting for subwoofer 1 to come. जो हमारा subwoofer 2 है is waiting for subwoofer 1 to come. We're just going to be looking at 2 subwoofers for now, just to understand, because we have 2 input signal sources. So let's go back to smart, and both are going to be in time. And if you see the level, we're going to be seeing it. Oh, sorry, this is, I need to correct the time. And so this is the level that you're going to get. Actually, just to make it better, let's just use a low pass signal. So it's actually for subwoofers. So I'm going to go back to my AU lab and change these to band pass signals.
And also just change the averaging now so that it is really fast. Like,
okay, yeah. Sorry. It just keeps moving a little here and there. So that's why I'll just keep it 1 second. Just gives a nice smooth this thing. So, and I'm going to, again, just zoom in. For those who know the zoom function, you can just right click and, choose that entire range that you need. So you have, this signal is there. This is your subwoofer. आप नीचे scale देख सकते हैं. 30 से लेके 125 200 almost 150 hertz तक scale है. हमारा जो सिग्नल है जो ग्रीन में है और ब्लू है, ये हमारे दो सबवूफर है. और आप देख सकते हैं कि अगर दोनों को ऐड किया, हम आगे की तरफ जो एक्सपेक्ट करेंगे वो परफेक्ट समेशन है जो है 6 dB, because both are right in time with each other, everything, both are in time with each other, and we're going to capture this. And if I am supposed to add delay to one of them, जो कि आप देख सकते हैं कि let's just go back to my presentation, which is here. पीछे की तरफ अगर आप इसको देखेंगे, हमने सबवूफर को जो है 5 मिलीसेकंड का डिले दिया है और ये क्वार्टर वेवलेंथ से पीछे है. So we can't show distance in smart, but we can at least add the distance, add the time it's taking to travel backwards. So 5 मिलीसेकंड का हमने डिले दिया है और 5 मिलीसेकंड का उसको पीछे की तरफ जाने के लिए टाइम लगेगा ट्रैवल करने को. So is everybody clear that 5, if you are assuming 50 hertz as the frequency that we want to cancel out, 5 milliseconds is the delay given to the subwoofer in front, and 5 milliseconds is the time it will take to travel from front to back. So does everybody agree that there'll be a 10 millisecond difference between towards the back side? If I just put the audience here, out here, between these two subwoofers, there'll be a 10 millisecond delay. Does everybody agree with that? I'm just going to clear it. So
I think, but a couple of questions. I think you finish what you're doing and then we'll address a few questions.
Okay. So let's just remove the sum. And now going back to my AU lab, let's just add, now it doesn't know what is front, what is back. You can choose any one, but let's just say this is a sound delay plugin that Rajesh gave me to use, and it's going to give you the option. So, okay. So I'm not adding any sound delay right now. All are 0, and you can see that the time unit is in milliseconds. So it's anything you put out here is into the multiplication factor. So you can put any value, but everything just goes from 0 to 9, because if you want to use the next one, you have to choose the next. So this is into 10. So I want to add 10 milliseconds. So I'm just going to add 1 unit of 10 milliseconds. So you can see at somewhere around, this is around 50. So this is the phase trace जो आप देख सकते हैं on the left side. If I just quickly, Rajesh, can you mark the phase trace, the units on the left?
Yeah, one second.
Yeah, तो आप देख सकते हैं इसका scale जो है 0 and is going down to 180. And then you can see जो हमारे दो signal है, blue और green, दोनों के बीच में the blue one at 50 hertz is what we're expecting, right? Because you've chosen 50 hertz as a center frequency. At 50 hertz, you're having 0 degrees, whereas the green has gone to minus 180. So there's a 180 degrees. एक दोनों के signals के बीच में 180 degrees का phase difference है. And we expect the signal to, at 180 degrees to, hit in, go almost negative. So let's just quickly measure this and see what the final signal is. And so this is what we are seeing out here in the signal out that is summing both channel 1 and channel 2, which is getting all the way down to infinity. So let me just capture this as signal 2. Oh, I captured the wrong signal previously. Just hold on. Just excuse me. I'm just going to remove the delay. I captured one of the individual signal. I didn't capture the sum signal. So let me just bypass this and capture the sum signal. So I'm going to capture this and clear my drawings. So let me just stop measurement and compare. Hey, why is my, sorry. And so this is my sum signal, and then I'm quickly going to add delay and capture the delay was here. Let me just confirm it's on 10 milliseconds. And yes, it is. Oops, sorry. And yeah. So I'm going to capture the red trace, which is here. जो भी highlighted है, जो भी trace आपका highlighted है, that is going to be the trace that you want to capture. So we have the two captured traces that you can see. I didn't rename them, but let me just rename them as backside and front side. Can everyone see the difference that you're seeing between the back and the front? Rajesh, is it all cool till now?
Yeah, perfect.
And why do we have this null at maybe 140, 150 hertz is because at 50 hertz, it's half a wavelength apart, and 150 hertz, it's 1.5 wavelength apart, and this is going to repeat. But jiska overall level hai, you can kind of change it and make whatever it is. And
one repeating question, sorry, I just thought we need to address this now, is that how do you select the target frequency? Like, why did you select 50 hertz?
I select 50 hertz is because it's pretty much in the center of my passband, and it's very easy to calculate. It's like 5 feet and 5 milliseconds. 5 feet. So basically, the easiest way, if you don't want to get on calculation, okay, you'll be pretty right on a 90% basis. But sound travels at, let's say, in 20 degrees at 344 meters per second. So 344 to feet is 3.28. So you're getting in this at 1,128 feet per second. So basically, let's say 1,100 feet per second. And you know that in 1 millisecond, so it's 1,128 feet per second. So that means in 1 millisecond is about 1.1 divided by 1,000. 1 second has 1,000 milliseconds, right? एक सेकंड में 1000 मिलीसेकंड है, तो इसको 1000 से डिवाइड करेंगे तो ये आपको 1.1 मिलीसेकंड मिलेगा. Easiest way to divide to kind of realize is, you know that जो आपका जो दो सबवूफर के बीच में जो डिस्टेंस है, उसका जो टाइम पीरियड, जो डिस्टेंस है उसका और जो डिले का टाइम पीरियड है लगभग सेम होना चाहिए. So if you're giving 5 milliseconds, 5 milliseconds is roughly around 5 feet, right? Because sound is traveling at 1 millisecond corresponds to 1 feet, 1.1 feet. So 5 milliseconds would correspond to 5 feet. So if you're putting 5 milliseconds of delay, you separate the subwoofers by 5 feet. And if you're choosing 4 milliseconds, you can do it by 4 feet. So if you're doing, let's say, lower time, let's say 8 milliseconds. So if I go to my this thing and change my sound delay to, again, now this is into 10. So I make this 0 and make this into 8. Is it? Yeah. And then you can see the response would shift. The target center frequency would move higher. The target frequency also depends on the size of the cabinet. आपके cabinet का जो size है, it also depends, right? Sometimes to keep front and back distance from grill to grill may not be convenient to keep 3 feet because जो आपका cabinet का depth है maybe 3 feet. So you would probably, and then you don't want them to stay, even if it agar 3 foot hai, aapko ekdam chipkana nahi hai, matlab you're going to have a different load. There's no way for the subwoofers to, the acoustic waves to come out. So you want to keep some distance of at least 1 foot between the front of the grill and back of the cabinet of two cabinets. जो आपके दो cabinet के बीच में at least 1-1.5 फुट का या 2 फुट का फर्क आना चाहिए. And that you will pretty much come to the conclusion that the जो आपका दोनों के बीच में separation है, दो cabinet grill to grill लगभग 4 से 5 फुट का फर्क आएगा. Does that explain everything?
Yeah, but I'd like to add one thing. A couple of questions have been asked. Like the first thing you got to understand is that why are you doing a cardioid setup? You know, the cardioid setup is not to do anything with the crossover range or the crossover between tops to subs. We are doing a cardioid setup specifically to reduce the amount of subwoofer level on the stage, so that the one is that the musicians can have a better experience, and more importantly that the mics on stage are not picking up too much of the subwoofer frequency range. So the reasons we choose 50 to 60 hertz, or rather the reason you make that decision is that what target frequency are you trying to cut off on the stage. Now it would vary because, for example, in a EDM show, in a DJ show, your target frequency may be 50 hertz, you know, because there may be a lot of level on that, which would, one of the reasons, one issue in EDM shows, especially for people who are using turntables with vinyls, is that when too much of the vibration comes, that, and if they don't have those absorber balls properly set up, that will cause an issue on the stage, especially when you have a lot of subwoofers. So it really depends on that. Correct me if I'm wrong, Karan and Rajesh.
Yes, it's absolutely correct. I mean, a lot of reasons may not be stage. Sometimes आप एक room में है which is very reverberant, जो back wall से बहुत से, you don't want too much low frequency going to the back wall.
Something, you may find that there's one resonant frequency which is causing a lot of issue, which is coming from the subwoofers, and you would want to target that as your frequency. So that is the kind of reason why you would really use.
So it's you know, it helps. Like I said, in the front, we're getting a lot of addition. You're seeing you're getting perfect 6 dB addition. On the back, you're getting this thing, and then the easiest way to quickly remember. I mean, you're not going to go wrong. You're going to be right to a point of, you know, 90%. If it's, you don't want to get into calculation, आपको calculation में ज़्यादा घुसना नहीं है. Same units. If I quickly just simulate on Blueprint, just let me in 5 seconds just show you quickly. 5 seconds के अंदर, not 5, basically a minute. I don't resize. Nitesh, is Blueprint visible?
Yeah.
Okay, so I'm just going to quickly add a flow and a stage where I change it to a circle, and radius is, I change a revolve and make the inner one 10. Maybe I don't have any elevation, and I change this over 360 degrees. And so I'm not doing any calculation, just out of the box. I'll just changing my unit to meter to feet and pounds. So I add a cabinet where I quickly add a stacked version and a subwoofer, which is E219, and it's positioned at position 1. I'll just try and move this so everybody can see it. So position 1, and I quickly add at position 2. And because I've used feet, pound, जो मैंने यहाँ feet और pound use किया है, I just move it ahead by say 5 feet. And then we know that the front subwoofer is delayed by 5 milliseconds, so I've added 5 millisecond delay. हमारा weight जो है flat, frequency you can choose this anywhere in subwoofer. Let's just say 50, because we are targeting 50. Although it should be 5.5 feet, but it's just 5 feet, just for convenience of understanding. And let me just change the range to 24 dB, and let's just see what happens if you simulate. So you're seeing pretty much a directional behavior of your this thing. And if I, agar maine isko bypass kiya, if I make it 0, if I change the delay to 0, let's just see what happens. Zoom thing bar keeps coming down. So agar main kuch delay add nahi kiya, you can see ye pura omnidirectional hai. Agar hamara stage piche hai, is giving low frequency pretty much everywhere. And if I just add 5 seconds of delay and measure it, you're getting quite a lot of cancellation behind 86 dB versus probably 108. So probably 20 odd dB, 20 dB का फर्क है front और back में. और आप SPL graph में भी इसको लगभग देख सकते हैं. You can try it at different frequencies. I mean, I'm not changing the distinct, but let's say at 63, what happens? And you're getting a slight back lobe, but still a lot lower, which is say 90 dB versus 100. So it's फिर भी 10 dB का फर्क है आपको front to back, and maybe at 40, if I go at 40, because the color scale is changed. If I just set the max SPL, let's say 110, sorry, 120, 125. आप देख सकते हैं कि the front to back is still about 110 versus around 98. So basically 10 से 20 decibel का आपको back cancellation, you're going to easily get it. And I'm just going to quickly, before we move out for lunch, show you what happens with front back front or gradient arrays. So let me just clear all this and stop my measurements, and again go back to my AU lab, bypass my delay. Okay. And just before lunch के पहले just एक last topic अगर cover करें, and just for everyone's this thing, I've covered impulse, infinite impulse response filters in the last session, but I'm going to directly jump to FiR filters after lunch so that we can finish that first, and then we can do normal Butterworth and everything. Or जो भी है, there's a recorded session that we did last time that you can see all the, आप अलग-अलग crossover देख सकते हैं, Butterworth, Bessel and everything. जो video का link है, I'll send it to you of the last time show in case we are not able to do it. But just for the convenience of everyone, जो आज subject है FiR filters, so after lunch I would like to focus entirely on FiR filters. So coming back now, if I go back to my PowerPoint, जो हम PowerPoint में जाएंगे वापस, end fired को आपने देखा है, we've simulated what we expect, and gradient array में आप देख सकते हैं जो subwoofer 1 है audience की तरफ और जो subwoofer 2 है पीछे की तरफ, हमने लगभग सेम कॉन्फ़िगरेशन यूज किया है, पर इस बार हम पीछे के सबवूफर को क्वार्टर वेवलेंथ से डिले करेंगे. सो if I quickly just scribble, this is the back, and I think I've put a slide of putting the mic as well. But if you're not polarity, does everyone agree जो हमने red area mark किया है, in that area you're going to have the same response that we got on the end fired in the front direction? Does everyone agree with that? Because right now we're delaying the back subwoofer, पीछे के subwoofer को हमने delay किया है quarter wavelength के साथ, और ये आगे की तरफ cancellation होगा और पीछे की तरफ addition होगा. Does everyone agree? Both the waves from subwoofer 1 and subwoofer 2 जो area मैंने red में mark किया है is going to be in perfect summation. And we know that if you're doing a polarity inversion, that's the reason we covered polarity. Now if you're doing a polarity inversion, जो subwoofer 1 और subwoofer 2 के जो signals है वो totally opposite polarity सारे frequency range के लिए होंगे. It's going to be in complete opposite polarity for the entire frequency range from 30 to whatever frequency range you're targeting, 100 hertz or whatever. And so you're going to have complete cancellation. And now on the front side, they are separated by half a cycle. दोनों के बीच में half a cycle का फर्क है. But अभी फर्क क्या है कि पीछे वाले subwoofer का polarity flip हुआ है. And we are going to try and see what happens with that, assuming mic 1 and mic 2. So again, I'm just going to this we are just going to after lunch. This is the last thing we just cover. I'm just going to try and again ये इसका बहुत से तरीके हैं because the problem with end fired subwoofers है कि ये बहुत real estate use करता है, आपके जमीन पे काफी ज्यादा जगह ऑक्यूपाई करेगा. इन्वर्टेड स्टैक में आप इसको फ्रंट एक स्पीकर आगे की तरफ, एक स्पीकर पीछे की तरफ और एक स्पीकर आगे की तरफ सिमुलेट कर सकते हैं. दे यूज जो अकूस्टिक सेंटर है जो सबवूफर के आगे और पीछे, उसको डिफ्रैक्शन मतलब साउंड वेव्स जो बेंड होके पीछे की तरफ जाते हैं वो प्रॉपर्टी यूज करके पीछे की तरफ इट यूजेस दैट सेपरेट द डिस्टेंस ऑफ क्वार्टर वेवलेंथ separation between the diffracted portion of the front facing and back facing subwoofer. Now again going back and just simulating this quickly, if let me just play it. Yeah, let me not play the sum. So if I am having signal 1 and signal 2 on the if I'm showing what is the resultant and without any delay, let's just remove all the delays. Does everyone agree that on the back there is no delay? When I'm going back to my PPT, on the back side, जो red area है, we are not having any. This red area जो मैं आपको दिखा रहा हूँ, this is not having any delay between the subwoofer. Does everyone agree on that? Subwoofer 2 जो है without polarity flip, जो subwoofer 2 है वो रुका है subwoofer 1 के लिए पीछे तक आने के लिए और दोनों एक साथ पीछे की तरफ आ रहे. There is no delay between the subwoofers on the back side in this current scenario. Is everyone in agreement? I hope everyone's in agreement because by the time subwoofer 1 travels to subwoofer 2, subwoofer 2 रुका है, फिर दोनों एक साथ हाथ पकड़ के आगे की तरफ कर रहे हैं. And what happens if, so like I said, the backside, assume this is the backside, the red trace, the sum 1 plus 2 is the backside. So assuming this is the backside, and just one second, I'm going to make Nitesh and Rajesh, I'm going to make you guys the co-host so you can always clear my drawing as well. It becomes easier. Okay. Okay. So this is the backside. And what happens if I flip the polarity? So you're seeing, if I go back to my AU lab, I'm going to, so let's just assign signal 1 just for easier convenience. Signal 1 is the back one and signal 2 is the forward one. So I'm going to flip the polarity of one of them. And you can see now that दोनों का level दोनों है लगभग same है, but एक का polarity पूरे frequency range. I hope you can see that the entire frequency range, there is ये constant 180 degrees जो blue और green base में है, you're having a constant 180 degrees phase shift between the entire frequency range. And this is what happens with a polarity flip. Polarity flip में आपका पूरा frequency range flip हो रहा है, and both the signals are pretty much here. I have my green signal and my blue signal. So if I select my green, आप देख सकते हैं green highlighted है, blue highlighted है. And if you are expecting 180 degrees of phase shift between both the signals, let's just see what happens if we sum. So if I sum, you're seeing nothing. The reason you're seeing nothing, you can see out here on the measurement is having no measured signal out here being generated because ये पूरा जो sum दोनों का है वो calculate हो रहा है. Now let me just capture, I mean, I don't know if there's Rajesh, can I capture a null response? Do you have any idea? The phase is visible, but the magnitude I'm not showing anything. So
no, you cannot capture a null response there.
Okay. Let me just try regardless.
You can capture a phrase, but you won't see magnitude. Basically, that will what will happen.
Yeah. Okay. Let me just call it backside. Oh, it's a trace exists with that name. Okay. So backside gradient is what I'm going to do. So now what's happening on the front side is what we got to see. Let me just clear this drawing. You saw on the back side, we are having complete cancellation. And on the front side out here, again, we are going to be having this subwoofer, which is delayed by जो subwoofer 1 or subwoofer 2 है. We know that we flip the polarity to the back subwoofer. जो हमने पीछे के subwoofer को ये polarity flip किया. और इसका अगर हम delay देखेंगे, यही subwoofer को हमको अभी delay करना है quarter wavelength. Let's just stick to the same one. So let's say 5 milliseconds for the delay that is given out here, which waiting for it, and assume the distance is another 5 milliseconds. So signal 1, we're going to add a delay, sound delay, which is back to 10 millisecond. And now we're going to see the sum, what is happening with on the front side, which is the situation that we have derived now. So we have signal 1, signal 2, and the sum. So let me capture this. This is, let's say, gradient sum. And आप देख सकते हैं कि इधर जो है दोनों का level same है. So on the back side, let me just hide this right now. On the back side, you're having zero response. जो आपका इधर आप देख सकते हैं magnitude कुछ भी नहीं है. तो you're having complete cancellation at the back, which was not the case. Let me just hide this and compare with the end fired as well. So let me just, this is the back side. No, where's the, okay. I've interchanged the, so ये जो है हमारा एंड फायर्ड का ये जो आप ग्रीन में ट्रेस देख रहे हैं, मैंने इसको नाम गलत लिखा है, बट इफ आई एम जस्ट गोना मार्क इट आउट, फ्रंट साइड यू आर हैविंग कंप्लीट समेशन विच इज एक्सीलेंट आउट हियर, एंड बैक साइड जो है आपको थोड़ा थोड़ा यू आर गेटिंग सम सबवूफर लेवल एट द बैक, a lot of cancellation, but of course there'll be a level difference of at least 10 to 20 dB. And if I am going to be doing my, let me just compare. Okay. And on the front side, if I'm using a front back front or gradient array, you can see I'm not getting complete summation, but again, out here within the passband, it's about up to, let's say the -6 dB point is about 80 Hertz. And I can move this point a lot further. I can move this point a little ahead. That's not a problem. I'm altering my delay and, you know, all that thing. वो सब delay और ये सब change करके ये point को थोड़ा आगे shift कर सकते हैं. But from 30 to 80 जो है, I'm getting pretty good summation, but not maximum summation. जो end fired में है, you're getting maximum summation on the front, but you're still having some level at the back. And gradient में आपको you're getting maximum cancellation at the back because level पीछे 0 है, but not maximum cancellation on the front. And then if you just quickly getting back to the phase trace, you're seeing at some point you're also seeing the level to be the same as the signal level. So जो हमारा signal level है, let's just see the blue trace and the green trace. ये जो level है at this point, you're seeing the जो हमारे आगे का portion है at about 83 Hertz. You're seeing that you know the level is, all of them have the same level, and you're seeing out here where is 6 dB, all of them have the same phase. So if I'm gonna just mark it out here, which just goes in agreement with our phase trace, ये जो है जहाँ सब का point, which everyone asking like what window do you select that the phase is pretty much in same. You can see out here it is the phase, all are in phase, and that's why you're getting 6 dB increase in level. And if I'm supposed to just look out here, we know by what we studied that when the level is same, जो some signal का जो level है, it is same when the phase difference is about 120 degrees. So if I'm going to quickly get into my phase trace, जो ये point है 84 around 84 degrees, you're seeing that the blue trace is having a phase of how much is it, -75, and the green trace is having a trace of a phase of around Rajesh, could you let me just move it up. You just move it up with the arrow buttons, or what is it?
Yep, it's arrow. So green is some green, and the difference between green and blue.
Yeah.
1, 2, 3, 30. Somewhere around 100, I guess.
So it's 30 degrees per division, as you can see in this
Yes.
point where I'm this thing, which is 30 degrees per division. So I'm having 4 divisions. Does everyone agree? I'm having roughly around 4 divisions of separation between the blue trace and let me hide the and let me just hide this. Does everyone agree that the level of separation in this area between the blue trace and the green trace is 4 divisions? And you can see on the left side is going from -70 to -190. So which is about 120 degrees of phase difference, which is why we are having, let me just switch it back on. That are having almost the same level of the sum signal out here in this period. So अगर दोनों signals के बीच में जो phase difference is 120 degrees, you're going to be getting the sum signal to have, pretty much the same level. If you want to know what is the phase angle or iska, it's something to do with mathematical calculation of addition of sound waves, and you guys can Google it. But it's if I can just quickly write, जो resultant है, let's say is cos angle is equal to, I think एक का magnitude, let's say A plus B cos जो delta है जो है, again I don't want to confuse you guys, divided by the total magnitude A plus B. This will give you the जो not cos A, let me just call it cos sum. जो sum angle जो pink trace का जो sum angle है, the phase of that is actually governed by A ka amplitude with B ka amplitude into the cos divided by the total amplitude. It's a mathematical equation, don't worry about it. But that's why you're seeing a different phase trace between blue and green. You're seeing a different phase trace out here, and then you can go into calculation of sine wave and you'll come up with a similar angle, phase angle, resultant phase angle for the pink trace. So does this pretty much cover end fired and this thing, and then after lunch we quickly move on to FiR filters, which is the topic that we all, जो हमारा topic है to look into. FiR filters we lunch के बाद देखेंगे. Is there any questions that needs to be addressed right now? Hello, anybody? Yeah.
A few questions on this thing, some amplifier voltages and all. That's it.
That I thought we can keep it.
Yeah, it's let's just I'm going to try and record this and kind of share so that you guys have some reference to go back to later. मैं ये थोड़ा session record करने वाला हूँ to go back for you guys to go back. But I want to really touch on the topic of FiR. And last time was I got very little time, and then one of the mistakes I made was my measurement microphone जो है जो last time was very close to my back wall. So then I was almost at a critical distance where जहाँ हमारा incident energy and reflected energy is almost same. इसके लिए coherence was not good. Again, you learn. I've never done in small measurements in small rooms. It's always been बड़े big ballroom में या बड़े outdoor venue में. तो इसके लिए last time थोड़ा एकदम जल्द में हमने कुछ measurement किया है, and I want to try and cover as much information as possible जो हमारे पास है, so that we get a clear understanding of setting DSPs and FiR measurements to as much extent as possible. So we had 125. We already 25 minutes. हम already 25 minute lunch break के बाहर हैं. मैं चाहूँगा कि I'll try and finish it in about 1.5 hour after lunch, so that हमारे पास at least आधा एक घंटा होगा बाकी के regular filters सिखाने के लिए और बाकी के questions लेने के लिए. So, is that okay, Nitesh and Rajesh?
Yeah,
Yep.
I think so. So we start at 2 o'clock?
Yeah, we start at 2 o'clock, and if anyone has any specific questions, they want to come in and send it a little earlier. If it's something too personal, I can come in 5-10 minutes earlier and show the same. So I just wanted to just go through some stuff with everyone.
Cool, then so let's take a break now and we'll be back at
Okay, अगर कुछ हिंदी या इंग्लिश में आपको सबके लिए रिपीट करना है, प्लीज लेट मी नो. I hope everyone is pretty much in sync with what we are doing here. इसका pace एकदम हिंदी इंग्लिश दोनों में रख के दोनों का लगभग pace I'm trying to keep it as easy as possible सबके लिए सबके समझने के लिए. So we come back after lunch and yeah, should be fun with FiR filters. All right, see you guys soon.
Okay.
Okay.
need an internal noise generator. So thank you, Mr. Marani, for giving me an internal noise generator. Otherwise, जैसे कि कुछ internal जो pink noise में generate करा था, पता नहीं शायद पहले के session में वो digital audio workstation पे routing है कि क्या, but smart से pink noise generator मेरे को accurate data नहीं दे रहा है. So मैं यहाँ जैसे कि मैंने आपको पहले समझाया था मेरे पहले वाले slide में. Let me just start the filters again, and let me also, if there is recording on, I just want to make sure everyone's recording. So it's
I switched.
Yeah. Oh, he's switched on. Okay, fine. So just to go back, like I explained out here, in this slide, I'm not using the loop back signal. So let me just quickly annotate that so you guys know. I'm not using this. I'm using the noise generator of Marani and giving it as my reference signal. So I don't know why my output of my sound card is not giving me, there's some kuch masti chalu hai ki kya, I just need to figure out. Maybe something else.
It could also be, Karan, it could also be when the output is coming out. Now it is, the output is also taking input 1 and input 2 both. It is sending both out of your same output.
Okay.
So normally there's a switch in the sound card which switches it to where it can be separated and it can go same. So something with that, but yeah, we can go ahead.
But I'm actually not even using my second output. So
no,
I don't know
the
why.
Same output, like the sound cards are made in such a way that your input 1 and input 2 both goes to the output.
Okay. Let me just try one last time if I'm just.
Yeah, cool.
Sorry.
And a request to do it more in Hindi.
हाँ जी. Okay. अभी से हम हिंदी में ज़्यादा करेंगे. Sorry for that. थोड़ा सा glitch था, technical glitch, जिसकी वजह से मुझे यहाँ कुछ output नहीं नजर आ रहा था. But then अभी इसका reference. Oh yeah, I need to switch back my reference level. Just hold on. My input needs to be changed back to my sound card. Yeah. Nope. So ठीक है. Let's just use the Marani internal pink noise generator as हम यहाँ Marani में pink noise generator use करेंगे हमारे sound generate करने के लिए. जैसा कि मैंने आपको slide show में दिखाया था कि हम एक reference loop back signal use कर सकते हैं. मेरा reference loop back signal कुछ routing internal laptop पे मेरे को routing एक बार देखना पड़ेगा क्योंकि मैंने internal sound card भी use किया था. तो उसकी वजह से हम डायरेक्ट Marani से एक स्पीकर को देंगे और वही उसका एक आउटपुट एक रेफरेंस को दे देंगे. तो यहाँ मैं आप देख सकते हैं. Let me just go do the schematic of Marani. Nitish, can you feel free to highlight whatever you need to.
Yeah.
But I'll just go full screen. So पहले हमारा आता है दो इनपुट A और B. ये 2/6 है. इसका नॉइज जनरेटर है. This has a noise generator. You can set the delay as well, gain and delay of both the input. You can set an input gain and input delay. जो हमारा delay है, आप कुछ भी set कर सकते हैं. Oh, I think I got the problem. It's I was checking what is the maximum delay. So maybe the delay was.
Yup.
Okay. Sorry. I was just checking all the functions. तो मैं चेक कर रहा था मैक्सिमम डिले कितना है. ये 160 मीटर तक आप डिले कर सकते हो इसको. Roughly in milliseconds, it's about 470-480 milliseconds. So I'm just going to set that to 0. और एक बार I'm going to again try to get this. Is smart visible again?
Yeah.
Okay. Let me just quickly switch back, and I didn't realize about the input delay, but let me just try. Maybe this is the problem. Okay, we are back. Sorry, my bad. It was मेरा ये input delay by mistake मैंने बहुत ज़्यादा set किया था और इसकी वजह से हमें बहुत ही दिक्कत आ रही थी. Let me just switch this off and okay. मैं चेक कर रहा था कि हम कितना मैक्सिमम डिले सेट कर सकते हैं. इसके लिए बाय मिस्टेक मैंने उसको 0 करने को मैंने उसको 0 नहीं किया था. बट इसको ब्लॉक डायग्राम को देखेंगे जैसे कि इनपुट गेन है, डिले है, हम फेज 180 डिग्रीज, फेज इसमें भी फेज ही लिखा है बट एक्चुअली ये वापस पोलैरिटी है जैसे मैंने आपको समझाया। हमारे इनपुट में हमारे पास अलग 11 आवाजेस 1 2 3 4 5 6 7 8 9 10 11 12 13 अलग अलग आप इनपुट EQ सेट कर सकते हो जो आपके इनपुट सिग्नल में कंप्रेसर है और वापस म्यूट अनम्यूट का फंक्शन है। और यहाँ मैट्रिक्स है जहाँ आप ये कोई भी सिग्नल को कहीं भी रूट कर सकते हो। तो ये मैंने इनपुट ए, मैं यहाँ पे अपना इनपुट ए दे रहा हूँ जो कि मैंने मेरे साउंड कार्ड का आउटपुट इनपुट ए में दिया है और इसको मैंने आउटपुट 1, आउटपुट 2 और आउटपुट 3 को दिया है। ये आप जो नीचे मैट्रिक्स देख रहे हो आप कोई भी इनपुट को कहीं भी रूट कर सकते हो। द मैट्रिक्स दैट यू आर सीइंग डाउन, you can route any input to any output. Now what is the reason for that is because many times बहुत बार आपके पास एक fixed two-way box होगा जिसके अंदर already passive crossover है। not only the not many processors give you this function, बहुत से processor आपको function ये देते नहीं है जहाँ आप let's say if I have output 1, I can also get the output 2 to output 1. Hold on. तो आप देख सकते हैं कि अगर मैंने अपना इनपुट दो अलग अलग चैनल को दिया है, कैन आई जूम इन? ओके, do you want me to zoom in on that?
No, I think okay, I mean I just marked it here in yellow.
Okay, cool. जो नितेश ने अभी यहाँ येलो में मार्क किया है आप देख सकते हैं कि मैंने आउटपुट 2 को आउटपुट 2 के टर्मिनल छोड़ के आउटपुट 1 पे दिया है। ये कहाँ हम यूज करेंगे, जैसे कि बहुत से एप्लीकेशन है जहाँ आपके पास मिड हाई का कैबिनेट है जिसमें ऑलरेडी पैसिव क्रॉसओवर बिल्ट इन है। उसके अंदर आपको अलग अलग HF के लिए अलग कंप्रेसर लिमिटर सेट करना है और MF के लिए अलग कंप्रेसर लिमिटर सेट करना है। और उसके साथ ही साथ हमने देखा है कि काफी बार जो let me see if do I have okay, let's show this PPT, and if I have a slide which has the speaker and I can show the different, okay, ये जो आप कैबिनेट का क्रॉस सेक्शन आप देख सकते हैं कि अब हमारा पैसिव क्रॉसओवर ऑलरेडी बिल्ट इन है जिसमें HF काफी अंदर है। The HF is quite inside compared to the woofer, but because it has a passive crossover and you have only a single input, there are many times that you can't do anything about the delay. There is हमेशा एक finite दोनों के बीच में distance है। So there are times that you could separate the frequency bands at the crossover frequency, add your delay to 1, maybe इसमें आपको woofer को HF woofer को आपको delay add करके वापस sum करना है। So this could be a very useful function when is Windows visible again?
Yeah.
Okay. I'm just switching desktop, so I don't know if it actually switches or not. So ये बहुत ही useful function है जहाँ आप you can setting the matrix, you can set output 2 to output 1, and you can add your own crossover frequency in the in different blocks and HF को अलग, MF को अलग, और बहुत सी कंपनियां करती हैं। I know that DNB uses this feature because they use passive crossover. DNB अंदर अपने cabinets में passive crossover use करती है। So this is something that's called multi-band limiting. और इसका फायदा क्या है? The advantage of this is sometimes आपका जो signal level है, maybe if it is limiting the HF, you don't want the mid to be left out. Sometimes you just don't want, maybe a lot of the intelligent speech and everything is still there. You want to retain the dynamic information. So again, it's a little more complicated in terms of setting it, but you could set it to protect your individual components separately. So this is something that is a very useful function where the matrix can be routed, anything can be put anywhere. This, what you see here, channel 1, channel A insert is your FiR data. यहाँ हम हमारा FiR input data enter करते हैं। यहाँ दोनों चैनल A चैनल B का FiR input हम enter कर सकते हैं, and each FiR will get to taps and coefficients later, but just to let you know, the Marani LPP 260 has 1024 taps on the input and 512 taps on the output. And just going to the output block after that, if you see out here, you can set जो हमारा crossover है, you can set it as IIR or FIR. Any of them is okay. Hold on, why is it not setting? Okay, so you can set it as IIR or FIR, whatever type. And here FIR filter आप देख सकते हैं कि इसको high pass filter, band pass या low pass filter या all pass filter या bypass कर सकते हैं. And you can also import third-party software, third-party filters that you are setting. How to make third-party filters? I'm going to get on that as well. I'm going to get into as much detail as I can to explain FIR filters. The number of taps you see, जो हम taps use करें, जो bank है, it shows you the number of coefficients you're using from the bank, and it is again showing you the attenuation that you want in the stop band. जो आपका stop band का attenuation है, आपको कितना steep, आप अगर left में graph देखेंगे तो ये बहुत ही steep slope है. If you want something shallow, this is you keep a lower attenuation. So attenuation is just basically कितना आपको level stop band में use कम करना है. And these are different windows. By default, आप Kaiser use करो. I don't want to get into too much into details of windowing because it's another mathematical computation. और बहुत कम फर्क है सबके बीच में. There's not in our application, you don't get, there's not a big difference, and how FIR filters work, we'll get into that. But first, we'll show you a demo of what is exactly happening between IIR and FIR filters. So I'm going to यहाँ मैं मेरा EQ bypass करने वाला हूँ, और जो मेरा slope मैंने set किया है, इसको भी मैं bypass करने वाला हूँ. I'm going to bypass the slope on channel 2 and do the same on channel 1. I'm going to keep no cutoff, and you can see channel 1, channel 2, दोनों का, and let me just see the gains are okay. Channel output 1 is -6. I'm going to keep it 0. So someone had asked me about setting the level. किसी ने एक सवाल पूछा था सब component के बीच में level क्या set करना है. सबका level लगभग same होना चाहिए. So we are going to go quickly into measurement. I've again, just to show you guys, मेरा input from my sound card is gone to input 1. Channel A 3 output को गए, output 1, output 2, output 3. And I'm again going to switch this back to output 2 only because मैंने अलग-अलग use किया है. We're going to do two applications. One is with a passive box and one is with a two-way box. हम दो application करने वाले हैं, एक passive box के साथ और एक two-way box के साथ. Right now, what we're going to do is going to see a two-way box जहाँ की बहुत से लोग इंडिया में लाइनर का नया फैशन आ गया है, जो सब लोग काफी लाइनर यूज कर रहे हैं. एंड बहुत से लोग वो चाहते हैं कि हम पैसिव क्रॉसओवर यूज करें. नाउ एडवांटेज ऑफ पैसिव क्रॉसओवर है कि ये बहुत ही इजी है, प्लग एंड प्ले, एक ही इनपुट देना है आपको बॉक्स को और इमीडिएटली आपको आउटपुट मिल जाता है. बट द प्रॉब्लम विद पैसिव क्रॉसओवर इज दैट आप देखेंगे कोई भी पैसिव क्रॉसओवर, आप सीन सो मेनी लाइनर में जिसका पैसिव क्रॉसओवर जल जाता है. सो इन दैट आप काफी एनर्जी वेस्ट कर रहे हैं अपने क्रॉसओवर के ऊपर. सो there's a lot of energy that you're actually wasting in your passive crossover. And in today's time, a DSP is not that expensive. आज के टाइम में DSP इतना महंगा नहीं है. And the cost of maybe one amplifier, अगर आप if you can assume maybe 4 to 8 line arrays, maybe 4 line arrays का सारा HF आप एक एम्पलीफायर के ऊपर यूज करेंगे. एम्पलीफायर का कीमत आज के टाइम में 30-40 हजार HF 4 बॉक्स के HF को चलाने के ऊपर 30-40 हजार के ऊपर नहीं है. एंड सो दैट्स वन एक्स्ट्रा एम्पलीफायर दैट यू यूजिंग and you're eliminating the cost of the crossover. Any good crossover, जो अच्छा crossover है, for a line array would not be costing anything less than 2,000-3,000. A good one, a good line array, a good crossover. So when you're using this thing, if you're 4 line arrays, you're probably cutting down 10,000 rupees on your passive crossover. आपने passive crossover 10,000 रुपए बचा रहे. But at the same time, amplifier का एक cost आपको add करना है, DSP का एक cost add करना है. Performance में ज़्यादा बेहतर होगा, protection आपको ज़्यादा बेहतर होगा. Long term, maybe on a system that costs maybe 5 to 10 lakhs, you're probably spending 50-60,000 or 1 लाख आप 10% आप ज्यादा खर्च कर रहे हैं. मेरे हिसाब से एक लाइनर के एप्लीकेशन में बहुत ही जरूरी है, क्योंकि you're trying to keep maximum energy component में, और crossover का unnecessary you're not heating up the crossover. And then you have side field like or two-way cabinet जैसे डबल 15 इंच या सिंगल 15 इंच या फ्लोर मॉनिटर, जिसमें आपको चाहिए कि एम्पलीफायर चैनल ज्यादा यूज नहीं हुए and you're using a passive crossover inside. So we're going to do 2 examples. First we're going to do a two-way box. पहले हम लोग एक two-way bi-amp box करने वाले हैं जहाँ HF और LF को अलग-अलग amplification दिया है. So I'm going to quickly just come into, I'm just going to mute the HF, unmute the HF and go back to smart and put this on the side and switch this on.
Can you reduce the level a bit?
यहाँ आप देख रहे हैं कि मैंने इसको कोई भी क्रॉसओवर नहीं अप्लाई किया. दिस इज द नेचुरल रोल ओवर ऑफ द हाई फ्रीक्वेंसी ड्राइवर. दिस इज व्हाई आई वाज सेइंग दैट every HF, every manufacturer, सबका material, सबका construction design, सबका अलग है. So everyone would have their own natural roll off in terms of the HF, and the phase response and everything will determine on the combined effect of using आपका crossover. जो आपका final phase response है, आपका आप कौन से filter type use कर रहे हैं इसके ऊपर depend होगा. And you can get all the data pretty accurately. आपको data काफी accurately यहाँ मिलेगा. And ये से ही हम लोग MF पे जाएंगे. तो if I'm going and unmuting the, I'm muting the HF and unmuting the, so I'm going to capture this. So you're seeing that the level of आप देख सकते हैं कि जो लेवल हमारा जो MF का है वो काफी HF के मुकाबले कम है. That's pretty evident from the specification sheet. जो आप कोई भी specification sheet देखेंगे उसमें MF का लेवल जो है काफी कोई भी woofer का लेवल 97-98 dB SPL होता है 1 watt at 1 meter, and the HF is always around 107-105. It's always 10-15 dB more. तो HF का sensitivity same power देने के ऊपर HF का sensitivity will definitely be a lot more. In a room that जो हम यहाँ room use कर रहे हैं यहाँ जैसे room आप देख सकते हैं कि ये काफी response आगे पीछे है, and that's because a lot of reflections are coming. One of the functions that smart gives us, if you can see out here on the right side, is called frequency domain time window. तो यहाँ आप जाके ऑप्शंस में राजेश इज इन ट्रांसफर फंक्शन, या इट्स आउट हियर. यहाँ आप देख सकते हैं नीचे एक enable FTW है which means आप एक समय का विंडो बना सकते हैं कि I am going to be capturing data only for that much time. I'm not going to be capturing data for more than that. So you're trying to eliminate some reflections that you may feel are interfering in this thing. So out here on the right side, you can see that there is an option that's saying frequency time windowing. And I just have to switch it on. और जो यहाँ टाइम मैं सेट कर रहा हूँ, जो भी मैंने जो मेजरमेंट चालू किया है उसके बाद से एक विंडो, एक खिड़की खोलेगा saying that I'm going to take all the data for that much time. So we know that time period is for every frequency. We know the time period for 100 hertz. The time period say 10 milliseconds, and maybe for 1 kilohertz is 1 millisecond. And I don't want to take too much data from probably more than 10 milliseconds, and I'm going to try and ignore the data which is probably before that. So if I just, I'll show you the difference, what is there between both of them. So, and if I enable this, आप देखेंगे कि ये बहुत ही smooth हो जाता है. So that is one function, but just to give you guys a heads up, it's not the same as averaging. So if I show you what's the difference between averaging and so I'm just going to, and time window और averaging के बीच में फर्क क्या, I'll just show you quickly. And you can see that below 250 hertz is becoming extremely smooth because that it's not kind of taking enough data. So if you want this to be accurate, you should probably buy. I used to use a software. मैं एक software use करता था, which का नाम था FiR Capture. This was by the founder of Lab Group, and Lab Group and the founder that they had invented this thing called FiR Capture, which is by a company named Wave Capture. बहुत से लोगों ने सुना होगा. And that used to usually recommend जो भी time period है, for example 10 millisecond का मैंने यहाँ window set किया है, तो usually anything above that, so 10 milliseconds for 100 hertz, I would consider reliable data from around 200 an octave higher than that. So something जो 200 hertz के ऊपर का data मैं उसको accurate तरीके से देखूंगा. So this is what I would do for just to quickly show you on averaging. So this is what happens. Let me just capture it quickly. Rajesh, does time windowing work on captured traces as well? Have you tried it? I don't know.
Yeah, if you have taken with it enabled.
Okay, so, and then I'm going to disable it, and then magnitude smoothing maybe 1/6. So I don't know. I need to capture it as a second trace, I guess. So so what you guys are seeing right now is an average response, and then the time window one is this response.
Do you mean smoothing current?
Oh yeah, sorry, not averaging. I was talking about smoothing. My bad. Is that clear that the difference between smoothing and time windowing is not the same? I mean, if you're time windowing doesn't mean you're smoothing it really. So I just want to show this so that people are clear that time windowing is not the same as smoothing. And
I would not recommend anyone to use time windowing, to be very frank.
Okay, let's not use time windowing.
At least jitne apne paas participants, I would not recommend that.
Okay, let's not use time windowing, and let's disable that for now, and let's just go to the box high frequency and this thing. So आप देख सकते हैं the level difference between we don't want to match the top level. You want to manage the you know, the average level, which is somewhere around here. What is the level I see around at 8 kilohertz के आसपास जो level है जो मेरा trace का, which is around near 0 dB, which is pretty much flat. ये जो ऊपर के peaks है, मैं हमेशा उसको level में काफी कुछ कम कर सकता हूँ. And if I go back to my mid frequency, my average level is somewhere around -6 dB. So मैं quickly अगर gains में जाऊंगा, I want to reduce my output by say -6. And if I quickly switch it on and measure it again, you're seeing that this line is pretty much जो हमारा line है वो काफी हद तक HF और MF का लगभग सेम है. वापस हमने कहीं कुछ भी ये हमने यहाँ कुछ ऐड नहीं किया है, कोई भी क्रॉसओवर या फिल्टर स्लो हमने ऐड नहीं किया है. And we're just going to quickly examine. Let me just capture this. So now just quickly going over, I'm just going to quickly do this thing saying that this is what I feel should be the crossover point. आप देख सकते हैं कि I know that based on the size of my HF, मेरा HF ज़्यादा बड़ा नहीं है. I'm going to try and keep it as you know, somewhere in the middle, somewhere around this area, around the 2.5. जो 2.5 किलोहर्ट्ज के आसपास मैं इसको क्रॉसओवर रीजन रखूंगा. आप देख सकते हैं दोनों का ओवरलैप हो रहा है लगभग ये लेवल पे. And then I will see the phase response. So just quickly disabling and adding maybe 2.5 kilohertz. So जो हमारा ये output है, I'm going to first use IIR, and then I'm going to show you guys with so the high pass filter is probably 24 dB an octave Linkwitz Riley, and again I can switch it on and measure again. So you can see कि ये हमारा जो HF का level है.
Do you want to take your mic a bit closer?
Okay. Hold on. I'm just going to quickly add a new delay. Okay.
Okay, just hit that small this thing. You don't have to do fine delay every time.
No, but I want to keep it fixed. I want to keep it fixed because
you can hit it and then again switch it off.
Yeah, but sometimes what I've noticed is it kind of gives this varying kind of number, and then it just sometimes it just gives me like this 0.05, 0.1 millisecond up and down. But anyways,
now I can see the HF better. Yeah, now the HF is better.
So the HF, आप देख सकते हैं इधर जो मेरा HF का trace है, it's compared to the original, the level has gone down, And I'm just going to just delete this one and capture this and say HF 2.5. And again, I'm going to add this to the MF, and you can see the phase response. Your phase response देख सकते हैं, ये 0 to 360 degree का, it's taken a full cycle. And जिसने last time का crossover का section attend किया था, उनको याद होगा कि every order, every 6 dB an octave, they're rotating the phase by 90 degrees. So since we are using, you can see we are using 24 dB an octave, we are expecting the phase to go up by 360 degrees. So this is something that falls in line with our expectation. There's nothing different, कुछ surprising नहीं है, क्योंकि हमने fourth order का crossover use किया है. So this is something that we're expecting. Now, quickly going back and muting the HF and going to the MF and adding, और यहाँ वापस हम लोग एक low pass filter 2.5 kilohertz का, let's just take 24 dB an octave linked to Riley, for example. So you're seeing, let me just capture this as well. So you're seeing out here, which is the crossover region. Like I said, we are looking at something where the level difference is not too big. So something that where the level difference is similar, that's where we want to be in phase. And Rajesh, you want to talk about phase slopes and delay, the steeper slope and something like that? Anything you want to add right now? Should we do it right now? Hello?
No, Karan, I don't want to add anything. You are doing good.
Okay. So Rajesh, could you help me to draw the tangent or just the tangent of the phase trace on both of them?
Sure. Okay, this is from.
So जो राजेश ने ड्रॉ किया है वो आप देख सकते हैं कि ये HF का फेस स्लोप है. एंड लास्ट टाइम जो हमने किया था, आपको मालूम है कि जो स्टीपर स्लोप है फ्रॉम लेफ्ट टू राइट, इट इज डिलेड फर्दर, और जो फ्लैटर स्लोप है वो ज्यादा इन टाइम है. सो आउट हियर हम जो HF है उसको एडवांस नहीं कर सकते हैं, तो MF को हम पीछे करेंगे, बिकॉज एंड इट्स वेरी कॉमन to have HF delayed more, and the reason for that is जो आप देखेंगे जो हॉर्न में HF हमेशा थोड़ा पीछे होता है, so it's always the HF is delayed further. So right now our choice to delay will be the mid frequency. So if I quickly just check in the crossover region, my mid frequency is the difference between both of them is probably in divisions maybe
3 boxes
60,
at the most.
Yeah, 3 boxes at the most. So 3
Yeah,
boxes
90
is 90 degrees of difference in phase, and the frequency is 2.5. So just quickly getting out that, I'll just put the calculator here. So 90 divided by 360, and that is into
somewhere
1000
between 0.1
divided by 2500, right?
Hmm.
So it's about 0.1 millisecond. So that's the kind of delay that just you add 0.1 and on the mid, and you should be good to go. So let's try that out. If we get a similar phase response out here.
Let's take, Karan, do you want to take a response like this without adding the delay first, the overall response of the speaker?
The thing is, it'll be pretty much in this thing because 90 degrees is still giving you some summation. It's not okay. You could be. Let's just take some summation.
At least thoda sa change to dikhega.
Okay. Let's switch on both of them together and see the measure response. And if we go back and so we had to delay the mid, and that was in output 2, and I'm going to be saying 0.1 millisecond. And if I quickly again just mute the HF and let's just see the phase of the so the brown trace was a HF, right?
Yep.
So let me just capture this MF 0.1 millisecond.
We'll need something more actually.
Yeah, there are again we've not set a crossover based on, it's not a default for crossover. So it also, we've just taken a arbitrary crossover and kind of seen what is this thing. But the idea is to just show that out here, jo crossover frequency mein hai, we are pretty much in phase. Let me just.
Can we do 0.12 or 0.13?
Yeah, we could. That's output 2, and that's delay is 0.12. You want to measure it again?
Yeah, sure.
Just a bit down, but yeah.
Yeah.
You want to capture it?
No, it's fine.
Oh, just hold on. The wires got unplugged. Just give me 1 second because I've actually unhooked the and put wires inside manually. So hold on. Move it back to 0.10 or 1.2 is fine.
Increase it a bit more.
You want to increase the delay?
Yeah, I want to see with more delay. Yeah.
Okay. What, 0.15?
We'll go to 0.2 directly.
Okay. Are you trying to look at phase inversion and this thing?
Yeah.
Oh yeah, that's. I wanted to come on to that a little later.
Okay. Fine. Okay.
You're trying to match the slopes and invert the phase, right?
Ekdam perfectly matched. Yes.
I wanted to come to that later, but I want to do step 1 first so that they kind of understand the difference.
Okay.
So just move to 0.1 again, and I'm going to unmute. So, does everyone agree with the phase at the crossover? Jo hai, it's pretty much in this whole region. It's pretty much एक साथ, it's similar. HF or MF का phase एक साथ जैसा है. And is there someone here? Yeah, someone is here. Okay, so let's do unmute the HF as well and have another simulation. So let me just disable this and sorry. So you can see, is the color similar or can make out the difference?
Now you can.
Okay. So you can see in the crossover region that you're having some different sum. And then if you're seeing the phase space, again, you're seeing a full 360-degree change in phase. Does everyone agree with this measurement of 360 degrees of phase?
Yeah.
We are using a 4th order crossover, so it's very natural for us to expect. ये हमने 4th order का crossover use किया है, तो ये बहुत natural है कि हमें ये 360 degrees का phase shift मिलेगा, क्योंकि ये हमें immediately as we know that there's going to be a phase shift of 360 degrees. So this is where finite impulse responses come in. मतलब finite impulse responses, the advantages, आप इसको phase को काफी linear रख सकते हैं. And one of the ways to do it is, let's say we've just done this, for example. Let's just we use infinite. Actually, I'll just show you if we save this and then I'll cross them with finite impulse response filters, and you can compare the phase space. So अभी हमने infinite impulse response का phase crossover use किया है, जो बहुत से crossover में आपको दिखेगा. हम ये इसको FiR के filter में आप देखेंगे. So HF is, and the advantage of FiR filters you can make them बहुत very steep, you can make them brick wall. मतलब फिल्टर्स को हम आप देख सकते हैं कि इनफाइनाइट इंपल्स रिस्पांस का काफी जेंटल स्लोप है, मतलब एकदम स्टीप भी करेंगे तो फिर भी एनर्जी इज ऑलवेज देयर, मतलब एक ऑक्टेव नीचे तक भी आपको एनर्जी कुछ आधे ऑक्टेव तक एटलीस्ट 15 से 20 dB लेवल कम करके फिर भी आउटपुट मिलेगा। FiR फिल्टर्स में आप जितने टैप्स आप बढ़ाते जाएंगे, डोंट गेट टू मच टू कंफ्यूज अबाउट टैप्स, आई विल एक्सप्लेन हाउ इट वर्क्स एग्जैक्टली इन सम टाइम। थोड़े टाइम में आपको समझाऊंगा कि टैप्स कैसे चलते हैं, पर जैसे ही टैप्स बढ़ते जाते हैं आप बहुत से उसको बहुत ही स्टीप, मतलब ईंट की दीवार की तरह रख सकते हैं कि मतलब वो जैसे ही ईंट के दीवार को हिट करे वो इमीडिएट उसका ड्रास्टिक लेवल ड्रॉप आप इमीडिएट आप देख सकते हैं राइट ग्राफ पे।
Yeah, one
second. And
I know it's not clearing for some reason.
let me try. Okay.
Huh.
Okay, so if you're just highlighting it, Nitish, are you highlighting?
Yeah.
Actually, don't highlight it. Just match the slope, because the minute I switch back, again the graph is going to change. So if you just show the slope, it will be. So let me just draw a line out here, and yeah, okay, cool, thanks. And if I go to an IIR filter, you're seeing the slope बहुत ही gentle, and if I make it steep, let's say 48 dB an octave, and it's still not as steep as an FiR filter. So is everyone understanding this part? And then we can quickly move on to making the same measurement with IIR filters. हम कुछ EQ कुछ भी अभी नहीं कर रहे. I'll quickly just show you an FiR filter. Let's just make it low pass filter, and I'm going to change the frequency to probably 2000 because it is less overlap. So it's, and we can actually just compare both the responses as well. So just hold on. Let me just mute my MF and switch this on. Okay. एक चीज जो मैं आपको बोलना चाहूंगा कि whenever you start using FiR filters, उसका जो एक ड्रॉबैक है जो है डिले और लेटेंसी। जैसे आप FiR फिल्टर यूज करेंगे उसमें आपका डिले बढ़ते जाएगा, which is why I will come to that again when I explain FiR filters. But I just want you to see that the phase space will go up because we need to add some more delay. So don't get confused कि मैं delay add क्यों कर रहा हूँ. So let me just unmute this HF again. And if I compare it with the HF out here, and जो डेटा आगे की तरफ आपको नहीं मिल रहा है क्योंकि मैंने डिले अभी तक फाइंड आउट नहीं किया है. अगर मैं डिले इंसर्ट करूंगा तो आप देख सकते हैं कि ये काफी स्टीप फिल्टर है. Is this visible? Nice and visible?
Yeah.
Okay. So one of the advantages of that is that you can use इसको हम बहुत ही कम frequency पे क्रॉस कर सकते हैं क्योंकि ये ब्रिक वॉल होने की वजह से you don't given a lot of power. जो decaying slope है उसका पावर काफी हद तक कम हो जाता है. उसकी वजह से आप देख सकते हैं कि मैंने इसका क्रॉसओवर फ्रीक्वेंसी 2.5 के बदले में 1.8 रखा है, 2000 रखा है. फिर भी इसका ड्रॉप जो है ये काफी स्टीप, काफी हद तक नीचे ये पॉइंट से गया. ये एक्स्ट्रा एनर्जी जो है जो आप IIR फिल्टर में आप देख रहे हैं वो HF की तरफ जा रही नहीं है. and you're not unnecessarily wasting power on it. It's not actually exactly wasting power, I would say, but you're getting very less level from the HF. Whereas if अगर आप ये पॉइंट पे अगर ये फ्रीक्वेंसी है 2.3 किलोहर्ट्ज, 2.3 किलोहर्ट्ज पे आपका लेवल डिफरेंस ऑलमोस्ट टू ऑलमोस्ट 6 dB या इट्स अराउंड 6-8 dB आपको ज्यादा मिल रहा है. The advantage of this is you can cross the HFs at a much lower frequency. आप देखेंगे कि एडमसन का डायरेक्टिविटी जो है उसका डायरेक्टिविटी मेंटेन क्यों होता है क्योंकि ये उसका क्रॉसओवर फ्रीक्वेंसी ऑलमोस्ट नीचे 800 हर्ट्ज तक है. अगर आप कोई भी अगर बाजार में जाएंगे बोलेंगे मैंने अपना HF, if you tell anyone I've crossed over my HF, cut off my HF at 800 hertz, they'll be like पागल हो गया, HF का कॉइल उड़ाने का है क्या? So this is one of the advantages of FiR filters that you get. You can make really steep filters. This is one of the advantages. And then डायरेक्टिविटी बहुत जरूरी है. काफी हद तक आप देखेंगे लाइव शो में आपको चाहिए कि स्टेज पे ज़्यादा एनर्जी आपके कैबिनेट से स्टेज की तरफ नहीं आए. You don't want a lot of energy coming from the cabinet to the stage, and this is where your HF is going to retain as much directivity as it can. आपका HF जो है हॉर्न की तरफ के साथ काफी डायरेक्टिविटी काफी हद तक रिटेन करेगा. And we're going to just do it for the MF as well. Just move it all over, and probably say the low pass is let's just change this to FiR filters and make it maybe 2800 for that matter, because it's extremely steep. So, and if I save it, actually let's just see the MF first. So मैंने capture नहीं किया, but just trying to show you guys how the filter is actually working. So let me just go on and switch the HF back on. Because of the overlap, you're seeing this extreme gain, but I can just kind of move the MF a little behind.
Is the delay still active on it? The delay that we had put?
Yeah.
Okay.
The delay is pretty active. So just to capture, I mean, this is just where they're overlapping a little. I don't want to waste too much time on it, and I can quickly just use a bell filter to remove it out. But have a look at the phase trace is what is something that I would want to, so before we start linearizing the entire phase. So this is my phase. Oh, I've not captured it. Hold on. Let me just capture this. And if you compare the phase of this, where's the other one? Summed one? Yeah, this is the one. I don't want this. Okay. So you can see the phase response. Don't look at below 250 and all. Let's just look at from 250 hertz onwards. Let's just look at the phase. You can see that the phase of the FiR filter is pretty much linear. Is not going through much rotation. It's going through some rotation at higher frequencies, and we can correct it. So one of the ways to correct it is what I'm going to show you guys now. How to get an extremely linear phase response and a magnitude response. एक आपको दिखाना चाहूँगा कि बहुत सी linear phase response और magnitude response आप कैसे पा सकते हैं. So we've captured this response, and I hope everyone can at least see the difference between जो हम regular crossover use कर रहे हैं उसका phase shift and using FiR filters the phase shift. Is that clear? Is that part clear? And then we can move on to kind of linearize it.
Yep, I think so.
Okay.
Yeah. So, just one thing, Karan. I just wanted to do one more thing. On your transfer function, I want you to put up the coherence ka upar so that all this below 250 we cannot see itself. Just hit T. Yeah.
Yeah. Okay.
And the coherence blanking.
So I'll tell you why I don't.
Why?
Okay. I'll tell you why I don't want to use a coherence blanking. I can use a coherence blanking. It's a very good this thing. सबको बताने के लिए कोहेरेंस की ये ब्लैंकिंग से क्या होता है बेसिकली जो कोहेरेंस आपके जो मेजर्ड सिग्नल का क्वालिटी आपको बता रहा है. ये आपको बता रहा है कि ये जो मेजर्ड सिग्नल आपको आप देख सकते हैं कि ये 50 हर्ट्ज पे मेरे को ये कोहेरेंस काफी नीचे गिर रहा है क्योंकि मेरे माइक में कुछ पावर सप्लाई का हम आ रहा है. There's some hum coming out of the power supply, which is why it's saying that this is not part of the signal that we've sent out. So don't consider it. So this is something that I didn't want to like sit and figure out because it'd probably be a good example to use out why the coherence trace is absolutely necessary. Now, Rajesh, just to explain you as well, why we use less of coherence blanking is because when you're exporting this curve, let's say if I use less coherence blanking, and if it is on my, let's not use it, this FiR filter. So this is a FiR filter, and if I copy it to let's just say इसको copy करना है मेरे को ASCII values में, and right now is my coherence less. Let me just reduce it further. जब हम कोहेरेंस यूज कर रहे हैं, काफी कुछ मैग्नीट्यूड आप देख सकते हैं, क्या मैग्नीट्यूड और ये रिस्पॉन्स काफी नंबर्स पे आप इंफॉर्मेशन थोड़ा मिसिंग हो जाता है. और जब कॉपी करते हैं आउट हियर, लेट्स जस्ट सी नोटपैड, और यहाँ इसको पेस्ट करेंगे. तो अभी जो स्टार देख रहे हैं, ऑल दी स्टार्स इज इंफॉर्मेशन दैट इज नॉट कैप्चर्ड. ये जो स्टार आप देख रहे हैं, ये इसका एक्चुअल मैग्नीट्यूड, और इसका अगर मैं फाइल के ऊपर जाऊंगा, ये मैग्नीट्यूड और ये हर एक फ्रीक्वेंसी पे उसका मैग्नीट्यूड, फेज और कोहेरेंस का इंफॉर्मेशन बता रहा है. तो अगर कोहेरेंस हम उसको टॉलरेंस कम रखेंगे, तो जहां जहां कोहेरेंस का हमने बताया कि कोहेरेंस should only be above 90%, then it's just going to replace it by a star. Now the problem with the star is, if I save this file, let's say I save this as coherence. Now a lot of software, let's say rephase, if I rephase is something to alter your phase, but let's just say I import measurement, and let's say coherence was my file, so it's going to give me a wrong measurement format because वहाँ पे बहुत star file के अंदर ये inserted है. Is that kind of clear with you guys? Rajesh, was that easy? Okay.
Yeah, okay.
Okay, so if I move on, let's say I'm keeping coherence extremely low, and I want to and how we don't interfere. Okay, one और FiR filters की और एक चीज है कि जैसे ही it already has a lot of delay, right? So we know it includes latency. जो हमारा latency पहले कुछ 7 मिलीसेकंड था, अभी हम डिले फाइंडर में देख रहे हैं 14 मिलीसेकंड, ऑलमोस्ट 7 मिलीसेकंड का ये क्रॉसओवर ऐड करने की वजह से एक लेटेंसी पैदा हो गया है. तो जैसे ही हम FiR फिल्टर यूज करते जाएंगे, तो उसमें लेटेंसी पैदा होते जाएगा, और लेटेंसी को कम करने के लिए we don't want अपना सिग्नल to be with too much latency. So एक जो प्रॉब्लम है, FiR filters does not work at very low frequency. You can say जो 200 या 250 hertz तक we don't use FiR filters because the time periods will be too long. It will be way too long to kind of get accurate information into the FiR filter. So इसके लिए, for reference, anything above 250 or 500 hertz is good enough for FiR filters. And for anything that's very low, because we know, आप देख सकते हैं कि low frequency में phase कितनी बार switch होते जा रहा है. It's having very large group delay. So if I quickly annotate something that with some lines, you can see there's continuous phase overlap in the low frequency area till almost 250 or 300 hertz. So इसकी वजह से we are not concerned about FiR filters too much in the low frequency domain. We're only going to look at maybe 250 or 500 hertz onwards in this whole spectrum. So again, I'm going to keep the coherence down and again go back to my FiR. मैं FiR वापस जाके बोलूँगा copy to ASCII, and if I go to in rephase, you can directly paste it, just import from clipboard, and you can see अभी ये import पूरा आपका measurement आ जाता है. ये इतना अच्छा क्यों लग रहा है? इसकी वजह से क्योंकि हमने range काफी बड़ा सेट किया है. If you change it to -30 maybe, it probably जो scale है, you just adjust it. But we'll get to that later how we do it. But for now, I'm just going to replace all these values. So all the stars have all gone. आप देख सकते हैं coherence की मैंने कम किया और सारे stars जो है काफी हद तक चले गए. And I'm going to save it as a coherent response. Now, when you're going on your DSP, which I'm using Marani right now, you can see on my input A, on my routing, I have something known as wizard. So wizard को हम एक बार खोलेंगे. There are two things. You can also measure. You don't need smart always to get this value. आपको हमेशा smart की जरूरत नहीं है. But smart is a great tool, so you can use it for all your measurements, and it's got 100 features that this doesn't have. But आपको अगर सिर्फ impulse में response measure करना है, so all you need is just your sound card, and I'll come to that later quietly, but for now you can say, can everyone see this open existing impulse response? और जो हमारा smart है, ये कुछ नहीं, ये हमारा impulse response है. This impulse response that you see on your top domain is convoluted with fast Fourier transform into your frequency domain and giving you a magnitude and phase. ये जो भी हमने measure किया वो actual impulse response ही है. So you just say open impulse response. I'm going to change my type to text. I know I saved it on desktop as coherence. And so this is showing me my coherence, and my window length, I'm not keeping it too long because I don't want too much latency. So जो हमारा window length है, I'm keeping it very small, जो आप देख सकते हैं. ये 5 millisecond तक ही रख रहा हूँ. And we've set the crossover, and you just press next. So again, I just press next. This is just telling you whether you want to see your group delay, phase, or magnitude. So right now, मेरे को magnitude में ज़्यादा interest है. So I'm just going to be looking at magnitude right now. There's something known as EQ target, and I'll come to that in a bit. So हम लोग को क्या modify करना है? I want to modify the magnitude as well as the phase. If I want only phase, remember जब हम subwoofer कर रहे थे Adamson के, and I was talking about how you are able to just modify the phase to ensure there's maximum cancellation. You can create all pass filters जहाँ magnitude को कुछ होता नहीं है, सिर्फ phase को आप बदल सकते हो, और phase के interaction आप देख सकते हैं, phase के interaction से काफी कुछ magnitude को आप influence कर सकते हैं. जैसे कि end fired subwoofer में हमने देखा कि पीछे की तरफ काफी कुछ हद तक कुछ energy आ रही है. What if you could modify the phase of one of the signals and ensure there's more cancellation on the back? So I don't want to keep it too complicated. How we get into that? That's something that would come into making all pass filters for modifying phase. मतलब phase को modify करने के लिए all pass filters होगा. हमारे input 1025 जो हम बदल नहीं सकते उसको. Max boost जो आप magnitude को अगर equalize कर रहे हैं, तो यहाँ आप सेट कर सकते हैं कि max boost या जो dip है वो कितना सेट करना है. ज्यादा अगर आपको ज्यादा डिप या बूस्ट नहीं करना है, तो ये लेवल को आप कम या ज्यादा कर सकते हैं. सो यू कैन मेक इट एनीथिंग दैट यू वांट. मे बी आपको एग्जिस्टिंग मेजरमेंट को 15 dB से ऊपर नीचे नहीं करना है. एंड देन इज द प्रिसिशन लेवल फ्रॉम 1 to 10 जो आप लेटेंसी आप सेट करना सकते हो. तो मेरे को मालूम है कि अगर फ्लोर मॉनिटर है, फ्लोर मॉनिटर में आर्टिस्ट काफी चिल्लाएगा अगर लेटेंसी ज्यादा है. मे बी आई वांट टू कीप इट 2 milliseconds and it'll reduce the number of taps and sampling rate accordingly. तो मेरा minimum frequency 250 है. मेरा जो मैं जहाँ तक आपको दिखाया 250 के ऊपर मेरा डेटा मेजरमेंट में काफी, और 20,000 हर्ट्ज तक मेरे को लेना है. और ये इसको मैग्नीट्यूड करना है या मैग्नीट्यूड और फेज दोनों करना है. इसमें स्मूथनिंग कितना है आप ये यहाँ सेट कर सकते हो. जैसे सेम स्मार्ट में हमने देखा है स्मूथनिंग कैसा हो सकता है. 1/24 एन ऑक्टेव करेंगे या 1/6 एन ऑक्टेव. जैसे ही स्मूथ करते जाएंगे उसका लेवल मतलब उसका रिस्पॉन्स कम पॉइंट्स पे ज्यादा एक्यूरेट होगा. तो आई एम जस्ट गोइंग टू कीप इट मे बी 1/24 एन ऑक्टेव सेम एज स्मार्ट. एंड यू कैन एडजस्ट योर जीरो लेवल सेटिंग. वेयर इज योर टारगेट रिस्पॉन्स. सो ये जो आप देख सकते हैं जो मेरा रेड है, रेड मेरा मेजरमेंट है, एंड मैं उसको जीरो लेवल एकदम ऊपर नहीं लेना चाहता हूँ कि ये सारे फ्रीक्वेंसी जो नीचे है वो बूस्ट होते जाएंगे. So I'm just going to try and keep the zero level somewhere around down, which is the average level, and it can cut everything else. Is everyone clear with this? So I'm just going to set my zero level at -2 dB. Is everyone okay with this?
Yes, I think so far.
And then you see अब ये left side में बोल रहा है कि calculate FIR का एक button आ रहा है, and this is giving me the option to calculate the FIR. So I can calculate, it gives me the FIR, and I again I can store the FIR to the device. So after calculate करके मैं store कर रहा हूँ, and it's calculating and storing, and let's just see what the response is. So it says, do you want to store all the configuration to PC? आपको ये file को PC पे save करना है. I don't want to save it right now, so I'm just going to say no. And अभी आप देख सकते हैं कि मेरा FIR bypass है. So I'm going to, since you already saw the response without the FIR, I'm going to keep it on and then see what the response is compared to my existing trace now. So So you guys can see that let me just remove the coherence so you guys can see the difference between after the FIR and with the FIR and without the FIR, and you're getting a pretty uniform magnitude and phase trace, whereas, I mean, of course, we've already used FIR, but if I remove this and probably use the summed at 90 degrees, this is the original जो हमने IR filters के साथ हमको magnitude मिला था and the phase response versus the FIR. So you're getting a pretty uniform FIR phase response in this entire convolution, what I can say. And let me just annotate the phase response. So you're seeing that ये जो phase response है काफी हद तक uniform है. Now this magnitude, although, and if I अगर इसका मेरे को specification sheet बनाना होता अपने customers को देने के लिए, then if I use a very good smoothing, say 1/6 an octave, and then कोई भी यहाँ देखेगा, let me just show it and say, wow, this is a great speaker. ये अगर मैंने specification sheet print किया और ये frequency response दिखाया, so it's going to be like, this is a fantastic speaker and let's buy it. But it's just इसको कुछ smoothing किया है, and if you remove the smoothing and keep it like, let's say 1/24 an octave, it's a pretty uniform this thing. And then उसको time windowing करेंगे तो it's even more smoother. So इसको आप देख सकते हैं, you're getting a pretty let's just compare it with the summed. The summed response is out here, and then let me clear these drawings and show you the phase trace as well. So आप देख सकते हैं, the phase trace is pretty uniform in your FIR filters, and you can see the change of uniform phase with this thing. Now going back in this, बहुत से लोगों को ये एकदम flat response पसंद नहीं है. You've seen if I open, let's say, acoustics idea of array morphing, they all add their own EQs and set their सब अपना अपना एक टारगेट रिस्पॉन्स, सबका अपना एक टारगेट रिस्पॉन्स है. जिसने एलोकुस्टिक्स से वेबिनार देखा है, आप देख सकते हैं उनके मेजरमेंट पे उनका अलग अलग टारगेट रिस्पॉन्स दिया है. When we used to work with DB technologies, they used to add, हवा में HF का एब्जॉर्प्शन काफी ज्यादा होता है, जैसे क्योंकि इसकी वजह से आपको थंडर जो है एकदम बादल की गरजने की आवाज एकदम लो फ्रीक्वेंसी में आती है. इट्स नॉट वेरी हाई पिच्ड इन रिस्पॉन्स. सो many let me just hide this. Many kind of over absorption of HF over distance, a lot of people using large line arrays for large distances would kind of have this kind of, or probably somewhere around here, this high shelving to about 5 to 6 dB, and you could add this with your your normal listing. So anything that एक बार आपने अपना signal set कर दिया, if you are going to be going to your input and say I want a high shelving EQ, तो ये आप देख सकते हैं कि मैं high shelving EQ maybe at 4K, maybe I'm showing you 6 dB, or maybe let's just, for easier to notice, 8 dB. And if I switch on my and I want to see capture. So you're seeing that after I've added a high shelving EQ, एक high shelving EQ add करने के बाद मेरा phase response वापस change हो गया. Again, there's a phase response that's added. Now let's go back and try and do this with a target curve. Okay, so I'm going to bypass this. इसको हम bypass करेंगे and go back to my wizard, and I'm going to open my existing ये coherence, and again just going next, magnitude and phase 1024 taps. I kept it maybe 15, I don't remember. Latency is 5 at set, 20,000 hertz. Okay, यहाँ आप देखेंगे यहाँ एक EQ target का window है, so I can actually set my target. Right now it's set at flat, but maybe if I could keep it at high shelving, and was it at 4K? I don't remember. 4K?
Yeah, yeah.
I don't remember the Q, but let's say maybe Q was 0.7, I think, and it was, I think, 8 dB. 8, was it 8 or 6?
I think you had set it to 6.
Okay, let's try 6. Okay.
Oh, 8 dB, 8 dB.
Okay, 8.
Yeah.
Okay, so this is my target, EQ target. Okay, and any smoothing type is minimize ripple, and there are you can have different all the ये जो आपके parameter EQ है आप कोई भी set कर सकते हो, so you can show the cursor and you can set this anywhere you want. जैसे भी आपको many people flow monitors, I know that the L-Acoustic X15 HQ has a bump at 110, and I actually personally like that response because it sounds quite good, and एक drummer को काफी अच्छा attack आता है. So you can set your target response as to what is your response that you want. I know in cinemas you have the X curve, उसका एक particular target है. So you can just set whatever target curve you want, and you can save it for future references or load your existing target curve in whatever you set, and whenever you want to bring it for particular venue, आपके कोई ballroom के लिए you feel that this kind of response is what you want, you can kind of get it. So you want to apply the target EQ target, yes, and again I'm going to normalize this by adjust this thing by -2 dB, which I had done जो हमारा flat response था, and I'm going to calculate the FiR, and oh sorry, this was a magnitude and phase, and the width was 1/24th, and I'm going to calculate it and then store it. No, I don't want to store it to the PC, and जो हमारा input है, I have bypassed this EQ. आप देख सकते हैं जो हमारा EQ था, it was +8 dB. The Q was 0.9. I've chosen 0.7, but okay, it's not too different. जो हमारा thickness, or I don't know how to explain the Q on high shelving filter, but it's not very different. But let's just go back to measurement and see what is my measurement and what is my phase like. So you guys can see if I response I disable. You guys can see that I had used my, and this was the original one. The blue one is the original without any EQ. The phase, in spite of adding an EQ with a target curve, the phase response remains the same. But the magnitude is what we pretty much wanted to get. We got the same thing. मतलब आपने high shelving EQ, you applied it in the impulse response domain, and you got, this was the response what you get, the pinky curve that you see right now. ये जो है हमें ये curve मिला, and the variation was that the phase changed from there, and then you could have a target response from your FiR wizard, and with the same phase response get the same magnitude. Is this part clear? So as you can see, जो ये EQ है high shelving का, उसकी वजह से हमें एक phase difference हमें मिला, और इसकी वजह से इसका नाम लोग बोलते हैं उसको minimum phase. They're called minimum phase EQs because it's introducing some amount of minimum phase variation in your measurement. Is everyone clear with this, with what we've done so far?
Yeah, just one question there was the 5 millisecond window size equal to the maximum amount of delay applied due to linearization of phase.
Okay, what's the question?
Was the like I mean, I guess that was about the latency.
I think,
Yes.
Karan, in your settings, now there was a setting where it was mentioned window size. So
Yes,
there you
the first one.
5 milliseconds, and then again in the time delay you have mentioned 5 milliseconds. So are those related?
No, they are not. 5 milliseconds initially is the time window. And if we go into FiR filters, I could explain about, that's the, okay, I'll explain it when I do my PowerPoint and show you what is the kind of windowing in terms of the measurement that we're doing.
Okay.
So,
And is the 5 millisecond that is put in the time window leading to the signal being delayed by around 5-6 milliseconds?
no.
No, no.
The
fine.
latency is a function of number of taps and
right.
sampling rate.
Okay.
ये जो हमारा latency है वो function है taps का and sampling rate. You guys want to just talk about something? I'm just coming back in. I'm just going to use the washroom and come back in 30 seconds.
Okay.
Yeah, sure.
Yeah, so just talk about something. I'll just be back. Just sorry, not gone since 3 hours. So hold on. Sorry about that.
We can take some questions if anyone has any. Nitesh, you want to talk about something?
I was just thinking of some questions to ask myself. So.
Okay, so some people were asking about what are the other FiR designers or what you can do. So you can create FiRs in third-party applications, like one is called FiR Designer, one is Reface. Then as you can see in this Marani, there is this FiR Wizard. So there are many different applications. Some are paid, some are free, and some DSPs come with their own application. So yeah, explain in Hindi again. Should it not show different delay time in Smart after adding the FiR filter? Yes, I think it has shown because initially अगर आप देखो तो Smart में जो FiR filter डालने से पहले delay time जो था वो 14 milliseconds था और जब FiR filter डाला है तभी वो 20 पे shift हुआ है.
I think the delay tracking was on that, right?
Yeah, the delay tracking was on. So,
yeah. So
around 6 millisecond का delay add हो गया सडन से. Explain in
and
Hindi
yeah, coming back to that, since you're adding that much more delay, like should you keep some kind of limit
to the delay being added?
Yeah.
I think it basically depends on how low in the frequency range you want to go.
Okay.
And again, then there are something like warped FiR filters where, you know, even if you go much down in frequency, the delay doesn't change. So that is also there.
Oh, okay.
Limit, I think we shouldn't go for anything more than 6 to 10 milliseconds, because then again, it will affect the kind of start affecting the way we perceive things. And then while in terms of time alignment, जब करना है, तो वो the time बहुत ज़्यादा हो जाएगा. And especially if you are mixing two systems, one is on FiR and if the other is not on FiR, then will be a pain to,
True.
Yeah.
One second, Karan, sorry, you're muted.
Sorry.
Yeah.
Am I audible now?
Yes.
Yep.
I think the thumb rule Adamson uses is pretty good, that they restricted themselves to 5 milliseconds, and that is kind of fine, tolerable in when you have between 5 to 10 and not exceeding that kind of. I mean, out here you can see that, and I'll show you a way to kind of bypass this entire thing. That so if I just let's just close this. And even if I just bypass my input FR, you can see that the latency, which is 20.5, जो हमारा latency जो है अब time of path is coming to 20.75 millisecond. So my latency is dropped by almost 6 milliseconds, and it's pretty much around that time that I targeted that I wanted to be around 5 milliseconds. So every time, and then now if I move it back to just the regular filters, the latency would drop further. So I've used FiR for my crossover between the HF and the mid, and I've used FiR for my linearization also. So one of the things that we can do, which I'm going to show you guys later, I could even, for example, let me kind of bypass this. So the first one and second one, input one is my HF, and I'll move it back to the infinite impulse response and get maybe 24 dB an octave, linkage rally, what we had said earlier. And channel 2 is again IIR, and it's again 24 dB an octave. Oh, what did I do? Sorry, it's on the high. Hold on. Yeah, it's already set. Cool. तो यहाँ आप देख सकते हैं कि मैंने क्रॉसओवर में FiR निकाल दिया, और अगर मैं इसको अभी वापस दोबारा देखूं, इसका आप सॉरी आई डिडंट कैप्चर इट, बट आप देख सकते हो इसका लेटेंसी जो है अभी जो 20 मिलीसेकंड था, 2 FiR के ब्लॉक्स हमने निकाल दिया, एंड दिस थिंग इज ड्रॉप टू 7.71. बट one of the things that we could do directly, instead of consuming too much time on this, we could इसको हम डायरेक्ट इसको यही रिस्पॉन्स को FiR अप्लाई कर सकते हैं. So even though there's a 360 degree phase shift, we don't need to use FiR in both the application. We can just use FiR in one on the input side. So let's just quickly capture it. And जो मैंने IR का ट्रांसफॉर्म है, I could copy to ASCII and move back here. I could what is the name of the file? I can just set, okay, coherence. Let me just replace all the values, and sorry, I don't want rephase. तो हम विजार्ड में जाके ये नए फाइल को देख सकते हैं, which is, I hope everyone, the yellow trace, we are having a 360 degree phase shift, and I've left time windowing on. This is why it looks so smooth. But anyways, let's not waste too much time on all these things now. So this is my window length. You can use the default. Those जो भी पूछ रहा है कि यहाँ window length क्या रखना है, I could set it to a higher value, and then it would still, my latency would be based on the latency. The windowing length is basically capturing what all frequencies are in that window. And since we are not considering too many low frequencies, we don't need to take a large window. It's in a nutshell, I can just explain it that way. And I want to make sure my target EQ is not this, so I'm going to bypass this. So back to 0. ये मेरा target EQ मेरे को high shelving नहीं चाहिए. And magnitude phase 1024, it's just, okay, fine, let's just keep it the same, 5 milliseconds to 20,000. Magnitude and phase, and 1/24 minus 2, and I will calculate the FiR and store the FiR. And it's right now bypass, so pretty much same response that you're getting, and Let's not bypass it. So आप देख सकते हैं कि I've managed to we are eliminating the entire phase shift by just using the input FiR and getting a very linear magnitude response. We're not getting too much, and we've for those who would agree, we are cutting more than we are putting. We are at the most adding some gain to 1.4 kilohertz. हमने ज़्यादा से ज़्यादा gain 1.4 को दिया है, पर बाकी जगह पे आप पूरे original response जिसको EQ नहीं किया था, सिर्फ crossover दिया था, हमने actually सिर्फ cut किया है. So there's no मेजर रिस्क हमारे पास. हमने इसके लिए हमने वो जीरो लेवल को 2 डेसिबल से कम किया. सो इट्स वेरी इंपॉर्टेंट यू सेट द करेक्ट जीरो लेवल, बिकॉज आपको अकूस्टिक कैंसिलेशन के पॉइंट्स को बूस्ट ज्यादा करना नहीं है. सो यू वांट टू ट्राई एंड कट द फ्रीक्वेंसी रादर देन गिविंग सम गेन टू सम सर्टेन फ्रीक्वेंसीज. सो जस्ट रिमेंबर यू नो व्हाट यू आर डूइंग, एंड यू नो पहले हमारा लेटेंसी 20 मिलीसेकंड था और अभी हमने उसको 7 मिलीसेकंड कर दिया है. So is this part clear? And then we can move on to measuring a box which has a crossover built in.
A few questions.
Yes.
So there's a question. A lot of softwares talk about averaging the response before linearizing the phrase, and we are doing it with just a single measurement. So the question is it okay, or what is the recommended procedure?
You average it. So for example, you need to kind of give third-party software, like you see Rephase, right? This is the original trace, and then in Rephase, there's something known as you got to tell the filter that I got to linearize my filter because you're using a crossover inside. If you're not using a crossover, it's a different thing. But how linearization works, you can go on the help of Rephase, or Rephase के website पे आप देख सकते हैं. It's a free version. I've given in my link to download it. Please play around with it. It's a brilliant tool. अगर हो सके उनको please कुछ पैसे भी donate करना, वो हमेशा ये बहुत से helpful. It's much better than the previous version, and it's something that's free. And if you guys want to see quickly, there is something known as FiR Designer by Eclipse Audio, I think. Yeah. तो इसमें FiR Designer में this is from a live smart measurement. You can आपके smart के live measurement से आप ये पूरा capture करके आपको FiR coefficient दे सकता है, and within a few minutes. It's nothing big, and it's faster than FiR, but then you have to pay I think $5.99 or $6.99.
Oh, it's very costly.
Yeah, it's costly.
Super costly, yeah.
But it makes your job easy. Now, if I'm going to be going what linearization is actually doing is it's kind of telling them that there is a crossover at this point, or इस पे expect करना कि there is going to be a phase shift, and at that point is going to try and it's the whole convolving algorithm that it has, that convolving around the crossover frequency, something like an FiR Designer does automatically. Rephase would need to be told. So if I'm say about I know I've used Linguist Rally 24 dB and Octave, and my crossover frequency is say 2500. It's going to tell this point that this yellow line ये जो है ये हमारा crossover frequency है, and and then again you can go to your. So again, when you're doing something like Rephase, what you need to make sure is that you do the gain before the phase, because what happens is जब भी आप gain को बदली करेंगे, for example I have this frequency which is 2406, so I could enter the frequency as 2406, and Q is not that big, and I could, the Q is too distinct, so maybe I need to make it like Q is 8, and make it somewhere around the 0 line. And आप देख सकते हैं कि जैसे ही मैं change करता हूँ, you're getting up, and if I say reduce this to which is 6049, I'm just going to do 2-3 frequencies. I'm not going to waste too much time because it's again going to take 5-10 minutes unnecessary, and maybe the Q is 4, and and probably a last would be 3502 maybe, and Q is maybe again 4. I could reduce this probably by this amount. And again, I have this bump 23661, which is a high Q. It's almost like a notch that I need to apply. 2361, and maybe 8 or maybe 10 for that matter, and kind of make it a nice this thing. And then you can go to your phase and bring your phase back to, let's say this is 6373, and very wide Q, maybe 0.5, as I need to lift the phase of everything. And this is, you could actually make the range plus minus 180 and increase it further and keep increasing the phase, basically 2394. And just keeping, so basically this is what you're doing with the phase response. I don't want to spend too much time just making this whole thing right now, but so your taps is 1024, जैसे कि मैंने देखा हमने input में हमारे taps 1024 है, और उसकी वजह से हमारा FFT length immediate calculate हो जाएगा. Windowing, again, it's not too critical. Don't get into too much complication. हम लोग को mathematician नहीं बनना है. हमारा sampling rate, we keep it at 48 kilohertz. We can generate 48 and 96, and we can just generate this, and so it's going to tell you, यहाँ आपको आएगा delay कि ये 10 millisecond से आपका delay आपको experience करना पड़ेगा. इसकी वजह से जो हमारे पास पुराना, if you double the sampling rate, for example, it's going to make it half. So if I generate, it should give you somewhere, yeah, it should give you 5 milliseconds as a delay if my sampling rate is higher. So I'm just going to keep it at 48 for now, and it's going to give you 10, and it's got impulse response is the name I set for it, right? What is the name? Yeah, file name is impulse, and I could go back, and यहाँ आप देख सकते हैं कि FiR import है. You can use an external FiR file. You can load it, and where's my desktop? Is here, and impulse, and it won't be as good because I'm not. मैंने यहाँ अभी काफी कुछ time नहीं देखा है. आप देख सकते हैं कि ये magnitude जो हमने 3-4 EQ set किए, यहाँ आपको magnitude आ रहा है, and I can store this to my device with a third-party software, and again do a measurement. Where smart is here. It won't be as good as this, but we could still compare it to the original. And which is without the, yeah. So you can see that it's corrected the magnitude. I've done too much of notching out here, and I've done it really quickly. And you can see the phase which was previously changing at, where was this? Yeah, out here is got now been made linear, but we've not reduced the phase of the lower frequencies and not increased the phase of the frequencies in this region. So which is why this phase shift that you're seeing is still there, because even in rephase we still had the phase shift. We didn't get rid of it. जो हमारा rephase का phase shift था, we didn't get rid of it, and you can do it. It's not rocket science, but I don't want to complicate too much. I just wanted to show you guys something in terms of third party software से कैसे import करते हैं. तो जरूरी नहीं है कि okay, Marani has it, but आपके पास अगर I know maybe 6 या 7 manufacturer है जो FiR filters use करते हैं, which is one is XTA, one is Lake जो है वो allow करता है, Rain does it, BSS does it, Marani does it. I'm not sure about many other manufacturers who do it. बहुत से manufacturers नहीं करते. एक anyways, don't want to talk about too many manufacturers, but अगर आपके manufacturer में inbuilt software नहीं है जो measure करे, या तो आप FiR designer use कर सकते हो, FiR capture use कर सकते हो, FiR filter host use कर सकते हो, rephase use कर सकते हो, rephase totally free है, और सभी सॉफ्टवेयर टेक्स्ट फाइल में इंपोर्ट कर सकती है। तो आप इसको पूरा फेस को लीनियराइज करके, मैग्नीट्यूड को लीनियराइज करके, एकदम जैसे कि हमने देखा यहाँ पे रिस्पॉन्स में काफी लीनियर रिस्पॉन्स हमको यहाँ मिल रहा है। लेट मी जस्ट हाइड दिस, या तो हमको ये काफी लीनियर रिस्पॉन्स मिल रहा है। एंड जस्ट बिफोर आई गेट इनटू एडवांटेजेस, डिसएडवांटेजेस एंड क्वेश्चंस, I want to quickly एक बार मैं इनबिल्ट जिसके अंदर पैसिव क्रॉसओवर बिल्ट इन है, ये हमने देखा कि हम लाइन एरे को कैसे कर सकते हैं, एंड यू कैन चेंज द EQ एंड टोनैलिटी हाउ यू गाइस वांट इट। एंड आई वांट टू क्विकली शो यू ऑन अ बॉक्स विद अ बिल्ट इन क्रॉसओवर। जैसे कि बहुत से लोग पैसिव बॉक्स यूज करते हैं जिसके अंदर क्रॉसओवर बिल्ट इन है, तो मैंने भी अपना एक छोटा सा घर का स्पीकर यूज किया है जिसमें हमारा पैसिव क्रॉसओवर बिल्ट इन है अंदर, तो उसको मैं जल्दी कनेक्ट करना चाहूंगा। सो आई जस्ट बी बैक इन 2 minutes. You guys, Rajesh and Nitesh, if you want to take some questions or talk about something, feel free to do so or share your screen. I'll just take 2 minutes.
Yeah, sure.
Nitesh, go ahead.
Nothing. Do you want to take this question here? How?
I think we'll take that out during the discussion.
Listen. Okay.
And then the second question, like, if I have stereo signal being fed into 4 speakers and a stereo sub, is it okay to linearize phase to avoid adding latency by adding it to the input? I do not get the question exactly, लेकिन अगर आपके सवाल का ये मतलब है कि अगर 2 sources है, तो क्या मैं, अगर मुझे टाइम अलाइन करना है, तो क्या मैं ये यूज कर सकता हूँ? आई थिंक इसके लिए a more better tool is using all pass filters, to be very frank. So if time aligning is what you are talking about, that's what I get. What does that question mean, Nitesh?
I don't know. I hope Sajak can.
Yes. सर जी, आप अगर ये हम लोग को सही समझ नहीं आया तो आप वापस एक बार लिख दो कुछ तो। Add FiR filters to the input.
In this case, he was adding it to the input only, right?
Yeah, I was adding it to the input. So like I said, both have its pros and cons. As you add, Adamson does it by adding it on the output because they want to maintain very steep filters on the, they don't use the input at all. आप output में जैसे हमने magnitude और phase दोनों किया है, आप is my screen visible, Nitesh?
Yes. I think I have
take this question, like,
yeah, I think he was asking that if you're, since you're having the outputs are connected to both the tops as well as the sub, and if you're linearizing the phase rather than linearizing on the output channel, sorry, as in putting the FiR on the output channel, would it be better to put it on the input channel so that your phase would be the latency rather would be equal between the
all
tops, all the outputs? That's what I hope that was the answer to it. And if
no,
so,
so
I think current
so
can answer that better. Yeah.
So what happens is that anything you do on the input is affecting all the outputs to which the input is connected, right? So
exactly, yeah.
You have to take a decision that what is it that you are achieving out of the input on the, that's why the input has a lot more taps and the output has a lot lesser taps, because it's assuming the output is always going to be cut off at some frequency and there's going to be a limited amount of frequency that it's going to be looking at. So that's why output has 512 taps and the input has this, 1024. Now, if it is your coverage that now, for example, if I'm using a 2-way box, which is what I'm going to be demoing right now with a passive crossover, I would just use the input because I'm not going to be using too much on the output side at all because it's already got its own crossover built in or something. But if it's something like an Adamson S10 line array where I want to make sure directivity is of concern, I don't want to use the input and I want to make sure the output is cut really steep and really low and with as much linear phase between the components and ensuring that the total overall system latency is not too much. So I don't want to be using input and output, but it also gives input a lot more, how do I say, it has more taps, so it's probably going to give you a lot more accuracy. But in the case of something like let's say a line array where you want to make sure the high frequency coverage is extremely tight and down to, let's say, 800 or 1000, because the minute the wavelength becomes bigger than the component diameter, let's say the mid range or the LF or something, you're going to have it spilling all over on the stage. So the advantage of this is that you can do it. If you don't need to do any crossover with FiR, then just do it on the input. Then and ensure that it's not affecting. You're not using one channel for a delayed speaker or a speaker in different like a home theater setup where you have probably a surrounds separate or something like that.
Good.
So if you have 4 speakers in your a home theater or something, I would probably use the outputs, because all outputs would probably be the room interaction again is there, right? So based on the position, your room would interact, and then you would probably want to cut some frequencies at the listening position based on the position of the speaker with respect to the listening position. So the room would interact with different speakers placed differently towards your listening position, and then I would use the output to kind of make sure at the listening position they're pretty okay and not, and then use the output. But whereas if it's something like a dual 15-inch like an JBL SRX 725 over a 728, yeah, ऐसा कुछ application में, I would probably just use the input on the tops, and that's about it. Does that make any sense? Oh.
Yeah.
Yes, Sajak ji is happy with your answer. So yes.
Okay, so let's just quickly, since we're already at 340, and I wanted to try and show aligning and summing of subwoofer with this thing on AU lab, but let's just quickly, and phase inversion, what Rajesh was talking about. तो बहुत जल्दी मैं 2A box को अगर देखूं, let me just see इसका, I'm gonna इसका सब EQ में जल्दी निकालने वाला हूँ, and on the input मेरे को ये bypass करना है. So मेरा output 1 पे मैंने speaker connect किया है, and oh, I've switched off the amplifier. Just hold on, I'll be back. Hold on. Input is back on, amplifier is back on, sorry. And ये छोटा सा ये छोटा सा स्पीकर है जो आप देख सकते हैं कि I know the crossover is somewhere around in the range of 3.5 kilohertz, जो मेरे को मालूम है, which is why I was checking the impulse response to just make sure that थोड़ा सा you can always move it by ±1 to make sure the peak arrives on time. और ये बहुत ही छोटा स्पीकर है, and I'm not going to waste too much time except showing that it's got a passive crossover. मैंने सिर्फ एक ही channel use किया है. As you can see, I've just used output 1 out here. It's got a passive crossover built in. There is nothing to expect and nothing extraordinary, but just to show you, you can do it on your जिसके अंदर crossover built in already. So I'm going to copy to ASCII and come back here, go to my wizard, and open, sorry, I'm not saved by impulse response. Hold on, sorry. And let me just quit. Has everyone understood rephase? I don't want to get into, I'm just closing it. So again, I'll just, instead of saving multiple files, I'm just going to open an existing, it's not opening, but anyways, notepad and pasting my impulse response and say home speaker. Wizard, open home speaker. ये हमारा response है home speaker का. Just quickly to show you, not to like get too much. And again, it's magnet phase, ye wo, blah 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 blah. Let's just say, or let's just keep it at 4 since it's a new speaker. And I want it up to 20,000. Magnet phase, 124. Let's just try 1/12. And calculate FiR. Did I normalize it correctly? Anyways, I've normalized. You guys understood concept of normalization, so I'm not going to.
Karan, there was a question on this thing. In this particular window, the green thing that you are saying, the green trace, it is the inverse of the magnitude trace.
Correct.
Right?
Inverse.
Okay. Yeah, okay.
So that is what's going to be the filter's response, really.
Okay. Okay.
Sorry, I didn't save store. I didn't do the zero adjust. Let's just save some time. I want to try and cover aligning the subs and the tops as well. And I don't want to save it. I remove the bypass and take a quick measurement again. Have I done it? Oh yeah, I've done a decibel offset. That's why it's giving you a level. So let's just keep both at, this is also, I want to keep it at, Rajesh, is there any shortcut to keep it at both? Okay. So this is,
just hit
what's
Y,
that?
Control Y, Command Y.
Okay, I put both of them at 4 dB offset, so it's visible nicely. And like I said, it's, I guess everyone is clear that we applied it to a box with a passive crossover built in as well. So दोनों एप्लीकेशन में हमने किया, हमने एक पैसिव बॉक्स को भी लगाया जिसके अंदर पैसिव क्रॉसओवर बिल्ट इन है, और उसके पहले हमने जो दिखाया वो एक एक्टिव स्पीकर भी था जिसके जो लाइन एरे में बहुत बार आप देखेंगे कि आपको एक एक्टिव स्पीकर दिखेगा. Is this part okay with everyone? Any questions that we?
No questions yet.
No questions as of now.
Okay, so basically you can do this and that. And just before we go on to aligning, what Rajesh wanted to do, just before that, I wanted to show you the, जो हमारे routing में जो है, जो एक तो FiR import, you can view the FiR file, whatever it is. So this is a view. And another important thing I really want to check is if you see the impulse response of an FiR filter, it is pretty much even on both sides, whereas जो आपका regular impulse response होगा, जो ऊपर का window आप देख रहे हैं, आप हमेशा देखेंगे कि ये एक side, मतलब उसका जो भी information आ रहा है एक ही side होगा, whereas FiR filter में आपको दोनों side you're going to see some ripple. So that's one way of looking at it, but I don't want to get into why, but you'll see that this is centered out here and you're getting ripples before and after. And one of the reasons is it uses information in your existing samples to create a new information. And I don't want to get into too much this thing because even I honestly don't know too much in depth of FiR, just the basics that we did in engineering. But Yeah, so this is जो हमारा regular impulse response है, जो हमारे speaker का, और ये जो हमारे FiR filter का है, you'll see some ripples on both the sides. It's very characteristic FiR filter का ये impulse response, and so this is the जो हमारे magnitude apply किया है, and then the phase, don't worry about it. This is the group delay, and बहुत जल्दी अगर आपको दिखाना है कि how we can do it, so you need an ASIO card, and then you need to set everything. In measuring, it gives you some basic. अगर if you don't have smart, if you not bought it, आप measurement microphone के साथ, don't worry too much on the ceiling. It should be more than 2 meters to ensure that the reflections are kind of eliminated. तो आपके speaker के ऊपर 2 मीटर के ऊपर reflection होना चाहिए. Measurement microphone से speaker तक 3 मीटर, height 2 मीटर नीचे तक. So it's basically making sure that so इसको एक बार आपका geometry set है, ये आपका room का measurement है. You can just say, okay, my geometry set up, and then just move on to next, and it's going to tell you that this is how you connect your sound card. Pretty simple. ये बहुत ही easy you know solution है. This is if you have your own this thing. So last bit, do we have 5-10 minutes to? Yeah, okay.
Can you
Pretty much on.
this quick question? Can you export the FiR filters from Marani?
Yes, you can.
You can.
So you can export it. You can, you know, a lot of things. It's a very good system. Quickly, just to before we move on, I just want to cover some things on the FiR. I'll just cover a little bit on the you know. जैसे कि हम देख रहे हैं यहाँ पे हमने सीखा था कि फिल्टर ऑर्डर जैसे ही बढ़ाते हैं उसका फेज शिफ्ट ऐड होना चालू हो जाता है. So you have 6 dB an octave, 12 dB an octave, 18 dB an octave, and as you keep going up, उसका phase shift add होना चालू हो जाता है. This is with infinite impulse response, and then this is what we had done last time. So I'm not repeating. We don't have time today. So basically, this is what let's say आपका एक input signal है. This is just basically in summary how your FiR input response filters are working. X, let's say is your input, Y is your output, और ये आप देख सकते हैं कि एक high frequency signal is superimposed on a low frequency signal. तो ये जो आप ऊपर का जो ripple देख रहे हो एक high frequency wave है जो low frequency wave के ऊपर superimposed है. And if you want this to be the output, it's as good as saying you want a low pass filter. आपको high frequency निकालना है. I can show you the addition of sine wave with इसका addition हम दिखा सकते हैं कम amplitude और high frequency कम amplitude का wave और low frequency का बड़ा amplitude का wave, and you'll get this result. But let's not get into addition of sine wave. But इसको हम low pass filter apply करके output हम ये मिलना चाहते हैं. So FiR filter is basically taking samples one after the other and passing it along one wire. So let's say what you see this Z is your window block size. So it's going to be someone was asking what is the window size of 5 milliseconds or whatever. This is what your Z is. It's actually, it's not exactly delaying after each other, but every sample is going through this window where, you know, the window is open and it captures information as it's passing along that line. So, you know, as X will go, X0 will be the first one to go along the line, X1, X2, X3. Sorry, this should have been X3. I don't know, I named it X4, but effects of doing a presentation just yesterday. And then हर एक जो sample हमने use किया है उसका ये जो coefficients है, they all are going to be multiplied by different coefficients, and all these samples are then going to be added, and then it's going to be given to you a vibe, just your output signal. This is just basically how your FiR filter works. Don't get into too much complication. आपने देखा कि बहुत से 2-3 step में आपको जो desired output है, अगर वो समझ में आया, we have to, you know, talk about the end result, and that's what's going to pay us in the end. So ये जो block है ये हमारा FiR filter है, and don't break word. Advantages, आप अपने phase और magnitude का independent control कर सकते हैं. उसका equalization आपने देखा बहुत ही accurate है, introducing almost no phase shift at all. There's no feedback loop. What happens is when you're using infinite impulse response filters like your regular Bell filters or even your crossover filters, it's using your existing inputs plus a sample of your output of the previous sample. So ये again, it's just going to get confusing, and I'll be showing diagrams of what we are doing. And ये inherently stable है. Just take it. ये finite impulse response, मतलब ये samples बहुत ही finite है. Infinite impulse response में we use windowing again over there to kind of avoid it going into infinity. तो inherently stable है. और इसमें आप बहुत से steep filters बना सकते हैं, जैसे कि मैंने आपको दिखाया. Very good. Disadvantages, it's a complex and expensive computation, तो आपको उसका hardware सस्ता नहीं है. आप देखेंगे बहुत मामूली प्रोसेसर्स में ये फीचर्स अवेलेबल नहीं है. इट्स अ ग्रेट इफ अ नॉर्मल डीएसपी, आपका नॉर्मल डीएसपी का प्राइस अगर 20,000 है, समथिंग लाइक दिस वुड कॉस्ट लाइक approximately maybe 60,000-65,000. so the price, it's computationally much more harder, so hardware is a lot cheaper. I'm aware that the chipsets are a lot more expensive. Latency, again, इसका अगर formula आप देखेंगे, is going to be n-1 coefficients divided by twice into sampling rate. So if it's 1024 coefficients, it's going to be 1023 divided by 2 into 96 kilohertz, which is value आ जाएगा 5 से 10 millisecond, and depending on how many coefficients it takes and everything. And again, is the traditional FiR filters are not extremely effective in low frequencies. उसका window size बहुत बड़ा चाहिए and whatever. Just before we wrap up, I want to quickly show you addition of this thing. So I'm going to go back to, let's just go back here, and signal generator हमारा है. I move it back to Soundflower, output 2, and इसका अगर AU lab को, if I just begin AU lab, and so I'm going to open my file, which was on my desktop. And I'm going to bypass everything, just play and signal 1. And okay, delay is set. So this is जो हमने देखा पहले starting में, it's signal 1, signal 2, and the sum. अगर हम इसको let's just use one of the signal as a low pass filter and the other as a high pass filter. So if I quickly go into AU lab and say one of them is, we're not using a band pass, we're not flipping the polarity. Okay, this is a low pass filter. Okay, and signal 2 is a high pass filter. And I don't want to show this. So low pass filter, high pass filter, I don't know इसमें कौन सा ये है, what frequency is using, but is this screen visible to everyone? This is assume आपके पास एक subwoofer है, which is your green, and then your blue is your mid high, and yeah, this is what you would expect. And at the crossover frequency, you can see that they are separated by probably 1, 2, 3, 4, 5, 6 blocks. Is that correct? Rajesh, are you here? You're the expert.
Yes, Karan, what happened?
I know, I was just showing summation between subs and mid high, and so are we on 6 blocks between the two signals in phase?
Yeah, this is a polarity inversion.
Yeah, but I'm just saying that
Yeah.
okay, fine. So let me just use a more yeah, this is more subwoofer like looking in configuration. So Rajesh, could you mark out the tangent of the slope at low and high?
Sure.
it's not easy to tell which is steeper in this, but the green is the subwoofer steeper in this case. So I don't know how to kind of explain it to everyone. Whether does everyone agree that the green curve is steeper than the blue curve? Okay, I'm assuming everyone agrees that the green curve जो है वो blue curve से ज़्यादा steep है. And if we are to add both these signals, we are probably going to be getting cancellation, because at the crossover region you are separated by 1, 2, 3, 4, 5, 6, just about 6 to 7 blocks. So it's about more than 180, it's about 190 degrees. So if I get the sum signal, ये हमारा sum signal, and you can see that you're getting a nice cancellation in this thing. Now, does everyone agree that we need to, because the sub is a lot steeper, we need to delay the mid high? Does everyone agree with that? ये जो mid high है, जो blue trace है, it's less steep than the sub, so we need to delay the mid, and I'm going to explain what's going to happen when we delay this and versus polarity inversion and then delaying. So Rajesh, please correct me, and please add in or stop me
Karan,
whenever.
that is what I'm trying to understand. Do you think that the mid phase is more steeper? I feel it is less steeper. I don't know, man.
Mid phase is less steeper. We need to delay the mid.
What do you feel? See, very frankly, I cannot make out the steepness in between the two, because below, like the one where it is going here, it's more of like we are beyond its magnitude, above 63 and all of that.
Yeah, but I just feel that again, let's just try. Let's just try. These are real world signals which don't exist in these are computer generated signals which don't exist in the real world. So we're just trying to simulate, because I don't have a subwoofer right now to kind of show actual summation right now. But
are you trying to show polarity inversion or something?
I'm going to be showing doing delay on a direct just directly applying delay, and then doing polarity inversion and then changing the delay.
Okay, sorry.
So if I am supposed to be saying, I would be saying that the blue trace would be what's the crossover frequency? It's about 95 hertz, and it's separated by can someone just note down the phase difference so I can quickly just calculate? So this is going from 112, and then the green trace at 95 is minus 91.5. So this is going from minus 91.5 to 0 to 112. So it's 112 plus 91.5. That's
210, somewhere around 210.
112 plus 91.5. So that's 200. Let's just say 200 divided by 360 into 1000 divided by 94, right? So it's about roughly 5.9 milliseconds is what we would expect to delay signal 2. So signal 2, which is a high pass, let's just say delay, and how much was it? 6 point?
5 point something, 5.5.
I forgot, sorry. 200 divided by 360 into 1000 divided by 94. 5.9. So, okay. Let's just say this is 5 and 0.9. So at this crossover frequency, let me just close this. And you can see at this, let me just hide the previous trace. Have I copied the previous? Okay. You can see आप सब देख सकते हैं कि ये crossover frequency पे हमें ये exact in phase लगभग दोनों का green और जो blue है दोनों का trace लगभग एक साथ दिख रहा है. But you can see that as we keep going away, the phase drastically changes. Is everyone in agreement with that? That we are in phase at the crossover frequency? Rajesh, can you move that green tangent?
Sure. clear, green. Where do you want me this?
No, that's fine. No need to move it. So
Okay.
if you show the sum signal, दोनों एक साथ polarity में है, दोनों एक साथ phase में है, not polarity, sorry. We can expect summation around the crossover. So let's just run a a summation. और आप देख सकते हैं कि ये sum signal जो है, it's pretty much in it's adding up, but you're seeing some ripple as you go ahead because phase is changing on this. So let's just sum 1. So does everyone agree that we are having in a crossover region are having here, but here you're having some ripple, and you're also seeing that the phase trace is no longer really that great. It's only at the crossover frequency we're having a lot of intersection, but जैसे ही हम और आगे जाते हैं, the phase slope completely changes. So one of the rules that we can apply is if this is a point that we are having them in time, the time period of that is so the time period of 90, we've done it at 94 hertz, so it's now 1000 divided by 94. This is 10 milliseconds or 10.6 milliseconds for the complete wave. And one of the options, that half cycle is about, it changes its phase to 180 degrees after half cycle. So one of the options is you could do a plus minus of half cycle and invert the phase of one of them. Rajesh, am I correct?
I don't think you can just phase invert. You don't have to add plus minus.
No. So, okay. So if I just phase invert, it's going to give me a completely, I believe it should give me, so this is, what do you want to phase invert? The sub or the mid-high?
Anything. Let's do mid-high.
Okay. So if you're inverting the mid-high, you're still getting cancellation. So one of the options is,
but this is what happens, Karan, this is what happens when you are doing this in AU lab.
No, wait. Let me get to it. Let me just try. Hold on. Okay. So usually, because when I read Merlin's this thing and it made complete, so you got to kind of reduce the delay by half the cycle and then flip the inversion. So if you have, what is the time period again? 10.6, right?
Yep.
1000 divided by 94 is 10.6 and divided by 2 is 5.3. So if you change the delay by, reduce the delay by 5.3 and invert one of them. So if you have I captured this? Let me just capture, the sum 1 plus 2, capture and say, this is how many seconds delay did we put? 6 point or 5.9?
We put 5.9, yes.
Okay, 5.9. And so if you reduce that delay by, 5.3. So let's go to AU lab and go to my sound delay. And so 5.9 minus 5.3, this becomes 0. And this becomes 5.3. And we've not yet done a polarity inversion on any of them. So if we are doing a polarity inversion of, let's say, let's say the sub. So you're seeing, let me just hide the sum response. And let me hide 5.9 as well. So you're seeing in this area, with the sub inverted in polarity, you're having, Rajesh, can you mark this crossover region and the phase trace of both of them?
Sure, will do.
Rajesh?
Yeah.
Can you annotate on the phase trace as well, like this a whole block from phase to magnitude?
Oh, okay.
Okay. So all you guys can see that in an area where the level is pretty much of significance, the phase and this thing is pretty much coming quite close to each other. So let me just capture this and say sum inverted, and this you can see is now with the sub. We inverted the sub, right?
Yep.
Okay. And if you're going back to my AU lab and instead of, let me just again not show this and go to my AU lab, and instead of inverting the sub, I invert the mid-high. And again, you're seeing, let me just show the sub, and a similar response with the mid-high inverted. And then I'm going to capture this and say mid-high invert. So just quickly checking on the 3 traces, and let's just switch this off. Polarity inversion was quite beneficial. If I just hide this, you can see that you're getting this bump out here, but you're also getting this, आपको यहाँ negative response भी मिल रहा है जब आप सिर्फ phase match कर रहे हो और polarity को change नहीं कर रहे हो. So polarity matching can, and जब हमने polarity inverse किया, आप देख सकते हो कि we're getting a nice full transition across this thing. But usually again, the rule I apply is whatever frequency you're seeing crossing over, and if you feel that the slope is not changing, again, if you see this, I didn't take the individual, मैंने अलग-अलग individual slopes का capture नहीं किया, but आपने देखा था कि दोनों signals का slope सिर्फ crossover frequency में match हो रहा था, और उसके पीछे और आगे the slopes were just going way out of control, which is why उसके ये हमें ये ripple आया, क्योंकि at this point probably जो phase difference है is kind of dropping to almost 180 degrees, but दोनों level का difference होने की वजह से ये पूरा level एकदम नीचे तक drop नहीं हो रहा है. It's probably dropping by maybe around couple of 2 or 3 dB. And then the other thing that we also may encounter is, let's say if we have this signal running, and a lot of mix engineers will face this problem, is that suddenly this आप सब देखेंगे कि ये जो bump हमें आ रहा है is suddenly not there at other frequencies like we saw in end fired subwoofer, but it's just there in the crossover region. So many of you, बहुत लोगों को ये थोड़ा अजीब लगेगा, and then you may want to add something on the input EQ. I don't have an input EQ here, but probably you can have, I'm just showing a parameter EQ on both to kind of reduce the level so that the sum level kind of comes down and becomes a lot more flat in terms of response. So आप कभी भी crossover region के आसपास कुछ EQ apply करेंगे, always apply it to the input, because you're going to be applying it to both the subwoofer as well as the on the mid-high. Now, one of the problems that we also encounter is that when we have, let's just disable this, and let's just say when you have aux-fed subs, when subs are on an aux, आपने देखा है कि बहुत बार हम subwoofers को aux पे set करते हैं. Nitesh, what is the probable level difference that you probably set on the aux? Probably 8 dB higher, 6 dB higher? Is he here?
Nitesh, okay.
Okay.
So very frankly, I don't think so. Nitesh, yeah.
Okay, so what is the level difference that you guys probably set on an aux-fed sub in in terms
I don't think we don't set a level difference.
Yeah, I know, but always you expect the aux-fed subs to always be a little higher. Like you don't expect, you usually don't.
Yeah,
nobody keeps them.
Yeah,
I just want to.
about 6 dB. Say.
What we do is we have the aux-fed subs and the mains at the same level. The only difference is when we are aligning, our subs are already during the alignment around 10 dB higher than the mains.
Okay. Yeah. So that's why I want to show that when you're aligning it, kind of, all the mix engineers, the sub level is much higher. So I just want to kind of show that when it is, let's say 0 dB, and let's just see the crossover frequency at that point. So when it is 0 dB, the crossover frequency is probably 90 Hz. ये यहाँ 90 Hz पे हमने crossover किया है जब हम लोग का level दोनों का same है. और जैसे ही हमने इसका level बढ़ाया, if we increase the level, let's say maybe a conventional listing that on shows that you see Okay, this doesn't allow me to take you more than 6, but yeah, I'll keep it 6. And
You
the
can
minute,
increase the output.
yeah, I can increase the output. Correct. Hold on. So let me increase the output by another maybe 4 dB. Okay, so probably as you can see, again in the L acoustic, where's the array morphing thing, you can see that the level on even like a VDOS or something is a lot higher than the rest of the you know, what people kind of expect. So they expect this 3 dB or 6 dB roll off from 100 to probably 1K, and you can see the crossover frequency, which was 94, is now 137. So if you're going to be aligning, align it where you're actually crossing it over rather than just keeping it at the same level, and then, you know, during the show enhancing the level, and then you know, I hope that kind of makes sense.
Karan, I want to add something over here.
Yeah, feel free. I'm pretty much done. So if you want to.
Okay, so basically I would go on to say that what we did, if you remember when you showed me the slopes, the slopes were actually parallel, and all we had to do was just invert the polarity. And when you do that, because they were parallel, they came again in phase in time. But when we were aligning at just the crossover frequency by adding the delay, we were in phase, but we were not in time.
Okay.
If you can just open up those things.
Yeah,
So
just let me.
because we are not in time.
So, and this is a high pass, and let me reduce the level back to 0. Okay.
Okay, so like.
And you want me to flip the polarity of one of them?
Yeah.
Okay.
And see, now if you observe this region and just go to delay, like back to 5.9 and no polarity inversion.
So I'm going to delay, hold on. 5.9. Okay. Why is it not changed? Oh, I've bypassed it, sorry.
And remove the polarity inversion. Okay, so if you guys see this area over here, and if you see the wraps that are coming in, there's again a wrap that has come in. That means we are not in time. So this is a perfect example of being in phase and not in time, and that's the reason only on the crossover frequency you get a bump, but then
Correct.
you do not get it even. And if you have aligned your system like this, which especially happens in the traditional method, जहाँ पे सब लोग बोलते हैं कि मैं टॉप्स में और सबs में एक साइन वेव डालूंगा, और जहाँ पे वो सबसे ज्यादा कैंसिल होता है वहां पे मैं इन्वर्ट कर दूंगा. So in that ना क्या होता है, you are aligning and in phase but you are not in time a number of times. और जब ऐसे system को align करते हैं तो even a small 3 to 4 dB change by the mix engineer in the sub levels throws your crossover all over the place. So the ideal thing is to align over the entire range, and I would recommend to see to it कि जो phase trace है वो पूरा completely match हो रहा है over, let's say अगर 90 Hz है आपका crossover, तो from let's say 60 to 130 तक अगर इतने इसमें आपका phase trace match हो रहा है completely, फिर mix engineer आने के बाद 10 dB भी अगर बढ़ाया आपका crossover नहीं बदलने वाला है. Yes, that's all I wanted to add.
Any question that we should be addressing?
We're done. Are we done?
Yeah, I'm done. I just want to show this as the last part of phase inversion as to why you don't inverting phase is not always a bad thing.
Yeah. Okay, you go ahead, and then we have one interesting question.
I'm done. I'm pretty much.
Okay. ठीक है. So one interesting question is, how do those phase wraps affect the sonic character of LF and mid frequencies and HF?
Rajesh will be in a better position to explain the phase wraps and but phase wraps is just basically it's just wrapping around further delay on. You wouldn't be having phase wrap if your delays are properly set. But if you're having excessive phase wrap within where your crossover region is, if you're not having too much phase wrap on, let's say your mid high and having too much phase wrap on your subs, then you've probably not entered the correct delay value in your delay finder, and there's probably a lot of difference between the time for between the mid high and your subs, and that's going to smear your impulse response. Correct me if I'm wrong. You can please answer that.
Yeah, it is. I think, see, about the sonic thing, it is everyone's personal palette, I would say. किसी को कुछ पसंद आता है, किसी को नहीं पसंद आता है. Obviously, there's a change in tonal character because of the linear phase. That's it. You might like it. I don't like it that much.
Rajesh, someone asked, can you again explain the part about matching between 60 to 130 across the entire?
Okay, so what happens is, अभी ये जो सिचुएशन आप देख रहे हो यहाँ पे, ये लोग इन फेज है, ये पर्टिकुलर रीजन में, और आउट ऑफ टाइम है. दिस इज अ एग्जांपल ऑफ इन फेज एंड आउट ऑफ टाइम, एंड दैट इज द रीजन. अभी इस सिचुएशन में क्या हो जाता है कि वी आर वेरी मच रेस्ट्रिक्टेड टू, हम लोग हमारा क्रॉसओवर फ्रीक्वेंसी देख रहे हैं सिर्फ. तो अभी हम लोग ये देख रहे हैं, ये क्रॉसओवर फ्रीक्वेंसी है, और हम लोग सिर्फ इसी का फेज अलाइन करने को देख रहे हैं. लेकिन जैसे ही अगर करंट, इफ यू जस्ट इंक्रीज द लेवल अगेन
of the subs, right?
Yeah, of the subs,
Yeah, just hold on. I just got to get rid of my. So I'm going to increase 6 on my this thing and maybe another 4 on. Yeah.
Okay. तो अगर आप अभी देखो तो अभी हमारी क्रॉसओवर फ्रीक्वेंसी जो है वो ये नहीं है, वो अभी ये हो गई है, which is here. And if you see at this point, now we are almost more than 180 degrees apart, क्योंकि हमने लेवल बदला और क्योंकि हम इन फेज थे और इन टाइम नहीं थे. But now just invert the polarity and remove the entire delay.
So I'm removing the delay and inverting the polarity.
अगर अभी आप देखो तो अभी मेरा क्रॉसओवर इधर रहे या इधर रहे, मेरे दोनों के फेस ट्रेस are well within less than 30 degrees apart.
Yeah, less than 30 degrees apart.
So even if अगर मैं यहाँ से लेके इतने रीजन में अगर मेरा क्रॉसओवर हो, जैसे कि अभी this is 12 dB more, can you get it down by like 6-7 dB? Yeah, good. तो अभी मेरी क्रॉसओवर फ्रीक्वेंसी हो गई ये, और मेरा फेज अभी भी जस्ट 30 डिग्रीज अपार्ट है. तो मेरा क्रॉसओवर रीजन जो है वो कंप्लीटली अलाइंड है. सो नाउ अभी आपने देखा कि इवन इफ आई चेंज फ्रॉम 12 dB मोर टू जस्ट 0 dB, मतलब 12 dB का अगर भी मैंने बेस सम्स में चेंज किया, आई एम स्टिल विद इन 30 डिग्रीज ऑफ फेज. सो if a mix engineer comes and changes the level, it will not make any difference. Yes, I think.
Yeah, I think that answered it quite well. So basically, you're looking at the slope across the entire, like a much wider frequency range, not just specific to that crossover frequency.
Yes. I'll just drop in a video link for that too.
Okay.
Cool.
Someone asked, when you use channel aux fader for aux fed sub, it changes. Yes, because even when you're changing the aux level from that particular channel, for example, from the kick channel, the overall level of the signal going to the subs is changing, and that would change the crossover frequency exactly.
Yes, it does change the acoustic crossover as we saw. Like we can just consider this electronic crossover, in a way transmitting as an acoustic crossover, not exactly the same frequency, but the same concept. और भले ही वो crossover frequency ऊपर नीचे हो, we are still aligned. So doesn't make a difference.
Cool. Anything else to be taken up?
No doubts, nothing.
No, as in no questions. If anyone has any questions, please write them in.
So I think it's good for now. I think we can call it a day. It's been a good long day. Again, we've gone past 4 o'clock.
Yeah. Can I get back to crossover filter and slope dB? कैसे decide? Okay, one question. Crossover filter and the slope, how do we decide it? कैसे decide करते हैं? ग्राफ देख के. अरे ग्राफ देख के. Okay.
You would be choosing your crossover point firstly based on also your मतलब आपका HF का size या for example ज़्यादा बड़ा नहीं है तो you don't want to cross it too low क्योंकि then you have chances of blowing it up. And
yeah, that depends. That depends on the component, right? On
component, the response, and then you see the overall response after applying a crossover. What is the response you're getting, and you want to make sure that the whatever crossover you're applying, along with the response of your HF or MF or anything that you're using the crossover for, it's within what you expect it to be, so that once you combine it with a subwoofer or something, it again sums up into the expected level.
Okay. The
exactly.
question is,
basically, you have to try it out. I don't think there's any particular ऐसे कुछ formula नहीं है कि अगर आपको ऐसे slope मिल रहे then you only use this particular type of crossover. Every filter, whether it's a Linkwitz, Riley, or Butterworth or Bessel, would give you a slightly different slope. So you have to measure both and then try to make sure that you are that your phase slopes are matched, if I'm right.
Yeah. I mean.
Okay. Yeah. The question was like how he wants to know how do we decide ये smart पे graph देख के, तो उस पे मैं add करता हूँ. So basically देखो आप अगर ये corner frequency पकड़ो अभी जो मेरी अपन slope is in terms of dB per octave. What is an octave? It is going from 63 to 125, from 125 to 250. तो अगर अभी हम ये subs का देखें, mid का देखें, 125 से 63 एक octave हो गया. तो 125 पे क्या level है? Around 0 पकड़ लेंगे. और 63 पे क्या level है? -9. So let's say this particular thing, this particular filter is decreasing the magnitude एक octave में 9 dB. So this is 9 dB per octave. Again, just by watching सिर्फ graph पे देख के you cannot exactly reciprocate, because अगर मतलब in my experience it has so happened that when we are electronically putting a 24 dB per octave का slope, acoustically it is somewhere around 15 dB per octave when you measure it in the speaker. Okay. So, yep.
I mean, I'd just like to add, if this is the bare response of the HF that you're getting, and then after you add after you add a 2.5 kilohertz, you can see the slope is no longer the same as the HF. It's different, and then that would be characterized by the response of the HF, which is in this stop band as well, because you see this slight bump that is coming as because of this gain that the HF driver has with respect to its inherent response. So maybe you would want to use something steeper, maybe you would want to use something not so steep, but you're going to make sure that you're trying to get a good slope, so that between your MF and HF, let's say the MF is out here, you're going to try and make sure that they sum and get an equal flat magnitude over there without adding too much. Yeah, and then again, I don't prefer very steep crossovers because it adds unnecessary phase delay and you can hear it, to be very honest. You can easily, अगर palm show होता था, मैं चाहता था कि आप आके FiR filter के FiR filter चालू करके और FiR filter बंद करके दोनों को एक साथ सुने, तो उसमें दोनों में आपको इमीडिएट फर्क नजर आता था, एंड दैट्स व्हाट फेज इज डूइंग. आपका मैग्नीट्यूड सेम होगा और फेज अलग होगा, तो और इन फेज भी होगा, 360 डिग्रीज का फेज शिफ्ट है. आप आंख बंद करके बोलेंगे कि इसका आवाज अलग है और उसका इतना पसंद नहीं है आपको. सो एडिंग टू मेनी स्टीप बहुत से लोग ऐसा करते हैं कि ये 180 डिग्रीज, लेट्स से 12 dB ऑक्टेव का क्रॉसओवर यूज करके दूसरे का पोलैरिटी इन्वर्ट करते हैं, तो दूसरे का पोलैरिटी डायरेक्ट 180 डिग्री से चालू हो जाता है. सो you get a pretty linear phase response without too much phase shift as well. So, and that's something that you'll see very common in well-designed boxes with a passive crossover. जो बहुत अच्छे boxes passive crossover के साथ डिजाइन किए गए हैं, crossover डालने के बावजूद आपको phase में ज्यादा shift नजर नहीं आएगा, क्योंकि एक का जो हम phase shift add कर रहे हैं दूसरे का polarity change करके आपको काफी linear phase यहाँ नजर आएगा, but not extremely flat, but not changing like by 360 degrees or something. So that's how you make a good crossover and design, and that's what is set for your आपके पूरे inventory के लिए, सब shows के लिए वो crossover set होगा.
Okay.
I think that's good.
Okay, thank you everyone for coming. See you next Saturday.
You want to just tell people what next Saturday, what we'll be doing?
So next Saturday, I'll preferably want to cover the slopes again of this crossovers, because many people have asked me to show slopes, but we didn't have time today. So we'll try and cover slopes, and then I'll probably do that for 30 minutes, and then talk about choosing the speaker, what each parameter means. हर एक parameter का क्या मतलब है, resonant frequency, DC resistance या QMS, QES, surface area, VS, ये सब सारे parameters का क्या मतलब है. You just basically go through it, not for too long, and then talk about amplifier specifications, talk about choosing amplifier कौन सा choose करना चाहिए सही speaker के लिए, थोड़ा बहुत horn के बारे में अगर time मिले हमें, and yeah, we'll try and keep it intact because it's a lot of theory, so I'll not want to make it too boring, but at least a little interesting so that everyone is, not sleeping by the end of it.
Yeah, I think that's pretty good for now. Some people have asked for a 3-way and 2-way speaker crossover frequency setup. I think next week,
let's do it next week. Yeah.
We'll come back to crossover slopes and just show. So I think that's good for now.
We can do it. Yeah, it should be good.
So thank you everyone. It's been a great session, a lot of interaction and good number of participants. So hope to see you all again next week. Thank you.
Okay, thank you. Bye-bye.